lecture videos, but this takes time because you need to get the type, the shape, the timeline of each of the content regions. And if you consider the speaker as well, it's even more difficult. So what we are proposing here is to use synthetic data for this, because with this we can generate large amounts of data on demand. However, as many of you will be aware, there is going to be some domain shift issue with this. So we want the synthetic data to be as realistically as possible, trying to use content from real sources, matching the layouts that you will see on these lectures, and also adding some types of realistic noise. And there have been some existing works trying to create data for different purposes, such as text detection, text recognition, and even some attempts of creating synthetic slides, but none of these match exactly the type of videos that we are targeting. So we are proposing our own model, which, by the way, is meant to be used during online training. So it's like you create the images on the fly, and the process goes through different steps. The first one is the content generation process, where basically we need to select which actual content regions are going to go into the synthetic image. But we have to keep in mind that despite having most of the content handwritten on these videos, there still be some typeset content, especially on edited videos online, because people put some titles, subtitles on them, and we want to get those right as well. So what we are doing is a combination of handwritten sources and typeset sources for math, text, and graphics. So here we are using some common known data set like IAM, the Chrome, Quick Draw from Google, Total Text, and even some render latex expression from the Wikipedia. But the problem of using different sources is they will be on different sizes. So we want to normalize the characters or the symbols on each of these type of content, so that we can resize them and have some control of what's going to be the average symbol size in the resulting image. Then for online sources, we also want to render them to offline images, and both processes can be a bit expensive. So we can do some cache pattern to try to save some time to make sure that this runs efficiently. Practice. So after getting the content that we are going to put on the image, the next step is to create some layout here. We had to consider that lecture videos are say not as clean as a technical or a business document, but they are also not totally random either. So they are somewhere in between. And what we are doing here is we are using some greedy layout generation algorithm that tries to create something that more or less resembles a paragraph with some degrees of freedom. We just give it the content regions and the aspect ratio, and it will create something that more or less looks like this. And after this, the next step is the content blending, which is basically putting all of these content regions with the layout over some selected background. And here we are taking images from existing datasets like MS Coco. We picked this one because this one includes some annotations for humans, like where are the humans on the image. And what we do is, based on the layout, we will blur the background of the content regions, and we will also, with some random probability, make the entire background of the image a single color, like a chalkboard or a whiteboard will be, right? And we will pick some contrasting color for the text, so it's readable. And we use the people mask to copy them back from the original image into the results, so the people are always included in the content, just like you would expect in an actual lecture. And with all of this information, we can also generate a corresponding pixel level ground truth. So this is like what the synthetic images look like. You can see that there is a mixture of typeset with handwriting and different types of like text or math together and people. Here is another example where the background has been replaced by a uniform color. Obviously, yes, it does not look like a lecture video, but you will be surprised to how much this can help to actually train those networks that are used to segment actual lecture videos. The last step is the data augmentation step, which will allow us to even add more variation into the sample, where we can use some traditional techniques that are used for convolutional neural networks, like zooming, cropping, rotations, changes of illumination, even adding some Gaussian noise. But there are some less common techniques that are very helpful in this context, like adding some compression noise. Take the image, pass it through some JPEG codec, and put it back into an image format. And this is a bit slow, but it really helps to reproduce some of the noise that you expect to see in an actual lecture recording. And apart from using synthetic data, we also experimented a bit with what we call a mixed data approach, which basically tries to pre-train the neural network on two tasks simultaneously. I mean, lecture video includes text and it includes people. So in a way, we want the network to get good features for both of them. So what we do is we train the network on using images from both data sets at the same time. And the network is only supervised on each batch, on each of the images, depending on what's the source. Then there is the actual segmentation of the content. Here we are experimenting with two types of segmentations. Like the first one is what you will call a binarization, where basically we're just trying to extract the content, no differentiation between what it is and everything else, including the speaker. But then there is the hardest case, that is the multi-class, where we want to differentiate between text, math, graphics, the speaker, and everything else. And for the binarization part, we are basically reusing a network that we recently proposed, which is called the FCN LectureNet. It's a fully convolutional neural network that can be used for extraction of content from lecture videos. For the multi-class segmentation, we are using a custom architecture where basically we took some modified basic ResNet blocks where we replaced the ReLU activations with GLU activation layers, and we use that for segmentation. So our experiments include obviously binarization and multi-class segmentation. We performed this using the lecture math data set, where we have 34 lecture videos, where 17 of these are meant to be used for training, 17 are meant to be used for testing. Originally, this data set did not include annotation of the content regions per type, so we had to annotate that as well, and we also had to make tighter mask, because originally it was using rectangles, but for segmentation we wanted like tighter polygons. And for people, unfortunately, it's very hard to get them like frame by frame. So what we did is we had to rely on an existing Mark RCNN model to locate the speaker on every frame, which is not perfect, but it works fairly well in practice. And here are some of the results that we got for binarization at the top of this table. We can see some of the originally published results for FCN LectureNet. And here is a comparison of what we got. If we use the real data alone, you can see that we get an pseudo F1 of 77.38%. If we train the network using synthetic data alone, it's a bit lower at 69.92%. But if we combine these two, using some pre-training on synthetic data followed by fine-tuning in the real data, there is a boost to 90.26% for binarization. And for all other conditions, we still get better numbers. Even like when we combine this with some text detection pre-training, we get even higher numbers than the ones that we had in the original FCN LectureNet paper. For the hardest task, that's semantic segmentation. If we use synthetic data alone, we can see that the average per pixel mean, the F1 score is not ideal. It's 58.1%. The problem is that some classes like graphics and text are not doing so well. But if you compare this with the results on training on real data only, it's not so different. Real data is just slightly higher. But when you combine synthetic data with the real one, the average F1 goes up to 73.6%. And then we also had the mixed strategy, right? So when we use the mixed strategy pre-training instead, we also get a boost of more than 10% of F1. And of course, if we combine the two strategies using mixed pre-training followed by synthetic pre-training followed by training on real data, then we get the highest F1 score of 73.7%. But of course, there is still a lot of room for improvement for text and graphics. So in conclusion, the mixed pre-training is helping the network learn good features that are good for both people and content detection. And when we use the synthetic data, our experiments show that it's really helping a lot. And while our initial results for semantic segmentation are promising in a way, there is some room for improvement, especially on content classes like text and graphics. So thank you very much for your attention. Are there any questions?
I have one question.
Press the
Press. Yeah.
So keep it first.
My question is like you have used this video lectures data, like the math. So you have like video, like when you talk about videos from like instructional videos like MIT, Stanford, CMU, so they have set design, very defined structure. Am I audible? Yeah. So they have a very defined structure of a chalkboard or whiteboard. Like, do you have utilized like when we talk about videos like animated videos like 3 Blue 1 Brown or like Yannick Culture, like private YouTubers have made their instructional videos. Can that be utilized in this kind of scenario for like rather than synthetic data?
I mean, the problem here is how do you tell how good is your performance on those videos, right? So you could use them, but you still have to annotate some of them first. You want to try on that. And for now, we are like moving from just pure handwriting to like a more diverse set that includes some combination of typeset as well, or some animations in the future. Yes.
There is quite some work about human occlusion, like within video. Did you look at these papers? Because they try to actually segment the human body that includes the background of the video.
Sorry, what do you mean?
There is several papers just recently, which is trying to detect a human, like a pedestrian or like a human body, including like any background. So if you take that and you match that with since you have multiple frames of the same video, you can practically reconstruct them without even using deep learning, just matching the pixels with the missing pixels, because you have right now some kind of missing part, which will be kind of similar to in paint. Did you try that?
I mean, not on this work, because here what we are doing is just segmentation alone, but yeah, we do have a lot of previous papers for lecture video analysis where we do consider the temporal. So content reconstruction is actually not an issue.
But the human uploading the image.
Yeah. I mean, yeah, there is a person moving in front of the content. So yeah, we do some temporal analysis where we can take the results from this, and we expect some temporal consistency when we can bring back that content. Yeah, we do have some work on summarization of lecture videos actually. But here we are only concentrated on the actual segmentation of the content.
Yes, I'm wondering why you're trying to segment people. Maybe you could just rely on the text section and you're just detecting text and graphic and technically.
Okay, yeah, that's actually a very good question. The thing is, the person is also an additional signal in the lecture videos. We had another work presented at ICFHR 2019. Actually, it was the Best Student Paper Award, where we were using the speaker to segment out the video, because based on what the speaker is doing, like erasing content or it's writing, you can actually get a lot of information from that. So it's like we are trying to, and we're a bit ambitious here. Right? We are trying to get everything with just a single pass, basically.
Maybe one last question from me. How do you decide which frame to segment? If you take a 1 hour video, you have like 100,000 frames.
Yeah, we segment 1 frame per second. So these results are taking 1 frame per second on the entire video. So yeah,
you are segmenting every frame.
More or less 1 per second. It's a ton of frames, yes.
Okay, so let's thank the speaker.
Thank you, Kenny, for a wonderful presentation. We will move on to the third paper now. This is
enhancing Indic handwriting recognition using global semantics information by Ajay Mandal and C.V. Jawahar. The paper will be presented by.
Good morning, everybody. So myself also. Now I'm going to present our work enhancing Indic handwriting face recognition using global semantic information. So in India there are a lot of script like Bangla, Devanagari, Gujarati, and all the script has like more than 100 Unicode characters. If you see, this is the Unicode characters of Devanagari script, and also there are in the script or in the language, there are few characters, the upper matra with the upper matra and lower matra. So if you see, so this is the lower matra and this is the upper matra, which is associated with the characters. And also sometimes the more characters, more than 2 characters or 3 characters combined together to create a conjugate character. So these are the example of conjugate characters which are present in all Indic languages. And when we come to the handwritten text, so as we collect
有没有看到我的眼睛？
handwritten text from different users, so due to their handwriting style, so there are a lot of variation in the text. Maybe the same text may be written in a different style. And also, as the writer used their pen to write the text, so there is non-uniform ink density over the words. And also, like as they are handwritten in a different style, so maybe like some characters are not recognized by the others. So there are a lot of confusion, which is the actual character written in the text. So due to that, there are a lot of the text are distorted or like blurred or incomplete character. So in that case, if we use the global semantic information, it will help to recognize the character better. So in 2020 in ICFHR, basically they proposed some architecture for the syntax recognition. So we inspired by this work. We developed one Indic text recognition model, which basically consists of 4 modules: rectification module, encoder module, semantic module, and decoder module. All of you know the encoder and decoder were used like CNN, RNN kind of architecture, but we have used the semantic module. This semantic module is basically the language model we have used to get the semantic information, which tells the decoder to recognize the word correctly. So here, this is the architecture. This is the rectification module. So due to the handwriting, so the images may not be there may be the geometrical distortion. So when you touch the rectification module, it corrects the geometric distortion. And the rectification module consists of spatial transformation network. Then in encoder module, this encoder module consists of a ResNet followed by 2-layered bidirectional STM, and it predicts the encoded feature. This is the semantic module. So it consists of 2 linear functions. The encoded feature first to the linear function and create the semantic information. So this semantic information basically, we try to during the training, we try to reduce the gap between the semantic information and the word embedding. For the word embedding, we use the language model, pre-trained language model, and during the training, we try to reduce the gap between the word embedding feature and the semantic information feature coming from the linear layer. And decoder basically consists of one GRU with the attention model, and the decoder use the semantic information as well as the visual information. So it has more power to recognize the word correctly. And the loss function we have used, the two kinds of loss we have used. One is the error. Error is between the cross into the loss between the predicted output and the ground truth, and the AD is basically the cosine embedding loss with the semantic information and the word embedding. When the training is completed, we use this model for the inference. But during the inference, we don't use this language model for predicting the words. So this is the dataset we have used for our experiment. So this is the publicly available dataset. This dataset consists of wide level features of the languages. Here, the number of writers is not too much, but yeah, this is the less than 30 users. And this is the statistics of the datasets. And we have done one evaluation study. Like if we use only the CLN architecture, no attention, no word embedding, no not using the word Google semantic information to the decoder. So this is the only what error rate this large. And then if we use the attention in the decoder, then it reduces the word recognition rate. And if we only use the word embedding then it reduce the word error rate. And when you use the attention and use the initialize the decoder with the semantic information, that it reduces much. And when you use all the three things, then it reduces much with respect to the recognition error. So this is the quantity score with respect to word error rate and the character error rate. So this is the state of the art what handwriting indic recognizer, and this is our model. You can see most of the all of the languages we get the better accuracy with respect to word error rate and the character error rate. So these are the example of the Pythagorean script. So the left side is all the word level images in the images, and this is the ground truth. This is the predicted by the current state of the art model. So here you can see those are the red colored characters. All are the not recognized correctly by the recognizer, but our model recognizes those characters correctly. So green are the recognized character correctly. And those are all the languages, like 10 languages, same samples the word images. And the second row is the ground truth, and this is the predicted. The first three columns are basically all the words which are recognized correctly. The last one is the words which are still not recognized correctly by our model. So for handwritten text recognition in Indic languages, we designed a decoder module with semantic information. This semantic information helps the decoder to recognize. Basically, it uses the language model or language information. It helps the decoder to recognize the word correctly, and it improves the word recognition rate 2.14% over the all 10 languages for the state of the art model. So these are the reference. So basically, this is the paper which is published in 2020 CVPI. This is the main paper, and this is the language model. In this link, you can find the 157 model for 157 languages. Thank you. Question.
Any questions?
Can you please be a bit more explicit about how the semantic information is annotated for reference for your system? Because somehow I understood that you top-down specify that these combined characters and diacritic symbols exist in these scripts, and I'm actually not seeing how to, let's say, feed this annotation into the system.
We are using the pre-trained language model. It already given into the we have just used the pre-trained language model. We are not trained the language model by our data.
Yes, but you have a module which predicts some semantic encoding.
Yes, Unicode.
On the semantic encoding
For every character, if it is a consonant character, like for this example, so for this is a like consonant character. This is a combination of 3 characters. So each character has a Unicode. So this is the sequence of 3 Unicode for this particular character.
Yeah, but it doesn't say anything about how the combination actually visually transforms the thing. So that is not anywhere inside. If that would be a simple combination of 3 characters, yeah, that wouldn't be interesting, I would say.
No, always like this.
No,
Yeah, anyway, we can discuss.
if you combine these two, you just get a concatenation of the 2 characters. Whereas if you combine these two, you're getting a completely different
Characters.
So the question is, how does the Unicode itself give you that semantic information? That's what I understood.
Yeah, exactly. Yeah.
Recognize the final form and then that back to up with the.
Actually, the font contains all the shapes and the combination of all there, you know. It automatically brings out the shape and then.
So yeah, the point that he was making is that this kind of shape information is already encoded in the font file. That's how you do. I'm sure. I mean, maybe we can take that discussion offline and have it later on.
For visualization, if you want to display this the Unicode into the system already installed this Unicode format or Unicode.
The question was in handwriting, how do you get that information in your model? I think we'll take the discussion offline. This is it takes a lot of time, and we are really running short of time. So if you don't mind, we'll move on to the next. Any other questions? Quickly, one. Okay. If not, thank you, Ajoy.
Okay, it's great to be able to share the stage with some other people doing some similar things. So in essence, what we're going to be doing in this paper is combining active learning with a transfer learning, and as opposed to the previous one that was combining self-training. So maybe just to get started, to give you an idea of some of the things we worked on in our lab. When COVID started. I thought it was interesting as we started talking about possibility of wearing masks if you felt like it in this session. Not a whole lot of us are really excited about that option after a few years of COVID. But one thing that we thought of is, well, there was actually an influenza, Spanish flu epidemic in 1918. What if we took all of the death records from the period around 1918 and actually read the death record to see if they died of influenza, and then try to map communities that had really strict masks, because they had doctors recommending wearing masks during the 1918 Spanish flu epidemic too. And we wanted to see if we could find a correlation. The ones that were really strict about masks, did they have less influenza deaths? So those are the kind of things that we kind of get involved in. Another one, it was actually interesting. We want to do handwriting recognition on census data and look through the time around the Second World War. And it's actually interesting to look how people reported their nationality, right? Because before the Second World War, a lot of people reported themselves to be of Japanese ancestry or German ancestry. And then after, how did they actually self-report? So those are similar things. We're actually funded by a company called Ancestry.com that actually builds family trees based on historical data. So we do read a lot of machine reading, a lot of documents like the birth and death records that are just paragraphs as well. And so as we've been involved in these projects, it's actually maybe the hardest part is always getting clean data to start training with. And most of you are familiar with how difficult that is. And so what we wanted to do, the last project we did actually had some French records that we were looking at. And it turns out that we never did we had, professional labelers actually transcribing the documents, and we never did get very good training data, and it really crippled our project. So we wanted to find out how to really get some training data that could help us to be accurate in our handwriting transcription. So anyway, again, just this notion of how do we get good label data and how do we use it most effectively. It turns out that hand labelers do all kinds of crazy stuff, like throwing in question marks when they can't understand something. No matter how much instruction you give them, they do things that are probably okay if you just want to present this to users, right? They might be able to see that question marks, oh, that would be, unknown values. But when you present that to a machine learning technique, it just drives it crazy. Or leaving out characters, some transcribers do that. And perhaps they ignore hyphens or other data that really messes up a machine learning algorithm. So there are some of these solutions that we've talked about. One that we were kind of fascinated with because we end up going between languages a lot. So we did a lot of work initially with German records. We then moved to French records, and we're now working on Polish records. And if you don't do something to add to your training set, the accuracy is fairly low. But how do you get to higher accuracy with the minimum amount of labeled data? So we thought, well, let's start with transfer learning. Let's start with the weights that we have, for example, from German. And let's use that with some hand-labeled French data, for example, to come up with a good model for French. We also looked at active learning. Can we somehow specify which samples to actually hand label that will give us the highest accuracy gain in our final models? And that was actually something that happened. So we worked with Ancestry, and they gave us a bunch of documents that were really poorly labeled. we said, well, we've got to have some more label data in order to be accurate. And they said, okay, tell me which records do you really want labels for? And we'll actually give those to our professional labelers. We've also talked in this session about synthetic data creation as another possibility. And so we're kind of looking at this notion of let's compare active transfer learning to some of the other traditional solutions to getting good training data for your model. So here's kind of the process that we're going to go through is we'll take a pre-trained model. And we've kind of been developing good pre-trained models for different languages. In the case, kind of interesting, in the case of reading these death records for the Spanish flu, doctors actually are their own classification of handwriting because they are really sloppy and they like to do all kinds of crazy things. So we would have several pre-trained models from different languages and different authors. And so the first step is then to go ahead and figure out which is the best pre-trained model for your data. And we kind of looked at several ways of doing this, but we're going to basically take a look at some samples from our data set. And then we ended up using CTC loss function to predict how accurate each of these models was on a sample of the new, some samples in the new domain that we want to look at. And so for those of you that are not familiar with CTC loss, we're basically going to go ahead and create a stream of partial characters and then concatenate those together. And out of that, we get a probability of accuracy for that sample. So then we're going to go ahead and select, based on that, which basically the samples that have low CTC loss values, so we're uncertain of how good their quality is, and we will ask our labelers in this particular case to sample those. For our experimentation, we did something similar to the previous research, where we would just train on a subsample of the data, and then when we figured out which active learning samples we wanted, we would go ahead and grab those predictions out of the data set. And so the next step then is to go ahead and use that CTC loss function to figure out how good we are so far. Train the model on the original data that we had, along with the labeled target values that we got by picking the ones with the lowest CTC loss values. And then go ahead and iterate until you start getting better results. And at this point, we can go ahead and stop training when we've met whatever criteria we have. And so from our perspective, most of our customers or funding sources have some, they want to, for the machine learning approaches, to approach a human indexer or labeler. And so we kind of keep this process going until we get some values that are similar to a human labeler. So if we take a look at this, in order to evaluate our results, we started with, first of all, just go ahead and train from scratch. You don't have any transfer learning from a previous model, then you go ahead and instead of using active training to select samples that have the lowest CTC loss value, we'll just select random ones. The transfer learning method, we'll go ahead and pre-train our weights, but then we pick different, we just randomly select samples to add to our collection. Our active scratch means we don't start with any particular weights, but we do pick samples that have the lowest accuracy to add to go ahead and label. And then finally, this active transfer process that has weights pre-trained, and then we go ahead and select samples that we think will most help our results. We started looking at IAMS, RIMES, and CBL test data. And if you take a look at it, again, Scratch is normal learning, and our active transfer here seem to be at a lower. Here we're taking a look at character error rate. So it again significantly less data to get a particular error rate. And here we're pre-training on the IAM data set, transferring those weights over to RIMES, and then selectively, actively picking samples to help us to get the best results on RIMES. So it seems like that active transfer learning was good, followed by this active Scratch. So even if you don't start with good weights beginning with, that the active learning actually was pretty effective. Going the other direction, however, so if we start with RIMES, so the French data, and try to apply those weights to an English IAM data set, it turns out that the active transfer learning was about the same as starting from scratch and not using transfer learning. That was kind of interesting. I'm not sure exactly why the two data sets differed in their ability to transfer valid knowledge across those, but I thought that was kind of interesting. The next step we did was we said, well, let's see how much data, if we're doing, again, active training, we're picking samples to actually label, how small amount of data can we actually use to get to the same accuracy that we had starting from scratch? And so it turns out that, you know, for example, on the RIMES data set, we could get the same results with about 18,000 samples as you could with 49,000 samples starting from scratch. So we saw a significant decrease in the amount of data that you had to hand label. And so similarly on the IAM data set, we're getting significantly less data that's necessary to get to the same results. So conclusions, we feel like this active transfer learning is an effective way of, again, using this precious resource of human labelers to actually improve the accuracy of your data. It fits new data sets quickly with less data. We're also working on journal transcriptions with historical documents for just journals, different authors. And we'd like to take a look at more sophisticated transfer learning methods and maybe combining some synthetic data into this process as well. Thank you. Go ahead.
Thank you for the talk. I think you're working at word level, but not line level. Do you have any idea your method to be extended to line level or document level? So sometimes we have full transcription or full page.
Yeah, so I mean, obviously your accuracy starts going down as you do more line level work. But we're just really stuck on word level right now.
Any other questions?
My question is like, you work with Ancestry, right?
Yes.
So you do some real world deployment, something like that?
Yes.
Yeah. So I maybe like, how do you tackle the problems for real world deployment, like domain shift, or like here from a journal purpose, like from one is source language, like say German,
right?
Target language called French. So how do you deal with domain shift issues if you are generating completely new data set? Like let's say like you're getting a new data sets out there from journals or something. How you tackle that problem in active transfer learning, real world deployment settings?
I'm not understanding exactly the question, but I'll give it a shot and you tell me if I'm wrong.
Give you more like a simple example, like you have a target domain
Yes,
and a train domain, train distribution and a target distribution.
yes,
In real world deployment, like as you working with Ancestry, there is an issue like when new data comes, when new data is generating and it is in the pipeline, how you tackle that problem when the scores go down, the word error rate goes down, like how you tackle that domain shift issue, or like even in the
yes. So I think what we're talking about here is we're assuming that we start on a project, we're going to build a machine learning model, and then we'll apply it. They'll apply it to the millions of records they have from there. And we haven't really gone into how you continue to incorporate results from that during the processing and production data. But I think that is a great question, because theoretically you could learn as you went from more data, as the previous speaker kind of talked about.
but there is a limitation of data. The data is limited, so you are having this like active learning and the active transfer learning is meant to tackle that limited data problem as well. So when you talk about synthetic data, synthetic data will also generate some kind of domain shift issues as well, right?
Yeah, that's a great question. As far as our perspective, we're not involved in the production part, so we kind of hand it off to them, and they take everything after that. But if you did have access to that production part of the process, that would actually be beneficial.
Any other questions? Can I ask one last question?
You may.
So, active learning is typically when you have large amount of unlabeled data and then you don't have enough labels. But transfer learning are setups in which when you have the overall amount of data is very less, that you want to transfer your learnings from a previous domain. So, in practical sense, what is the bottleneck in your problem? Is it the lack of amount of data, or is it lack of amount of unlabeled labeled data that's
So the lack of labeled data. And so I think that's the most expensive piece, is getting labeled data. And so we want to minimize the amount of labeled data to get.
And in that context, like you have a deep learning network that is trained between these iterations.
Yeah.
So how is it practically done? Like you have a batch of documents that you use, label, and then go for the next round, or because the training would take some time, I see.
Right. Yeah. So that piece of labeling the data for practical pursuits takes a long time. Unfortunately, like 6 months to get them to label something.
Okay.
Yeah.
That's great.
Thank you.
Good afternoon, everyone. I'm Simon Corbier, and today I will present our work, which is entitled A Combination of Explication Segmentation with Seq-to-Seq Recognition for Fine Analysis of Children Handwriting. So, we are interested of analysis French handwritten word in dictating concept. So traditionally, a recognition model takes in input an handwritten word, and as input, it produces a sequence of character. In our context, we are interested of analysis model. So as is input, it takes an handwritten word, and as input, it produces a segmentation of letter and the recognized letter. So why do you do that? In learning education context, the children made some mistake compared to an instruction. In this case is alors, which means then in French. And this letter segmentation allows the system to produce some feedback. Like I say, we are interested on children handwriting, so the children learn how to write, so they are deformed handwriting. Sometimes it's difficult to understand even for a human. And they made a lot of spelling mistakes. So phonetic mistakes, they add letter, forget letter, and many more. So in this work, we are not starting from scratch. We are beginning with an existing system which was developed for kindergarten, which is currently used in a French school. So this system was designed for a recopy context. So As input, it takes the instruction given by the professor and the handwriting made by the children. The first step is to compute a segmentation lattice. So with some heuristic and expert knowledge, we cut handwriting at specific point to predict this lattice. Then for each element, we compute letter hypothesis. This step was guided by the prior knowledge, which is the instruction. And then we compute the best path with edit distance to search the good word. And with that, we can make feedback to the children. So this is the starting point. So it works well in recopy context, but if we extend this on a dictation context, so the children heard the word, they made a lot of misspelling mistakes, so this guiding strategy become obsolete. So here come our work. So the idea of this work is to use this existing analysis system, which has accurate segmentation, but approximative recognition, with a deep learning model, which is a sec-to-sec model, which has approximative segmentation, but have accurate recognition. The idea of this combination is to have an accurate system on segmentation and recognition. So let me detail a little bit about our contribution. So the first contribution is to use the sec-to-sec model as a prior, because it's a good recognition performance. So in this existing system, the new source of prior is the result of sec-to-sec model. If you use this example where the dictated instruction is 100, which means 100, and the children write ZM, which is totally different. If you use the first strategy A, where the system was guided by the instruction, they failed to recognize the word and to provide a good segmentation. If you use a strategy B, where you use a phonetic hypothesis to guide the system, so it's a pseudo word similar to the assumption. Again, the system failed to recognize the word and provide precise segmentation. If you use the strategy C, where we use the sec-to-sec prediction to guide the system, here the system can recognize the good word and provide the accurate segmentation. So, okay, it's worked well. But as you can imagine, it's repose solely to the sec-to-sec prediction. So, if you take another example where the dictated instruction is bien, which means good, here the sec-to-sec model make a mistake to predict the letter B. So he made a mistake in recognition result, but provide a good segmentation. So the second contribution is the idea is to use all these guidance strategy, so the instruction, phonetic, and the sec-to-sec prediction, and to make an alignment to produce a new source of prior knowledge. Because each strategy sometimes made some mistake, but if you align them right, you can have a new source of prior knowledge. So this is the fusion part of this contribution. And the competition part, the idea is to analyze the handwriting made by the children with all guidance strategy. So the instruction, phonetic, and sec-to-sec guidance. Use the fusion system to make another prior knowledge. And at the end, make a competition to keep the guidance strategy who has the best score in terms of recognition, to give feedback to the children. So let's take a look at some results. So in our work, we use a private data set, which was collected during different projects in school. They are composed by French cursive lowercase word. And for experiment, we evaluate our model on two aspects, the recognition part. So we use recognition rate, and the segmentation aspect, where you use the classical intersection over union matrix. The first line corresponding to the sec model only. So like I said, we had accurate recognition, but poor segmentation performance. The second line corresponding to the existing system, we developed for work copy context, but it will extend to dictation context. They fail to recognize properly, but have great recognition performance. The third line corresponding to the phonetic guidance was the first strategy to improve the system. So with phonetic proposition to guide the system. So it's a little improvement of recognition, but it's not satisfactory enough. And the two last correspond to our contribution. So with the sec-to-sec prediction and when used fusion guidance and competition. So we can see the use of multi-guidance strategy allow to have a system which are accurate and recognition and segmentation. So I'll present briefly our two contributions. And for the further work, we work on to design generic model when you don't have to use instruction and phonetic guidance. So with semantic segmentation network like mask RCNN. Another point is to make more experiment in classroom to verify if our system is efficient and robust. And the last point is to study how to deliver feedback to children to see it's interesting or not. Thank you for your attention. And if you have a question.
If you have any question, you can ask.
If you have any question, do not hesitate. Yes, please.
So when I understood you correctly, you trained the sequence-to-sequence model solely on the data that you collected from children handwriting. Is that correct?
No, you do that first, but there are not enough data. So we train the sec-to-sec model on IAM, then fine-tune children data.
Okay, that actually answers my question because I was figuring if it would help to include, for example, added handwriting, or if that's like too specific for the domain. But if you do so, then
sec-to-sec need more data to perform well. So
thanks.
Anyone else?
Thank you. I was recently involved in a segmentation project for handwriting, and it was quite challenging actually to find a good ground truth for the segmentation for cursive words and for characters, especially within the word. So for children's handwriting, I assume it's even harder. So do you know how in this database that you use, how the ground truth was created?
By us. So a lot of word was annotated at word level by a company, and some researcher word annotate some data at level by a later level. So not all the best because it's very time consuming to annotate.
Did you make a hard cut for the ligatures between two letters, or did you define some kind of area where one character
annotate the word? The letter
at the character level.
At the input, the handwriting are online, so we don't have to put bounding bonds. We have just cutting point.
I understand. So you have one sharp cutting point that was defined by you, basically.
Yes.
Okay. I think it's something to reconsider because it's not that clear where one character ends and when the other starts, right?
Yes, because some annotator can put the point here or here, so it's a little bit in data, but We can add a tolerance zone, but they are more difficult to annotate because it's another type of data.
Okay, thank you.
It's if he was wrong or it's difficult. So it's like the same for the letter O or A that depend of the annotated data. So the system say it's O or A. So it's they're not a right result.
Okay, maybe with the last question is from Zoom. And the question is the following. Did you create a guideline how to transcribe the children handwriting?
Not yet.
Not yet. Okay, so thank
Good afternoon, everyone. I am Burak Madi from Ben-Gurion University. I represent our work text alignment on image domain. This work done jointly with Ahmed Ruby and Jihad Al-Sani. But let's start. Okay, we will include introductions to the problem, explain the motivations and the problem. We will have we'll have algorithm overview over the algorithms and that in that domain. We will make a step-by-step example, and finally we have visual results. We will start with the problem. Before printing machine, we're inventing manuscript reproductions have done manually. This type of pre-production leads to differences between the copies of the same manuscripts. These differences could be in the text domain, page layout, writing styles, paper and pen types. For example, here we have two manuscripts of the same, two different copies of the same manuscript in Arabic. They have different writing styles and number of page lines. This example, for example, we have also in Hebrew, we have like different in page layout where the middle part in the left side match the text context of the right side. Okay, that's why we need this for research tasks. Recovering original manuscripts from available copies is essential for manuscript critic, which aim to authenticate, edit, and publish manuscripts. Also, in another science field called systematology, where they attempt to reconstruct the transmission of text based on the relation between the surviving copies. One important thing before we continue, the reconstruction of these two fields needs a very essential and vital process called manuscript alignment. The manuscript alignment is done manually by highly educated professionals, and also it's time consuming and expensive. Then we need to explain what is manuscript alignment is. As manuscript alignment is a process where we locate the shared and the different text of the different copies for the same manuscript. Then, since it was done manually and it's time consuming, and algorithms has been invented to exceed these limitations. We have two types of manuscripts that could be done in order to find the alignment between two manuscripts. One of them is text domain manuscripts. When we take the manuscripts, we applying transcriptions and computing the alignment in the text domain, while the other part is image domain, where we computed the alignment on the image domain directly. Okay, limitation of the text domain. Handwritten recognizers do not always provide good accuracy when applying to historical documents, especially for Arabic documents. Also for line and what we call, when we create synopsis for philologists to explore visual features in addition to text, is very essential to have results or image results. While reprojections of the text alignment results back to image space is very challenging. Our algorithm is image-based algorithms. As before we continue, we will explain the data set. As we have 4 Arabic historical manuscript data sets, each 2 are copy of the same manuscript. This from Arabic book called Milal wa Nihal for Shahrastani, who was authored in 1127 to 1128. This is from VML HD. It's another data set which include 5 different manuscripts. Only 2 books of them have the same, there are 2 copies of the same manuscript. Then we take these 2 books as a VML HD 1. We call this align 1 and align 2, VML align. We just number each one of them. The same thing goes for this data set, HD1 and HD2. Our workflow consists of 2 stages. We have a subword detection process. And after that, we aligning the subwords from the 2 different manuscripts. As for subword detection, data set preparation, we sliding a window on the text line of these manuscripts. And after that, we sliding a window with a stride of entire subboard, with entire subboards. After we sliding the window, we crop the patch of the sliding window and resize the labels inside or the detection bounding books of these labels according to the resize ratio or the batch size. Let's see, we could, okay. Then after that, we adapt, sorry. Then after that, we adapt YOLO model to detect the subboard inside these patches. We train YOLO, we split the data set to predict the bounding books inside the patches. For each one of the data set that we mentioned before, we created a detection data set. We just added a prefix before each one of them. And we adapting 2 model of training. One of them, we training YOLO from scratch, and the other one, we used pre-trained YOLO. The pre-trained YOLO, we picking external book, applying the same data procedures, and making a tuning over each one of these data sets. And as we can see that the pre-trained version giving better results than training from scratch. The aligning part, the data sets that we mentioned before, having two types of labels. One of them is bounding books, and the other one is transcription of these bounding books. We take each 2 data set of the same manuscript, the different copy of the same manuscripts, and we crop these subboards and group them together based on their transcription. For VML D1 and HD2, we're creating subboard HD, which contain 21K pair subboards. And for the second one, it contains almost 52K subboards. In order to estimate for each 2 subboards, we need also to estimate, in order to align to these 2 subboards, we need to calculate if they are similar or different. To do that, we adopt CME model to calculate the similarity. In order to train CME's network, we sample a positive and negative pairs. Positive pairs, as an example, they are two subwords that have the same transcription, have the same semantic transcription. Negative, the negative pairs are, otherwise they are negative pairs. We compare or we test the state of the art with using our data set, the first one. And when we're using a branch in the CNN, model in the CMEs, ReasonNet 34, we outperform the state of the art with a great margin. As let's like going on step-by-step example over all the workflow. First of all, we extract two text lines from different books of the same manuscript. After that, we sliding a window with the 50% of overlapping. We applying YOLO to detect these subwords with the overlapping window. We applying non-maximum suppression to remove or to remove redundant bounding box. And finally, we get bounding box around the subwords in the two sentences. After that, we cropping these subwords in order to make a group of sub-images, similar to we could like consider them as a sequence of strings. After that, we order them in a matrix, and filling each cell in this matrix with the similarity of trained CMEs over the two manuscripts. After that, we applying LCS, longest common subsequence, based on the result of based on the filled matrix using the CMEs network. Here we treating each subwords as a character, while the CMEs could in the image domain could calculate the similarity between them. As we could see, when after like applying the alignment using LCS, we making like backward finding the solution. This is part of the LCS. And as we could see it making alignment between two subwords that have the same semantic meaning. For visual results, this is like two lines from different manuscripts. And as we could see that like these two parts have the semantic meanings while they're having different writing styles. This one is also having a different different writing styles, have the same meaning but have different writing styles. For conclusion, we show that text alignment in text domain have some disadvantages. We present a new approach for manuscript alignment on image domain. Our approach utilizes YOLO for detecting of the subwords and CMEs network to calculate the similarity between them. Finally, we adapt a longest common subsequence and to treat a string of image as a string of characters to obtain accurate alignment. Thank you.
Thank you, Barak, for this talk. Just in time, it's perfect. Thanks a lot. Is anybody have some question?
Are you assuming that the two documents are perfectly matched, all the words, or there were different writings, so there'll be some gaps?
They have overlapping, but they are not like identically matched.
So slight variations on the same theme.
Yes, it's sometimes like it having also like some words in Arabic have written over decades or over centuries. Like some words was one connected word, and sometimes it's split. And in this word, the alignment will not give results
Mhm.
It's not the same.
Okay, I've got some similar stuff with some reprint, different printings of different books where they made edits between editions. Thank you.
Any other question?
I'm just wondering what algorithm you use for your alignment once you have your subwords. I know there's a Needleman Wunsch alignment that allows you to put in gaps or mismatches and give them penalties. Have you looked into any
Yes,
algorithms like that?
You mean like in LCS, like edit distance? They're also yes, we in the for gaps we also giving a punishment if there are gaps or not. But if there are gaps or not, for example. For yes, like in the formula in the full paper, we also written that the gaps is we written like punishment for gaps that based on, like for example, if we having a very long subsequence and we have gap here, we will giving a less punishment, and we aim to align this one with the corresponding one, because the more we have a big alignment, it will be less probability to mismatch in the middle.
Thanks. Last question.
Thank you. Is it possible to do alignment at page level or at volume level for the
Yes,
text?
in order to do page level, we're building what we call a super line. We extract all the text line, concatenate them together, and you could apply a super alignment on page level.
Thank you.
Okay. Hello, everyone. I'm Suman, and I'm a final year PhD student at National University of Singapore. And I will be talking about our work towards understanding and improving handwriting with AI. So now, what makes our handwriting good, or what makes anyone's handwriting good? If there is an aesthetic judgment of handwriting that follows implicit rules, can those rules be recovered by observing the good and bad samples? To answer these questions, we apply explainability techniques to the classification of good and bad handwriting. And we show that indeed it is possible to recover those rules from those samples. So to this end, we developed an AI system that uses a modified version of line as an image explainer and generates images consisting of suggestions for improvement. So what we do first is, this is the general overview. We first label a given data set based on certain rules or criteria. Then we train a classifier based on these samples. And then over that, we use a classifier to understand what the classifier has learned. And then we hope to recover those rules from those from these explanations. So the data that we label, it is based on Minnesota handwriting assessment, which is widely used in the teaching domain to assess whether a handwriting is good or bad. So based on this assessment, there are like 5 major categories based on which they assess a handwriting. The first one is legibility. The second one is the form of the handwriting. The third one is the alignment of the letters. The fourth is the size, whether all the letters are of even or uniform size or not. And the final one is the spacing between the alphabets. So there are 2 main research questions that we have addressed in this work. The first one is, can an explainer be created to infer how a user should change their handwriting to make their handwriting better, including what aspects to retain and what aspects to change? The second research question that we have looked at here is, what are the key differences between a good and a bad handwriting? So this is the overview of our system, where we first have a handwriting image, then we have a classifier. Note, you can use any classifier here. But for our experiments, we have used a basic CNN architecture with 2 layers. Then we have a modified line section in which we have a segmenter which creates superpixels. And then we have a toggling system that helps to create the replacement images. And finally, we can get an explanation out of it. So there are multiple segmenters that you can use for the purpose of segmenting these images. We have looked at mainly 3 of them. First one is the quick shift, which uses approximation of kernelized mean shift. The second one is Pleasant swaps, which is based on graph-based representation. And the final one is Slick, which is based on k-means clustering. So just an example here. This is a alphabet 6 from the MNIST data set. And here we have shown like how the segmentation looks like for all 3 kinds of segmenter processes. In the first one, you can see for the quick shift one, you can't kind of make out what segments it has created, means like the structure of the 6 is totally lost. For the second one, you can see that it has created like way more number of segments than actually is required. And for the last one, that is Slick, you see that you can still make out some of the edges or the curve of 6, that is the green and some of the red parts. So for our experiments with the MNIST data set that we have like looked at the digit 6, we are using Slick for this purpose. So when you are using Lime as an explainer, what it technically does is it will take a superpixel, and within that, it will take the mean values of all the pixels that are present within a superpixel, and then use it as a replacement image, and then replace it to the corresponding pixels that were present in the superpixel. And this is how it generates a replacement image to see whether a certain part impacts the classification. Now, this concept works for natural images because they have colors, you have your RGB channels, and then you can get a mean out of it, which makes sense. Now, this does not work with black and white images because when you have a black and white image, the replacement image that you are getting out of it is like a uniform replacement image, which does not give you any information about the segments. So here, because we don't, the segments are not in color, we do not have any discriminative details within their boundaries. Therefore, it does not work. So what can we do next? What we can do is we can try and use a negative for it. So here in this case, the replacement image will now become a black ink and white background. So your 6 will be written in a black ink and your background will be white, which is opposite to the original image. Now this ensures that all the pixels will be toggled to the opposite to see the effect of the classifier on the classifier. This explainer can test for changes in the classification output when the black segments are turned white and when the white segments are turned black. But this is not very efficient because, as you can see, there is a lot of background that is present in this image, and those background need not be toggled. So what we do next is, rather than having a negative replacement image, we kind of use a Gaussian filter to blur out the inverted image and set all the pixels that are not affected by the blur to background color, that is black. Now all the pixels that are far away from the writing are black, as in the original image, and thus toggling them causes no effect. In a way, this is imposing domain knowledge and to guide the classifiers to generate explanations only in the vicinity of the ink. So for our experiments, we tried having 2 kinds of data sets. The first one is the MNIST data set, which is widely popular. From that, we chose 4,000 instances of number 6. Now you would be wondering why we chose the number 6. We kind of had a debate which digit to choose, but like we went with 6 because you can write 6 in a lot of wrong ways. That is, you can write it as a B, you can write it as in many other ways. So we just went ahead with this one. The second data set that we created is a handwritten word data set where we had 981 samples of the word studio. So here in this example, I have shown some of the bad instances of the digit 6. That is, the classifier misclassified the digit 6. So for the first one, you see that the first column that you are seeing that shows what are the instances because of which the classifier classifies it as bad. The second column that you are seeing, the green color, shows that what are the aspects that should be kept. And the red or the pinkish area that you are seeing are the aspects that contribute towards the classification of this as some other, like it was an alphabet L rather than 6. And the last column that you are seeing is the suggested changes that we are giving. So in this one, you can see that the first part, the 6 is not exactly connected to the line that you have, but in the suggested change, it shows that it should be connected back to the line that you have in the 6. Similarly, in the second example, you can see that it has been written in a weird way where the 6, where you should touch the line, has touched beforehand. And that should not be the case, and it should be in a circular way. Similarly, for the other cases as well. So now this work is in a very initial stage, and there are numerous possible directions that you can go about it. So the first one is like we worked in a very small data set, and you can look at considerably large data set which can be curated and labeled. I think it would give us more informative information or with that. Then we can also use feature engineering to better tune the classifier. So this whole work is actually impacted by the type of the classifier you're using, and the more accurate your classifier, the better results you would be getting out of it. The third one is we can investigate different ideas from other existing literature that are pertaining to beautification. So there are parallel works that work towards beautification of handwriting. So we can borrow some concepts from there as well. So now for application areas, this work can be used for helping teachers to maybe suggest how the students or how other people could improve their handwriting. Also, it can be used for, like I said, beautification tasks. So if somebody wants to, like this one, if you have a calligraphy, if you want to learn something and you're not doing it right, maybe you can improve your handwriting and you can write it better in the calligraphy style. So to summarize, we first label a certain set of data sets, then we trained a classifier, we learned an explainer over that, then we evaluated the instance explanations, and then finally we tried to investigate ways to understand or improve the system. That's it from my side. Thank you.
Questions? Go ahead.
Excellent presentation. I just had two questions. One question, so there are digits 0 to 9. There are digits. Okay, they're
yeah.
You have divided into one is good class writing with bad class writing,
yep.
And I use local interpretability methods like LIME, and there is one thing called you can use shapely additive explanations.
You can go
yeah.
Any of them,
These are surrogate based.
Yes.
Did you ever looked into post hoc methods which are score cam class activation maps?
No, this one was because it was a pilot study. We haven't looked at the post hoc explanation text, but that is a good suggestion though.
Okay, so we are pertaining in the future that you will be looking forward to it. Okay.
Yes.
And did you replicated this work in alphabets
Yeah, we did use
because there you get a better you have larger data set 26 alphabets or in different languages.
Yeah, we didn't use a single alphabet thing here. We just used it over a word that is studio. I don't know if it is here, but anyways, we worked on two of the words, that is studio and a word quickly, where we had this Y or G, where you have a word or alphabet that comes down as well and has an upper part. But we didn't work on single alphabets or something of that kind. But I would say that it was that one is more challenging as compared to digits.
Yeah, an addition, because if you let's say number 6 or like, okay, if you just data augment it or rotate it, like then it
Mhm.
becomes a number 9.
Yeah.
So your model would get confused in that aspect that, okay, the initial data has feed with 6, and when you're training it and we're augmenting it or rotating it,
Mhm.
it looks like a number 9. Then
Yeah.
how you'll handle those kind of scenarios? That's like in the interpretability side.
Like currently the set that we had, we didn't try it with the augmentation or any other techniques. We just fed in like the number 6 that we have had, and we had like a plenty number of bad examples.
Yeah, like
so we didn't give it a try, but I think if you have your augmented images in your training section, your classifier, if your classifier is sturdy enough, I don't think you should have any problems in the interpretability part, because the one that we have changed, it is only on the line side. So once your classifier is robust, you will not have problems on the explainer part.
Okay.
Go ahead.
It's an interesting problem, and I don't claim to have the best handwriting out there either. But I'm wondering if it would be a better approach, rather than looking at the different colors and segmenting that way. If most schools, at least in America, have templates of how they're trying to teach children to write what an optimal letter might look like.
Yeah.
If you were to instead to be looking at taking the letters as binary and trying to say what sort of morphing or warping would be needed, how much more morphing or warping would be needed to meet to the ideal. And from there, the more warping that's needed, the worse the quality, the less warping that's needed, therefore the better the quality, which seems like a much simpler approach.
Yeah, like I do agree with that. It's like you would see that the rules that we have used are quite, like the 5 rules that we have used, they are quite simple rules. But when you go into the real world, there are more complex rules that they use. They just don't use your form legibility and those things. Plus bias also comes into account. But I do agree that like having a fixed template and then like kind of comparing based on that would be an easier way. But I think that once you create templates, you're kind of fixing the, means how do I say, like sometimes our handwriting, there is no one good way to write. So the template there defeats the purpose. The thing is, like students might write in a different way from the template, but they would still be considered as good handwriting.
But you could have multiple templates, but again, most schools, at least in America, and have templates that they start children aiming toward.
Yeah, means.
And so if you're doing this particularly for young writers, then they should be trying to say how close they can get to that.
Yeah.
And by measuring the amount of warping or morphing to get their geometric distance.
Yeah, I do
would
agree
get you there better.
Yeah, thank you so much.
Other questions? I guess I was a little bit unsure of exactly how you made the suggestions for improvement.
Yeah.
Could you review that for us?
Yes, so that is a very good question. So the thing here is, here, if you see the red segments that you have, if you see in the first part, the red segments that you have, they are both in the portion where you should have a write-up and where you shouldn't have. So now currently what we have is, it just shows the segments which contribute to the classification where the 6 is bad. Now we don't know whether that segment should be, that you should put an ink there or you should just erase there. So currently what we are doing is, once we get these red segments, based on the Minnesota handwriting, we just make the changes based on what should be there, but it is not automated currently. So that is the manual part that we have.
Great. Let's go ahead and thank our speaker.
Thank you so much.
Okay. Our next talk will discuss text edges guided networks for historical document super resolution. And our speaker will be Borak Mahdi from Ben Gurion University of the Negev in Beersheba, Israel.
This one. This one. Okay.
Okay. Hi, everyone. My name is Burak Madi. Today, I will present Text Ages Guide Network for Historical Document Super Resolution. This work has been done jointly with Reem Al-Assam and Professor Jihad Saneh. Okay, our presentation will include introductions. We will also have data overview, and we'll explain our model loss. And finally, we will have an evaluation. First of all, what is super resolution? A super resolution is a process that aims to increase the resolution and enhance the visibility of low resolution images. A lot of works have been done in different domains, such as natural images in recent years, but historical documents, images has not been addressed well or have a lack of attention. One of the fields in super resolution that may have be relation with what we want to do is called the text domain. Text domain for super resolutions deals with modern fonts and relying on extracting prior information from a recognizer. Okay, for example, we see on the row, it's like starting with classic super resolution, followed by 2 deep learning methods, and the one that the row point to is using the transcription of the word inside the image to increase the super resolution. As we see that for each one of these images, it have a transcriptions that written in the columns, in the first row of the columns, and the correct of or the accuracy of each model is being decided based on the green letters that has been or that have been recognized by recognizer that they used in their paper compared to the transcription above. And as we could see that using semantic features give a boost and giving better results. Unfortunately, for handwritten or historical handwritten, recognizing don't giving much good accuracy. Thus, the text domain works is still unapplicable, such for Arabic documents or Hebrew documents. Then, in this presentation, we presenting the first work that deal with super resolution for historical document without relying on prior information. Our model is called the text attention super resolution. It's one of the GAN family. In order to build a fair comparison, we compare it with state-of-the-art models in super resolution, but in the general domain. The general domain, it's a domain that deals with natural images and do not rely on prior information to do the super resolution, such as SRGAN, and we obtain better results. For our data sets, we have a VMLHD. It's 5 Arabic manuscripts written in 1088 to 1451. It contains 668 pages, have 5 different fonts, simple layout, page layout, do not have much touching components. For each one of these data sets, we sample 20 pages, and we 20 pages, and we call it book 1 to book 5. We name them book 1 to book 5. Also, we use a very complex layout data set called AHTI. It have having touching words and also touching sentences, and have a very complex data set. It contains two different writing styles. The data preparation, we sampled the 50 patches from each one of these 50 patches from each one of the pages in the data set. Our patches with size of 256, we call the high resolution with abbreviation of HR, and also we resize them or reduce their size to 64 by 64 to get or to obtain a low resolution. We call them low resolution, LR. Our model is again models that contains two architectures, generators and discriminator. As we will explain, our generator, it's contain its input a low resolution and out HR star, which is the output of high resolution. It's contain convolution layers with a skip connection to include the low features and also semantic features. It's also include residual over residual Dennis blocks, which very famous that they're using in super resolution models. And finally, we have activation function with pixel shuffle to reduce the channel and increase the image dimension. In order to, as we see before, text domain models rely on semantic features such as transcriptions before doing the super resolution. Also, we know that ages include more information than other pixels inside the manuscripts. And finally, we aim also to build a customization models that work good on working well with historical documents. In order to do that, we're building a new text age loss that encourage the model to save the ages while it making the super resolution without corrupting the ages. It led the model to make a sharp ages while and preserve the ages without corrupting them. For experimental evaluation, we applying the data preparation. Till now, we have 6 data sets, 5 books from VML and 1 from AHTI. We train and evaluate these models on the data sets and compare it with ESDR, SRGAN, SRFET, SRGAN, and RCAN. It's like the famous models in the domain of super resolution, where each model input a low resolution input and output HR star 1. We compare them and using BCNR and SSIM results. For results, we have the best results over the 6 data sets for BCNR evaluation, and for SSIM evaluation, we have the most cases with a small margin in VML book 1 and AHTI set. Now we will show an example. The example is a little smaller. To do that, we compare each one of the examples with a grounded truth, okay, with like using animation. As for example, the nearest as none, it's like corrupting the ages. It's having very bad results. For also, we could see that it's all corrupting the ages and also the ages of the text. It's artifact also. For bilinear, it's also suffer from excessive blur. Okay, now we will start with the models. We like examining through the training of the models that the models suffer in the text or in the historical documents domain. It having like different problems. One of them that it do not preserve fine details as we can see, it's corrupting them, and also have a localization artifact textures above them. Just for more visualization, we have for like, if we could see the ages very well, also it's produced like artifacts with color dots with green and red around the edges of the results. It's a result of instability of the model. For SRGAN, it's corrupted. That we could see that the left 2 black lines is like fuse them together. For ERC or RCAN or other models, it have the same problem. It's giving a very hard noise, and also we have a very corrupted edges on the text and also on the lines. We could see this also. SRFET have a instability on the results, giving a texture, very heavy texture noise, and also giving like it's produced some artifact dots, red dots. For SRGAN also, we could see that it produced artifact noise blocks.
For ESRGAN, also for artifacts, textures, it's also produce artifact texture above the text, but it's like succeed to produce the textures in the background, but like fail to produce clean text. Our models, it's like giving a best results, and also it's having better results in the edges, and also preserve the fine details, like such like two black lines in the left side. For conclusions, we show that the incapability of text domain to super resolve historical documents, and for the general domain, we present a new approach for super resolution for historical domain. Our experimental evaluation shows that our models outperform others in terms of PCNR and SSI metrics. Thanks. Any question?
Questions?
Okay.
So we're going to try to get back on schedule a little bit. So if you don't mind, we'll go ahead and you can ask any questions after the session. Thank you.
Thank you.
Okay, our next talk will be on a benchmark handwritten character data set, acquisition, compilation, and recognition by Kanwaljit Kaur from Punjabi University.
Good morning to all. I am Kamaljeet Kaur, and today I will be presenting the paper entitled A Benchmark Gurmukhi Handwritten Character Dataset, Acquisition, Compilation, and Recognition. The work is the joint effort of Vidyut Varun Chaudhary and Dr. Gurpreet Singh Lahal. So we will be discussing about dataset collection related to Gurmukhi script, its creation and extraction, and then recognition of the units based on VGG16 model, and also experimental results and comparative analysis. So we have introduced a new large-scale benchmark dataset, which is named as Gurmukhi HWDB 1.0. The dataset consists of total of 1,37,700 samples, which are of 41 basic Gurmukhi characters and 10 numerals. And the recognition task is carried out using CNN architecture, which is based on a VGG16 model. And after experimentation, we are getting good recognition accuracies for Gurmukhi characters and numerals also. So while we are talking about tasks like handwritten recognition, the primary requirement, we should have a large number of data set which must be collected from good number of people. When we search literature, we can find some of the available benchmark data sets for languages like Chinese, Latin, Arabic, and Korean, and for Indic scripts also like Bangla, Devanagari, Gujarati, Telugu, Tamil. But as far as Gurmukhi script is concerned, there is a lack of extensive publicly available data set for this script. So we came across only 7 small data sets which are listed in this table. The problems with these data sets are they are of small size and they are not even complete. Some of them do not include the complete character set of Gurmukhi, and some of even do not include the numerals, and they are less diverse and collected from small number of people. So in the present work, we have tried to overcome all these shortcomings. For dataset collection, we have considered all the basic 41 Gurmukhi characters and numerals also. And we have tried to collect the dataset from large number of population, including students, professors, farmers, housewives, and retired persons, so that our dataset should have large handwriting style variations, and it should be more diverse and unconstrained. So talking about Gurmukhi script, it is the script which is primarily used to write the Punjabi language, which is the language of 160 million people all over the world, and it is spoken in Punjab region of India and Pakistan. And also you can see from the image that the primary Sikh holy scripture Shri Guru Granth Sahib is also written in Gurmukhi. The origin of the script is attributed to Guru Angad Dev Ji, the second Sikh Guru, who did the necessary modifications and rearrangements in earlier characters to shape them into a proper script. So the script has 35 original letters and 6 additional letters. We call them as Naveen Varg or Naveen Toli, which are created by placing a dot at the foot of the consonant. And the script also has its set of 10 numerals, 0 to 9 numerals. It has 10 diacritic signs and 3 peri-akhar, which are used to make consonant clusters, 2 characters bindi and tipi for nasalization, and 1 character adak to produce the gemination sound. Apart from the Western punctuation symbols, Gurmukhi has its own punctuation mark called Visarg, which is used to denote the abbreviation, Dandi to mark the end of a sentence, and Do Dandi to mark the end of a words. So in literature, we have found many of the work which is done using conventional techniques like SVM with RBF or KNN, etc. We came across very few recognition efforts which are done using deep learning methods. So we have tried to apply the deep learning model, which is based on VGG16, to the collected Gurmukhi dataset. So talking about data collection, the samples have been collected on A4 size paper. On A4 size paper, we have drawn a matrix of horizontal cells. In first column, we are printing the character, and then there are subsequent 11 cells in that column horizontally, in which writer is writing the character 11 times repeatedly. So the collection is distributed over 41 characters and 10 numerals Gurmukhi classes. And we have collected the samples from 265 persons of ages ranging from 15 to 60 years. Okay, these are some of the samples of numerals. Previous are the samples of Gurmukhi characters. And you can see from the table that we have tried to collect the sample from a variety of population, including students, research scholars, even employed or self-employed workers, and farmers and retired persons, so that our data set is diverse and unconstrained. And also we have collected the demographic information of the writer, such as name, age, gender, and occupation, which can further be used for the research activities like writer identification also. And addition to the character dataset, we are also generating a Gurmukhi paragraph level dataset. So these are the steps for dataset creation and extraction. So after collecting the samples, we have scanned the samples at 300 dpi. And then from this figure, you can see we have computed the horizontal projection profile of the text region. And based on the peaks and valleys present in the text region, we have segmented the lines. And then around boundary area around these lines is detected using half transformation. And we have removed the detected boundary area using 8-way connectivity. And then individual characters are again cropped using horizontal and vertical projection profile. So the table shows the dataset detail. So we have 41 character classes, and we have collected the samples from 265 persons. And in each character class, we have 2,700 samples. So total samples are 1,10,700. And similarly for the numeric, we have 10 numerals classes and 27,000 total 27,000 total samples for numerals. And out of this, 80% of data is used for training, and 10% is set aside for validation and testing. The lower figure, number 5, shows you some of the handwriting style variations in samples. So you can see how different people write different characters. So in figure 5A, you can see the character Uda, which is written differently by different writers. So in some of the sample, the horizontal headline is significantly oblique. In some, it is not present, and in this is extended. The figure 5B shows that shows the samples in which people are not joining all the parts of the characters properly. And these are the samples which are written by people of higher ages. So they are again introducing greater shape variations and distortions. And there exists, the figure 5D shows the group of samples which are similar in shape. So we are retaining all these samples for variations. So these are some more handwritten samples from the data set. So first 2 samples are for Gurmukhi character Uda and Nana, and last 2 are Gurmukhi numerals 6 and 9, which is called 6 and 9. So you can see the handwriting style variations present in the data set. So for recognition, we are using VGG16 based deep CNN model to recognize the units. We have performed several experiments, but in some of the experiments, we are not achieving the greater accuracies. So we have done some of the changes in the model. So we have fine-tuned its block 4 and 5, and first 3 blocks are kept non-trainable. And then we removed its fully connected layer and added our own adaptation layer, which consists of 2 dense layers of 512 and 256 units. And to generalize the model better and to avoid the dataset overfitting, we have used L1 and L2 regularizers. So we have experimented with different image sizes. Out of that, 64 by 64 by 3 is giving us good accuracy, and it is also taking less time to train. So the model is evaluated using the proposed data set. And we are also performing the augmentation to generalize the model better. So using the augmenter, we are taking 1,000 random samples from each character class, and then we are applying rotation, shearing, and random distortions, and generating 3,000 samples per class to increase the data set. So thus we are increasing the dataset size, training dataset size also, and we are also performing the, having the augmented images in training also. So from the tables, you can see we are getting results for different batch sizes. Out of this batch size 64 for character and numerals is giving us good accuracy. So for characters, we are getting 98.42% accuracy, and for numerals, we are getting 97.51% accuracy. This is the classification accuracy curve. So we have compared the results with some of the state-of-the-art methods. So you can see when we are comparing with conventional techniques, our method is surpassing the results present in the state-of-the-art literature. And also in comparison to deep learning methods present in literature, our model is giving us satisfactory results. We have also compared with the existing benchmark datasets. So in all these, our model is getting good results as compared to the literature. So concluding, we have created or presented a standard benchmark Gurmukhi dataset, and it will be made available for public academic research. And we have applied CNN architecture based on VGG 16, and we are getting good recognition accuracies. And we are still trying to improve the performance of the model by training it for more epochs and train test ratios. So on training the model for more epochs, we are already obtaining a hike in accuracy. And in future, as we are working on generating paragraph level dataset for Gurmukhi, so we will be working on words and sentence recognition also. So we like to acknowledge all the writers of the dataset who have spent their time and effort to fill the samples towards the development of this dataset. Thank you.
Questions? So as you looked at errors, was it more difficult to accurately transcribe the handwriting from older people or younger people?
Actually, it was very difficult to collect the database from older people because they did not want to spend time in handwriting also, and they find it difficult to do the handwriting. So it was very difficult. Overall, all the data set was collecting all the data set from different people is very difficult, but it was very difficult to collect it from older people.
Okay, let's thank our speaker.
Thank you so much.
Our next talk will be self-supervised vision transformers with data augmentation strategies using morphological operations for writer retrieval by Marco Pierre from Austria.
Okay, hello everyone. Thanks for being here, really nice. Today I want to present to you our paper called Self-Supervised Vision Transformers with Data Augmentation Strategies Using Morphological Operations for Writer Retrieval. My name is Marco Pierre. I'm from the Computer Vision Lab at TU Wien in Austria, Vienna. And this is joint work from my colleagues, Florian Kleber, Robert Solnatik, and myself. And today I want to talk about, I want to briefly introduce the task of writer retrieval. Then I want to motivate our approach, in particular the self-supervised learning or contrastive learning. Then I describe our proposed approach. And in the end, I show you the results. So pretty straightforward. So let's dive into it. First of all, what's writer retrieval? Usually we're given a database of documents written by a different amount of authors. You can see an example here on the slide. And we're given a query document. And the goal is to retrieve a ranked list, which contains the documents of the same author. This is a ranked list. So in that case here, the retrieval would be ideal. And we are targeting this result, of course. So the principal pipeline for writer retrieval usually consists of a sampling technique. So we do not process the document at the page level. We're extracting local informations. For example, we are extracting pages at SIFT key point locations, which is quite popular in related work. Or in our work, we just divide the document in pages of the same size. Then we have a neural network, which extracts the embeddings. And then we have an encoding strategy. So we have a lot of different embeddings for one page and we encode them. And in the end, we can perform a distance-based ranking. Okay, what's the motivation? First of all, we conduct our experiments on the ICTA-17 database, which is also called historical WI database. The test set consists of 3,600 documents, so this is quite large for our task. And I put here 3 different documents from the same author, and you can see that the appearance of these 3 pages is quite different in terms of the pen, for example, but also the general appearance of the handwriting. And we call this the intra-class variance. So we can observe a lot different characteristics of intra-class variance. Of course, this is a nice motivation. I just want to give you a broader view. So actually, we are working in Austria with the police, and our main problem was basically that we have a lot of different samples from prisoners, for example, and they use different kinds of pens and also other characteristics. For example, older people write completely different. And we were looking for different data augmentation strategies. How can we tackle those characteristics, and how can we eliminate the characteristics introduced by different pens, for example? And in this historical document database, this is also the case, as you can see in these images. Then I also want to move to self-supervised learning. I guess most are kind of familiar with self-supervised learning or contrastive learning. This is quite popular on ImageNet, for example. There are a lot of different approaches. So what's the goal of this? Typically, the contrastive learning approaches nowadays are learning from 2 different samples, positive pairs. And the idea is that you augment your image to generate those 2 different pair views by different augmentation pipelines. And those pipelines are targeted to eliminate the semantic information, which is not necessary for our task. So this is kind of ideal for the right retrieval part, because we can simply apply augmentation in these 2 examples here. This would be an example with the morphological operations. You can see that we can change the characteristic of the pen, and we can train our network in a self-supervised manner with this. And the goal is that those 2 images have an embedding as similar as possible. So now we are proposing using morphological operations for writing, kind of a traditional approach. I mean, you could also use a generative adversarial network, for example, to differ the style, but we want to keep it as simple as possible for the self-supervised pipeline. So we randomly apply erosion or dilation with randomly sampled kernels. You can see the result here. So for example, with erosion, we can increase the thickness of the pen, and with dilation, we can do the opposite, basically. You can see different effects of different kernels. And yeah, with this kind of technique and augmentation, we are able to generate different views of our handwriting. What is our setup? We use a ResNet 50 and a vision transformer. The main network is our vision transformer. We are kind of using the vanilla transformer. I guess most of you are familiar with it. We have those patches extracted. We use 16x16 patch size. Then we have a linear projection to get the embeddings, and then we perform the transformer part, the self-attention on those embeddings. In most of the self-supervised approaches, there is some kind of projector. We use an MLP. And for inference, we just drop the projector to get the embeddings for the retrieval part. So we use the output of the transformer encoder for our inference and retrieval part. For the loss, we just use a cross entropy similarity loss. You could also use, for example, a cosine similarity, for example, to calculate the similarity of the embeddings. Then I also already mentioned it. We do not perform our retrieval on a page level. We extract 200 times 224 times 224 patches from each page. So just dividing our page into different patches and forward them to our network. And for the aggregation, we just use a quite simple approach, sum pooling for the global descriptor. So this is the overview. This is the main principle of self-supervised learning. We have a student and a teacher. These are
what is the first one?
Okay, we have a student and a teacher.
Yes, sir.
Okay. Okay. So we have a student and a teacher. This is the same architecture, but this is different to, for example, metric learning, where the networks share the same weights. In our case, these are two different networks. And the principle is that the student is updated via backpropagation, so a normal training in our case, and the teacher is updated by the student parameters via exponential moving average. And yeah, we have T1 and T2, which define our randomly sampled transformation, in our case, the morphological operations, to generate the two views. And yeah, there's also the centering part, because most of the self-supervised learning parts have the problem that this is really prone to collapsing. So if you just have two positive pairs, then the loss can be minimized by just outputting, for example, 0, and the loss would be 0 as well. So this is the centering part to avoid collapsing. And we end up with two different embeddings, X1 and X2, which should be as similar as possible to achieve the goal of the training. How do we evaluate our approach? In our domain, we report mean average precision and top 1 accuracy. We also evaluate the data augmentation strategies. So we compare our proposed pipeline to other traditionally used data augmentations. Then we also evaluate the two different networks. And we also try out morphological operations as a traditionally used data augmentation in a supervised setting. So with the triplet loss, for example. So what are the basic results on the contrastive learning? We tried out a baseline approach, which just consists of rotation, translation, and blurring. Then we also try out the contrastive learning without any augmentation. So we just use a random crop. And then we use our morphological operations. And in our experiments, our approach outperforms the other two pipelines by a huge margin. So for example, compared to the baseline by just 30%, for example, in terms of the mean average position. Then the supervised training, we use a triplet loss, where we use the writer labels. So this is actually supervised. And we just augment every sample with the morphological operations and compare this to a traditionally trained triplet loss network. And you can see that the results are enhanced by 7.8%. So actually, by just introducing the morphological operations to the writer retrieval part, we can improve the performance for free, actually. So we conclude basically that we can use the morphological operations for a general data augmentation technique in our task. Then I also want to highlight our contributions compared to the related work. There are some approaches, for example, by Wang et al., which is kind of similar to us. They are also using extracting patches of our size and just some pooling. Then we have the winner of the competition where the dataset was introduced. And then we have the state-of-the-art approach by Christlein et al., who are using some pooling as well as the explicit encoding. This is called MFLAT, vector of locally aggregated descriptors, and the example support vector machine. And I just want to highlight that, for example, when we are both compared to Christlein et al., when we're both using the same encoding, our approach is, for example, over 20% better than theirs. And we're also easily outperforming Wang et al. And the winner of the competition. Yeah. Of course, we could improve our results by using some explicit encoding. And we might be in range of state-of-the-art, but this was not really the target of our work. Our target was basically to introduce some data augmentations for writer retrieval and to introduce an unsupervised approach for this, or self-supervised. So this now is the conclusion. I already mentioned it. This is the first self-supervised learning for writer retrieval. Then we also proposed the morphological operations as a general data augmentation strategy for handwriting in general, but in particular for writer retrieval. And for future work, of course, all these approaches I showed you, they could implement the morphological operations. but we could also investigate, for example, diffusion models, which is quite popular right now, to enhance the variation of the stars, for example. Or for example, there are some guns out there. I think our keynote talker also mentioned Scrabble gun. This is also capable of varying the style of the handwriting when you give them a sample of the author, for example. So we could investigate in this to further improve the availability of the training data. Okay, and with this, I want to conclude my talk. Thank you very much.
Questions? Go ahead.
So, like, I have two questions. Like, the first question I have, like, when you talk about supervised settings, you use triplet loss. And like in self-supervised, you're making a contrastive learning-based approach you mentioned. Did you explore supervised contrastive loss in this supervised settings?
You mean
supervised contrastive loss?
Yes. Do you mean with negative pairs as well?
Yeah.
I mean, you could use that, but actually in our domain, triplet loss is the state-of-the-art technique. So this is basically the same, just with
and if you remove the negative pairs, just for ablation, like if you remove the negative pairs and then you utilize the supervised contrastive loss, that would be a...
You could use this, yes, but triple loss performs usually better, for example, on CVL dataset, IM, so the modern dataset. I think for the historical database, the contrastive loss is not evaluated as of yet, but triple loss is kind of the benchmark in the right retrieval.
Okay. My next question is, when you're using a vision transformer, like when you say it, so you're using a ResNet backbone. So if I'm not wrong, the ResNet backbone is for just like a feature extractor at like as a window of writer or retrieval problem. So you have one set of windows, the another set. It's a sliding window approach comparatively. So you can use like a pyramidal transformer as well, pyramidal VITs and shifted like swing transformer based backbone, and then completely remove the ResNet backbone. Like I didn't got the like why you're using ResNet backbone if you have this advanced transformer architectures like pyramidal vision transformers and all that.
We are evaluating two different network architectures. So the vision transformer, and then we showed that the approach also works on the residual network.
Okay, so
these were just two different experiments with different network architectures.
So you want to give a comparison, like okay, with the traditional CNN based, how you're better?
Yes, so, okay. The vision transformer was actually there for our project work. So for example, we visualized the attention and showed where the important information for the vision transformer is basically located, and we could use that to hand over to the experts at the police, because they have to somehow deliver some proofs that the handwriting is similar from two different documents. So this was the main motivation for vision transformer, and the vision transformer actually outperformed the residual network as well on the historic data.
Okay, thank
you. You know, I think we're kind of getting behind. Maybe we can save the rest of the questions for after the session. Thank you.
Thank you.
Okay, we're now going to go to 3.6, 7, and 8, which are online. So I assume that the speakers will go ahead and share their screen on Zoom. The first one will be Compose V++, lightweight online signature verification framework through compound feature extraction and few-shot learning.
Hi all. Good morning to Professor Mark and Professor C.B. Johar. I'm Chandrasekhar, completed my PhD from ICFHR TCT. It's part of my PhD work. So first, my work is in online signature. So first, I want to distinguish what actually the online signature or offline signature. If you type it on a paper and by using scanner, if you convert into an image, it will be an offline signature. And if we use any specialized digital advanced devices where the user can sign on the device based upon various factors, it will capture the X profile, Y profile, various pressure, etc. of his user. Now, so what happens is these are the first when we sign on the device, it will sample the digital signature at various sample points, and each sample point is represented as by these coordinates: x coordinate, y coordinate, time, pen up, pen down, etc. So these are the sample points. The signature is sampled at 84 points, and these are the various points available. So if we try to use this information and try to classify the signature, we call it as a online local feature based online signature. Else, if we convert these features based upon these local features, 84 points, if we convert them into a, like if we use any statistical features to based upon these 84 features, if we use statistical features like maximum velocity, maximum acceleration, jerk, etc., so those we call it as a global feature based online signature. So now in any framework, so we have some set of features, signature is transferred into features, and here we can write, like we can work on feature processing, or we can work on model. So these two are the points where we can contribute for the efficient classification of the signatures. So we worked on these 2 points. So the main aim is I will explain through an algorithm. First, we proposed one dimensionality reduction algorithm where these global features, here we have global features, say 1 cross 100, each signature is represented as 1 cross 100 feature vector, but we want to work such a way that we want to extract the features to make it 1 cross 3. Okay, and then we feed into the deep learning based model. So first we proposed an algorithm where we work with eigenvalues returned by the principal component analysis of the feature vector. So there we are reducing the features from 100 to 7. In some cases, it is to 3. Then we feed those feature vector into the depth-wise separable convolution-based neural network. Sorry. Sorry. So what is algorithm? So algorithm contains a set of users, and each user contains a set of features. So feature 1, feature 2, feature D, etc. So feature 1 is a column vector. So here, one signature, we have 1 cross 100. Suppose if I have 25 features for a user, I have 25 columns representing the F1 vector. The aim is, even though I have 1 cross 100 feature vector, here I have 1 cross 100 for one signature. I have, for each user, maximum I have 25 signatures. So this particular column contains 25 values. This particular column contains 25 values. Now we want to compute which are the best features out of 100, which are the best features. So I will select only 3 to 7 features, means extraction, and then I will use it for the model. So here what we are using is, so out of these 100 columns, we want to select best column. So what is the algorithm is, simple. For each feature column, here we have a column. For each column, compute, we will perform PCA. So PCA of the particular feature vector. Okay. So we have D feature vector. For D feature vectors, if we feed F into the PCA, we will get total D values, eigenvalues. So eigenvalues indicate the importance of each feature vector. Now what we are doing is, now we want to analyze the impact. What is the impact we want to study is, if I drop, we have eigenvectors. PCA returns 2 values, eigenvalues and eigenvectors. So for these feature vectors, correspondingly, I have eigenvalues and eigenvectors. We want to analyze importance of each vector. Suppose if I drop, I want to reduce the dimensionality from D to P. That means total D is there. Suppose I want to reduce from D dimensionality to D minus 1. That means if I want to drop lambda D, what will be the impact? If I drop lambda D minus 1, what is the impact? So for each eigenvector, we are computing the importance. So what is this normalized reduction loss? So this is for that particular, suppose if I want to drop from lambda D to lambda P, so this is the formula we are using. So that particular importance by sum of all the importance. So this was the metric proposed by Professor C.A. Murthy of IISc Calcutta. So this metric we have used to decide the importance of each eigenvector. Now, once we get the importance, so if that importance of a feature vector P is less than or equal to 0, we are calling it as a weak feature set because its impact is 0 or even negative. If threshold is a tuning parameter where we can tune it. So if it is greater than 0 and less than or equal to t, we are calling it as a moderate feature vector. It means the impact, if I drop that feature vector or corresponding eigenvector, the impact is moderate. And if the score is greater than threshold, it is a strong feature set. Means those eigenvectors are strong. So we are adding corresponding features. Once we compute all the features, what we are doing is we are multiplying the values, the importance with the corresponding vectors, and we are taking the sum overall. So this results into a single value. This also results into a single value. So overall, what we are doing is we are computing the weak vector, the moderate vector, and the strong vectors. So in this way, we are getting a 1 cross, maybe maximum. We found that 7 values. Okay. So what we are doing is here, if you observe that, we given more importance to strong feature set. So strong feature set remain as it is. And for weak and moderate, we are computing the dot product between the weights and the vector. So this result into a single value, this result into a scalar value. So these scalars plus strong feature vector. So strong feature set may contain 4, 5, 6, and then these two 8. So this will be my new extracted feature vector. That feature vector we feed into the model. So instead of 1 cross 100, each user signature is 1 cross 100. Instead of feeding 1 cross 100, we extracted based upon the importance using PCA, eigenvectors and eigenvalues. If I drop each feature vector, what will be the impact? And impact is measured less than or equal to 0, 0 to threshold, above threshold. The above threshold is a strong feature vector, 0 to under t is a medium vector, less than 0 is a weak vector. So these 3 feature vectors we feed into the depth-wise separable convolution neural network, and it's a classification problem. So GNN or a 4-gen. So in this way, what we are doing is we are giving higher importance to more impact features, moderate importance to medium level, and just a strong or weak feature vectors are almost ignored. So now it became 1 cross 3 instead of 1 cross 100. So now if you see, in the study, in the literature, almost every work considered minimum 80 and 100 features, because the MCYT data set contains 100 features, where we did an attempt with minimum 3. Minimum 3 means if the strong feature vector contains 1 feature, and the medium and weak are two scalar values, and strong. So strong sometimes returns 1, and maximum it returns 5 values. So minimum 3 features, maximum 7 features, we are getting 22.94 as a error. Whereas if those who used 80 features, they are getting close to 13.42, and those who are using 100, they are getting 13.72. So with a drastic reduction of 97 features, so the error is like 9 points. So 9 percentage points it increased, but here we reduced by 97%. So it now, in case as number of samples increases, the error is getting reduced, means to the state of the art. Okay, like this. In case of another data set, SVC data set, we here maximum we used 3 features, whereas other works used 40, 47. Here we got very good less error and state of the art. So what the representation, if we use based upon the feature importance, so they have very good differentiating capacity, even closely matching signatures also. Okay, so we analyzed this work with 2 data sets. So we found that, and as the number of samples increases, S1 means one-shot learning. We are taking only 1 signature for training and remaining signatures for testing. So in case of one-shot learning also, because of these representation ability, so the error is 1.67. Whereas if even though the other works are using 40 features, the error is 5.83. So, and as number of training samples increases from 1 to 5, 5 to 10, 10 to 15, the learning capacity increases, and closely it is returning 0 error. So if you see, as number of samples increases, majority, almost all users, they are getting 0 error. Almost it's a 0. Why? Because here it is making it as a 0. So it's pointing to 0 here. And in case of random category also, majority of cases, as 4 indicates 4 number of users and green indicates 3.5 to 3. So it majority falls here, and very few cases, negligible 1 or 2 cases, 3 plus 3, 6 cases. So they are the ER is a bit higher. Okay, yeah. So this is what we have done. The main aim is utilize rather than using 100 feature vectors, analyze the importance of each feature vector. That means a column. So here it's a column. Here for one signature only we have shown like this. Suppose if I have 25 signatures, I will have 25 columns representing feature 1, feature 2, feature 3. Out of these 100 features, what we are doing, we are classifying them into either weak, moderate, or strong impact based upon their dropping. If I drop this feature, what will be the impact? For that dropping, Professor C.A. Murthy et al. From ISI Kolkata, they proposed one metric called as this one, NDL. Okay, so normalized dropping loss. So this dropping loss where we compute if I drop a particular feature vector, correspondingly importance, the eigenvalue by sum of all the eigenvalues will give me the impact. So based upon the impact, we are grouping the features each out of the 100 features into either weak, moderate, or strong. At the end, what we are doing, because strong feature set, we are not performing any dot product between the values and the impact. But for moderate and strong, we are performing the dot product and getting the scalar values. And we are framing the feature vector. That feature vector we are feeding into the model. And in few cases, we found that the drastic reduction leads to like a bit 9% higher error, but there is a 97% reduction in the number of features. In some data sets, standard data sets, it surpassed the state of the art. Yeah, thank you. Any suggestions, any questions?
Thank our speaker. Do we have time for maybe one question?
Please.
I'm just going to now confess that for the last 5 years, I've signed a different signature every time I sign a Visa card. So how sensitive, or what are the use cases for your signature verifier?
Use cases, one is addressing this to faster inference, because I'm dealing with only less number of features. The output, the result will be faster. So these models can be deployed into edge devices, because the processing, the time to process 100 features is drastically reduces when we use only 3 features. So the storage and the computation drastically reduces, but there is a slight increase in the error. So if we can compensate the error, so this particular model works better where we need faster inference and smaller storage.
Thank you. We appreciate your remarks. Let's give him one more round of applause.
Thank you, Professor Mark, and thank you, Professor Jawahar. Thank you. It's also in signature verification. So yeah, this is what I explained in the previous session. Now, I want to tell that here what happened when I'm in 3rd year. My lab mates, they published this paper. What is the paper? Is impact of fully connected layers on performance of convolution neural networks for image classification. So the summary of the paper is we are using some set of convolution and max pooling layer. Finally, there will be flattened layer followed by dense part for classification. So here the study, what they did is they studied about what will be the impact if I use only 1 dense layer or 2 dense layer or up to some set of dense layers if I use in the classification result. So this is what the experiments they have done. On going through this paper, I found some observations. First thing is, so they studied only a dense part. So why not the convolution part? So this is my first observation. And second one is they used a term called impact. So why we in general, in which scenarios we use impact if I have alternatives? If I have an alternative, then I will use the word impact. So here I can use the impact of dense layers. I can use 1 dense layer or 2 or some n layers. So if there is an alternative, then we do some impact study. So from these 2 observations, one is why dense, why not impact of convolution layers, and impact means when we have alternatives. So in this scenario, first one is we want to study how many convolution layers. That is first one. Next, from this impact, the convolution operation, I can do 2 types of convolution. One is vanilla convolution. Second one is depth-wise separable convolution, and third one is dilated convolution. So these are the options available. Okay, next, when it comes to signature, now I will enter into my work. So this is an online signature, as I have explained in the previous talk. So at each sample point, the device captures x coordinate, y coordinate, pressure, altitude, azimuthal angle, etc. So for each sample point, these are the coordinates. So I can represent this in this direction, or if I transpose it, it will be in this direction. Okay, so it will be like this. Now what we did, now I can perform convolution operation, but convolution operation I can do two types. See, if I use representation 1 like this, see, if I x coordinate, y coordinate, etc. So I can do 1D convolution. 1D convolution means it spans over only one this one sample point. If I use 2D, it will spans over multiple sample points. In fact, information from multiple sample points. Okay, so if I use a 1D, it will capture only one profile, and if I use 2D, it will capture green is 2D, so complete information. So first alternative is either I can use one first representation and then perform 1D convolution or 2D convolution. Second one is just to do representation, change the representation. Now if I do 1D convolution, I can follow complete trace of profiles. Okay, here if I do 1D convolution, I will analyze the correlation between x coordinate, y coordinate, pressure, etc. Here if I do 1D convolution, I can analyze the impact of the x coordinates. Then if I do 2D, alternatively, the information which I extract is different. So this is how we do. So which one is better? 1D is better or 2D is better, or following this representation? If I follow representation 1, what is representation 1? This one. On this, I'm doing 1D convolution, 2D convolution. So if I do this, now the error is lesser in case of out of this convolution operation. Again, I have two alternatives: separable convolution, dilated convolution. So if I use dilated convolution, and in this representation, in case of one-shot learning, my error got drastically reduced. And if I use separable 2D, separable and dilated in this representation like this, which spans over multiple profiles, the error is higher. Okay, this is the observation we made. Second one is representation 2. What is representation 2? Transpose of this. So in this representation, again, perform 1D convolution. For 1D convolution, again, depth-wise and dilated. Similarly for 2D. So here, if you see that these are the various error rates. Okay, so in both the cases, we feel that this is a representation which is better and 1D convolution is better. Now, one more alternative. See, we have a signature which spans over multiple sample points depending upon the length of the presentation. So, is it required to analyze complete length, or if we found out the optimal length, which is enough to extract the best characteristics of a signature? So we did a study. So here for user 1, the maximum length is here, but the average, on an average, if we consider 25 samples of that particular user, his average is varying here, and out of which the blue one says that this is the optimal length which I can use to classify the signature as a genuine array forgery. So instead of processing huge means more sample points per signature, we can sample less than, with less number of by considering less number of sample points, even less than the average, we can able to attain best classification accuracy. So here we saved the time. So based upon these three techniques, so what are those? One is alternative, considering the optimal signature length for each user. Rather than using the complete set of details, we can use optimal length. Second one, we can use which representation of representing signature, then which convolution is better. So these are the various alternatives we consider, and we perform a thorough study, and these are the various if we compared with a vision transformer with attention. So representation 1 and with 1D convolution, in that if we use dilated one, it is resulting in higher classification accurate, means the error is less compared to even vision transformer also. And at that point of time, these are the state of the art. So if we consider optimal representation, optimal convolution, so with here, there is no scientific formula or algorithm, just which is better among the alternatives, which will give me the best option. So see, drastically it got reduced to 4 points. The error is reduced from 13.26 to 9.72, state of the art. Similarly, for another data set also. So we got state of the art, and it is better than transformer with attention. So out of the available alternatives, if we can find out the best combination to perform for classification activity, so we can achieve good classification model. So that's what we tried. Yeah, thank you.
Great, let's thank our speakers.
So any questions?
Thank you for your presentation. Is there a question? Go ahead.
Sir, why didn't you utilize had an ablation on deformable convolutions and the corresponding deformable attention? Like, I understand why you're using depth-wise, but deformable convolutions also have a similar kind of offset introduce a 2D offset to the sampling grid and use in the signature verification problem. What was the reason of not utilizing them?
Honestly, the reason is at that point of time, this is paperwork 2020 we did. So at that point of time, the convolution which you're telling is not available. So we go ahead with the depth and dilated and depth separable convolution.
Did you try deformable convolutions
So
further?
after that, I completed my PhD and left the job, so I didn't try it.
Okay. Okay. So I think deformable convolution is something which you can try with corresponding deformable attention, because attention and convolutions are both analogous operations in a transformer domain. So yeah, I think that will give a better insight that why when you're posing this thing like a vision transformer performer less compared to this. So you're basically talking about the convex architecture, the convolution next architecture which came, which uses a depth-wise convolution. So I think you should try with deformable convolution and see that whether the transformers are performing better or not, and with the deformable attention at that end of the transformer.
Hello everyone. I'm Mimi Yu, a master student.
Yourself, or are you conserving bandwidth?
Can you hear me?
We can hear you. Do you have a video of your camera of you as a speaker, or are you just trying to conserve bandwidth?
Sorry, I'm hurt my back, so I need to head to in the bed to do this presentation.
That's okay. So you may begin.
Yes. Hello everyone. I'm Mimi Yu, a master student. Today I'm going to talk about our work, which is about the prototype-based model for handwritten text recognition. My report has 4 parts. First is the background. Handwritten text recognition is an important research topic due to its wide applications. Our method is based on convolutional prototype network. It's a hybrid model. It combines the advantage of discriminative and generative models. CPN shows better robustness and generalization in closed set recognition, open set recognition, and field short learning. However, it is difficult to apply CPN to text line recognition because the text line is composed of different characters and unknown character positions. By giving each frame the pseudo label, Gore first proposed a prototype-based handwritten text recognition method. Our method is inspired by Gore's work. Although it achieves good performance, but it still suffers from unstable training and the high computation cost due to sliding window on the input image. To address those issues, we use sliding windows on the fiche map to reduce the computation cost. Moreover, we use the reliable pseudo labels by 3 methods, namely dynamic weighting, pseudo label filtering, and consistency learning to improve the stability of training and performance. And in experiment, we find when visual-based classifier is sensitive to the model initialization, and the gradient is easily to be 0. So compare with Go. We use the DCE-based prototype classifier, which has better convergence. Then is the method. As the figure shows, we use CTC-based convolutional prototype learning framework, which contains 2 parts, CNN encoder and a prototype-based character classifier. In prediction, the text image is encoded by CNN, generating the feature sequence. Each character feature vector in the feature sequence corresponds to a local region in the input image through the receiving field, forming a series of equally spaced sliding windows. After that, the features are classified by the prototype classifier. In our work, we set key prototypes for characters and 1 prototype for the blank. We use Euclidean distance to measure the similarity between feature and the prototype. So the confidence distribution Y can be expressed by this formula. The model is trained with 3 losses: weakly supervised discrimination loss, namely CTC loss, which equal to the pseudo-label-based frame-wise cross-entropy loss, weakly supervised generation loss, prototype loss, which is the pseudo-label-based generation loss, and consistency regularization. According to this paper, by assuming the gradients of CTC loss and cross-entropy loss are equal, the pseudo-labels can be derived from the original CTC update formula. The pseudo-label is determined by the ground truth label L, and the models and the current model outputs Y. We use the CTC loss as our discrimination loss, which can be directly learned from sequence labels. Avoiding label in the character position, CTC training can be viewed as a iterative frame-wise fitting process. We use prototype loss as our generation loss. It can format a compact feature distribution in the feature space. Dynamic weighting, pseudo-label filtering are adapted to reduce the influence of unreliable pseudo-labels. Due to the inaccurate confidence of the model outputs in the early stage, a large number of unreliable pseudo-labels are generated. However, as the number of training epochs increase, the pseudo-labels are reliable. So we dynamically set the loss weight, increasing with the number of training epochs. And we use the decoding result to measure the reliability of the pseudo-labels. If the decoding result of pseudo-labels is the same as the real label, the pseudo-labels is considered to be reliable. Then only the reliable character pseudo labels are used to compute PL loss. Then we introduce consistency regularization to obtain more reliable confidence distributions and pseudo labels. Following a dropout, the input image X is fit to go through the forward path of the model twice. Since the dropout operator randomly drop units in the model, so the confidence distributions Y1 and Y2 are different for the same input. To regularize the model predictions by minimizing the bidirectional divergence between these two out distributions for the same sample. And then the discrimination loss is correspondingly defined as the average of the two forward paths. So the total loss is the sum of the three losses. Then is the experiment. For handwritten digital recognition, we use the CAR dataset. For handwritten Chinese recognition, we use synthetic and real text image for model training and evaluate our model on ICTA 2013. We can see for handwritten Chinese text recognition, our methods can achieve comparable performance with the best result. And compared with the method proposed by Go, our method outperforms it by 3 points without language model. We also compared the parameter size of different methods. It can be seen our method is a good trade-off between the accuracy and the parameter size. For handwritten digital text recognition, our method achieves a high accuracy and reduce the error rate by 12% compared with the previous best result. In ablation experiments, the prototype classifier and the prototype loss and consistency learning can improve the text recognition accuracy, which demonstrates the effectiveness of our method. To demonstrate the generalization of our method, we construct a transfer learning experiment. We pre-train our model on the single characters for 10 epochs and fine-tune on real text line image with various percentage. With only 1% real text line image for fine-tuning, our method can outperform naive linear classifier by 7 points in the same setting. And the experimental results so our method better applies the knowledge learned from character data to the text lines. That our method has better generalization performance in transfer learning with fewer text lines. However, when more text lines are used to fine-tune the model, the performance gap between the three models becomes similar. This shows that with the increase in the number of text lines, the advantage of pre-training on single characters become not important. we visualize some recognition result. Our method is robust to different writing styles and punctuation marks. We visualize the character location inspired by NMS. We can get the best candidate character center position by selecting the one with the highest confidence among adjacent character frames, and the width of the character is determined by the prior knowledge. For example, for digital in CR dataset, we use the half of image height as the character width, and we use the height of text line as the character height. Then in this paper, we design a prototype-based text recognition method with feature level sliding windows for classification. Moreover, to improve the stability of training and performance, we use DCE-based classifier and proposed 3 methods to get more reliable pseudo-labels, namely dynamic weighting, pseudo-label filtering, and consistency learning. And the experimental result can demonstrate the effectiveness of our methods and justifies the advantage in transfer learning from character recognition to text line recognition with small size datasets. In the future, we will try to use the multi-prototypes, and we will also try more tasks such as confidence, calibrations, and incremental learning for the text line image. That's all. Thank you.
Thank you very much. Okay, are there any questions either online or in person? Nothing online. Anybody in person? Okay. Well, we want to thank you very much for your presentation and hope that next time you'll be able to join us in person. Thank you very much for joining by Zoom. I hope you'll stay to listen to the rest of the session. Okay, our next.
Thank you.
Paper number 2 will be presented by Xiaoyi Zhang. It's the Chaco Character Contrastive Learning for Handwritten Text Recognition.
Yes, shall I share the screen?
Yes, please share your screen.
Okay. Can you see my screen?
Yes, thank you very much. Okay.
Okay.
You have 12 minutes to present and then 3 minutes for questions and answer. You may.
Okay, thank you.
Start.
Okay. Hello, everyone. I'm Xiaoyi Zhang from the South China University of Technology, Guangzhou, China. I'm honored to present our paper titled Chaco, Character Contrastive Learning for Handwriting Text Recognition. I will introduce our paper from 5 aspects. They are the introduction, related work, method, experiments, and conclusion. For the introduction, text recognition is a vital task of computer vision. Most existing methods are based on a fully supervised manner, which means that there is a corresponding label for each input image. But the manual annotation requires time and cost. Moreover, the incorrect label will interfere with the model training process. Therefore, reducing manual annotation in text recognition has emerged as an important research topic. Self-supervised learning provides a method for this problem. Previous methods are implemented from the perspective of words, taking the entire word image as model input. In this paper, we adopt another perspective in self-supervised learning, which is the perspective of characters, taking the character unit as model input. About the related work, for the concept-based self-supervised framework, many studies have contributed to different aspects of the contractive learning frameworks, such as the design of positive and negative sample pairs and network structures like MoCo, SimClear, and SimSam. These contractive learning methods are applied to the single object image classification task. However, words consist of multiple characters, and the above methods are not suitable for multi-object images. Thus, we decompose word images into single character images for contractive learning. With the development of generative and contractive self-supervised learning, self-supervised text learning methods have emerged. In the generative self-supervised method, SimN divided a text image into two adjacent patches. In the contractive self-supervised method, there are SetClear and Percent. This contractive method took the entire word image as model input. In this paper, we refer to the contractive method and adopt the perspective of characters, taking the characters and strokes in the word image as model input. About our method, we first propose character unit cropping. In the word recognition task, the model first recognizes the characters in the image individually and then determines the words formed by these characters. Thus, a more essential task in word recognition is character recognition. The character unit is divided as an image containing some characters and strokes. To get the character unit, we need to crop the word image. However, the random cropping may result in the positive pairs having completely different characters. In this case, it's unreasonable to minimize the distance between them in contractive learning. Therefore, building on the random cropping approach, a character unit cropping module is proposed to generate positive pairs which can contain the same characters. The algorithm for the character unit cropping is presented on the right. The input is the grayscale image, wide scale, high scale, center radial, and output size. We first get the width and height of the initial character unit, and then we get the upper left coordinate of sample C. And then with the center radial R, we get the upper left coordinate of the positive sample. Finally, we resize the positive pairs to output size. By the way, characters are generally combined horizontally into words. So to get the characters, wide scale is relatively small and high scale is relatively large. On the left image, for sample C, the selection region of the positive sample is shown as the red box. The positive pairs contain the orange region, which also means containing the same character. It's worth noting that when the center radial R is larger, the orange region is bigger and the selection region of the positive sample is smaller, which means the red box will be smaller. And data augmentation is used to increase the diversity of training samples. The data augmentation method used in this paper includes distortion, brightness adjustment, blurring, and noise. The figure on the right shows examples of data augmentation used for character units and their positive samples. The overall framework is shown. There are three major parts: character unit cropping, data augmentation denoted by AUG, and feature extraction. For feature extraction, we follow MoCo V2. The word image gets the positive pairs, which are the character units, after passing through the character unit cropping module. After data augmentation, one pass through the encoder and the projection head, and the other pass through the momentum encoder and the momentum projection head. The contractive loss is then calculated for positive and negative samples. Then the proposed method tracker is validated on the downstream text recognition task. As shown in Figure 5, the text recognizer consists of an encoder and a decoder. There are two types of text recognizer, CTC-based and attention-based recognizer. Then about the experiment, we conduct our experiments on public handwriting benchmarks, which are IAM, RIMS, and CVL. We use word level accuracy as the evaluation metric for all experiments. We train on one GPU. In the self-supervised stage, there are the hyperparameter settings. We use the character units as model input. Port size is 32 times 32. For downstream text recognition tasks, we use the entire word image. Port size is 32 times 100. And we use the same data augmentation as set clear, including light cropping, linear contrast, and Gaussian probe. For representation quality, the encoder parameters are frozen and only the decoder is trained. Figure 6 shows the visualization of the feature extraction of the encoder in the self-supervised training stage. As shown in Figure 6a, as the number of training epochs increase, the encoder gradually learns the features of the characters in the character unit. For the entire word image, the encoder can still identify the features of each character in the word. Figure 6b provides more examples of feature extraction, which confirms that charcoal effectively learns good feature representations in self-supervised training. For the baseline, the parameters of encoder and decoder are initialized randomly. And for other methods, the encoder is initialized with the encoder parameters obtained from self-supervised training, and the decoder is initialized randomly. From Table 2, it's observed that our method is much better than the baseline and other self-supervised methods. Charcoal is at least 0.6 points higher than Moco V2 star, indicating that the CUCM performs better than random cropping. The proposed method learns outstanding character representations and distinguishes characters in the character unit from adjacent characters. For SIM supervised evaluation, both the encoder and the decoder are trained. Table 3 shows the SIM supervised results. It can be observed that our method almost achieved the best or second best results on all 3 datasets. Our method outperforms Moco V2 star on most datasets, indicating that the effectiveness of CUCM. CUCM means the character unit cropping module. Compared with the current self-supervised test methods, our method performs better on the IAM dataset. Based on these experiments, it can be seen that constructive learning from the character unit perspective is effective. In this paper, in this part, we conclude our paper. A character constructive learning method called charcoal is proposed, which greatly reduces the demand for memory. A character unit cropping module is proposed to obtain the positive pairs so they can contain the same character. Experiment on 3 widely used handwriting dataset indicates that our method achieves better representation quality and promising results. And this is the end of my presentation. Thank you very much. Does anyone have questions?
Excuse me, I have a question.
Okay. You have a question online.
Yes, how did you come out with the idea of self-supervised learning from the perspectives of characters?
As we know, words consist of multiple characters. So in word recognition, a more essential task is to recognize the features of characters. Therefore, we try to learn only the features of character units directly in the self-supervised stage. And the experiments also proves that the model can also perceive the features of words through character learning. Also, our method greatly reduced the demand for memory during the self-supervised stage.
Okay, thank you very much.
Okay,
are there further questions in person or online? Xiaoyi, did you notice anything different about the performance on short words versus long words? Not necessarily just because of the number of letters, but because long words also are compressed in width?
The long words, I think the long words is also, our work is also good for it.
But you did not do any analysis comparing the length of the word to the performance?
Okay, I will, yes, we will change, we will get this box in the future experiments.
Okay, just curious. Any other questions? Okay, let's thank our author one more time. I hope that you'll stay and listen to the remainder of the presentations. Our third paper is presented by Ji Kwang, a vision transformer-based scene text recognizer with multi-grained encoding and decoding. So I told you this is one of the papers for the session that's not playing handwriting. Ji Kwang, are you there?
Yes, I'm
Xiao Yi,
here, but
stop sharing.
hey, first please, Xiaoyi cancel her screen sharing so I
Yeah.
can share my
Xiao Yi,
screen.
please cancel your screen share. There we go.
Okay. So can you see my, yes?
We can
Okay.
see your screen and you may begin. You have 12 minutes to present and 3 minutes for Q&A.
Okay. Hello everyone, I'm Zhiqiao from Tomorrow Advancing Life, and in this presentation, I will introduce our work, a vision transformer-based syntax recognizer with multi-grain encoding and decoding. This work is jointly completed by Zhiqiao, it's me, and Zhilongji, Ye Yuan, and Jinfeng Bai. This presentation contains several major parts. First is the motivation. Text recognition is a task to transcribe the text in an image to computer editable text format. And existing text recognition methods usually adopt an encoder-decoder framework, where the encoder is to extract abundant visual and context features, and the decoder predicts the target text from the features provided by the encoder. Specifically for the encoder, CNN and RNN are two common components. For the decoder, the CTC and attention mechanism are two common decoding techniques. However, the CNN-based encoder may suffer from some drawbacks. First is the inductive bias of the CNN may harm the performance of the model with the increasing amount of training data. Second, due to the locality, the CNN suffer from the limited receptive field. And nowadays, vision transformer, also known as the VIT, has attracted more and more attention. And we explained that the VIT also adapts to the text recognition for three major reasons. First, text recognition needs long-range dependencies and context information. Second, the need for large-scale training data for vision transformer is not a major problem for text recognition, since the text images can be obtained by the synthetic techniques. And third is that text recognition is a cross-modal test between the visual images and the linguistic text, and the transformer can be a union framework to bridge the gap between these two models. So one of the motivation of our paper is to bring the VIT into the text recognition with some target designs. And for the decoder, traditional CTC-based and attention-based decoding are somewhat different. CTC-based decoding depends on a fine-grained dense predictions from a local view, but attention-based decoding depends on a dynamic attention weights from a global view. So the second motivation is to integrate these two decoding techniques into a single decoder and let them benefit from each other. And there are some works introducing the VIT into text recognition and achieve the impressive performance. However, there are still some limitations, as shown in the left figure. They use single-size patches for the VIT-based encoder and single decoding techniques for the decoder. As mentioned before, in this work, we improved the VIT-based text recognizer with multi-grain encoding and decoding. And specifically, as shown in the right figure, we propose a two-stage encoder with different patch sizes, where the first stage extracts the fine-grained visual features, and the second stage aims at the cross-grained context informations. For decoder, we propose a joint decoder which integrates two decoding techniques and lets them interact with each other. Furthermore, we adopt a MAE-based self-supervised pro-training to improve the learning of fine-grained visual features. And this slide illustrates the pipeline of our proposed method, which adopts a fully transformer-based architecture. It contains two parts. two-stage encoder and the joint decoder. For the two-stage encoder, we follow the most settings of the traditional VIT architecture. In the first stage, the patch size is set to 4x4, and the number of the transformer blocks is 6. After the first stage, we adopt an additional patch embedding layer, where the patch size is changed to a vertical rectangles. This patch embedding layer converts the two-dimensional feature maps into one-dimensional feature sequence. And the feature sequence will be input to the second stage encoder later. And the second stage encoder is the same as the first stage with 6 transformer blocks, except the input. And before the introduction of the joint decoder, let's review the CTC-based and attention-based decoding quickly. The CTC-based decoding makes predictions on each feature frames, and a split and merge post-processing is used to transcribe the final results. And the attention-based decoding predicts an attention weight for each character to align the corresponding features. And the traditional attention-based decoding predicts in an autoregressive manner. However, in our joint decoder, we adopt the non-autoregressive decoding, and the reading order works as a query in the attention operation. And the motivation of the joint decoder is to integrate two decoding techniques into a single decoder. The inputs of the joint decoder are the visual features from the encoder and the reading order for the attention-based decoding process. And additional segment embedding is introduced to help the model distinguish the two inputs. And different from the training together, the features belonging to each decoding process can interact with each other and benefit from each other. The outputs of the joint decoder are still two parts, belonging to the CTC and attention decoding, respectively. And when inference, we just choose the attention-based outputs as our final prediction. And the third contribution of our work is a self-supervised pre-training method called focusing MAE. And MAE is a self-supervised pre-training method to train the model with masked image modeling, and inspired by the pixel reconstruction text used in the MAE. We want to let the model focus on learning the details of pixels belonging to the characters, which is more valuable for the text recognition task. So our proposed focusing MAE aims to mask and reconstruct the pixels belonging to the areas of the characters, but under an unsupervised manner, we cannot obtain the localization of each characters. And here we use a traditional image processing technique called maximally stable extremal regions, also known as MSER, to deal with this problem. Next, I will introduce the details of our focusing MAE. As shown in the figure, the upper branch is same as the traditional MAE. We let the first stage encoder embed the visible patches and append a shallow decoder performs pixel reconstruction. And the bottom branch provides a character-aware 0-1 mask for the final objective function. Specifically, there are 4 steps in the bottom branch. First, we extract the MSER from the input image. Then a dilation operation is used to expand the area of MSER to reduce the noises generated from the MSER. Next, we convert the deleted MSER map to the patches mask. And finally, the patches mask are multiplied to the reconstruction loss. And this slide will show the implementation details of our work. First is the objective function. There are 2 training stages, self-supervised pre-training and fine-tuning. The pre-training uses the MSE loss for image reconstruction, and the mask in the formula is the patches mask generated from the MSER in the previous slide. And during fine-tuning, a combination loss of cause entropy and CTC loss is adopted for the joint decoder. And we use two sensitive data sets for pre-training and fine-tune and evaluate our method on 6 public benchmarks. The size of input image is 32 times 128. The first stage encoder contains 6 layers transformer units with 4 times 4 patch size. And the second stage encoder also includes 6 transformer units with 32 times 4 patch size. The joint decoder is also based on transformer with 4 layers. Okay, let's go to the experiment. We first verify the effectiveness of the 2-stage encoder as shown in the table. Compared with single patch size encoder, our 2-stage encoder achieves the balance between the accuracies and the flows. And in the bottom table, we analyze the proposed joint decoder, where the joint decoder works better than the single technique decoder of CTC or attention mechanism, which verifies that 2 decoding techniques can benefit from each other in the joint decoder. Next, we verify the effectiveness of the MAE-based self-supervised pre-training. The MAE-based pre-training helps model with recognition, and our proposed focusing MAE further improves the performance. And we also visualize the image reconstruction results, which shows that the model can also reconstruct the text images well. And our proposed focusing MAE generates better reconstruction results with more sharpened and clear characters in the right dash line. And finally, we compare our method with other SOTA works. As shown in the table, our proposed method achieves the best or comparable accuracies on the several benchmarks with less parameters and a fast inference speed. And finally, we will conclude our work. In this paper, we propose a fully transformer-based text recognizer with 2-stage encoder and a joint decoder. We also propose a focusing MAE, a self-supervised pre-training to help the model with better learning of fine-grained character features. And in the future, we will further explore the transformer architectures and unsupervised pre-training, adapting to the text recognition. And that's all my presentation. Thanks.
Thank you very much. Are there questions online or from the audience? We have one here in person. Just a moment, get the microphone.
Hello, Z, hi. So can you go to a slide where you're giving a comparison of CNN with transformers? The initial first 2 slides, if I'm not wrong, the first 2 slides. The first slide, not this side, the first slide we're comparing where you have written that CNNs lack inductive biases, if I'm not wrong.
I think you want one of your earliest slides.
The earliest slide where you have mentioned that convolution neural networks lack inductive biases.
Like slide 2 or 3?
Yeah.
In your slide deck?
3? Yeah. Okay.
Yeah. Next slide. Yeah. Next slide, please.
This?
Yeah, this slide. So you have said that the inductive biases of the CNNs harm the performance with the increasing amount of training data. I want to know that like CNNs also have a translation equivariance property and VITs lack inductive biases. And VITs also lack the property of modeling the local structure. So did you think of trying something where the CNN can become a feature extractor backbone, and then you can try the VIT from a self-supervised standpoint, a kind of an hybrid architecture?
Sorry, I'm not very clear of your question, but you mean
my question is like, did you tried a hybrid kind of an architecture? Because when you say the inductive biasing is harming the performance, compared to, and your standpoint here is that VITs lack inductive biases, right? And that's why
you mean the CN plus the transformer units like work as the feature extractor. CN plus VIT, yes. You mean hybrid?
Yeah. Rather like because we say that vision transformer lacks inductive bias and they cannot model the local structure very well. So
yes.
I could not find that motivation just because the transformers are on the horizon. So for the same problem statement, you're getting it.
Actually, there has already been some works use this architecture, but recently the poor VIT architectures has a mainstream, and because it can achieve the better performance. Yes.
Further questions in person or online? Question up here in the front.
Yeah, hi Z. Question from the same slide. Like the second reason is like CNNs have limited receptive field. So any thoughts on using dilated convolutions for that?
Any talks or paper, you mean?
Dilated convolutions, like to increase the receptive field, like any experiment or something?
Sorry, I was not very clear of your question.
He's looking to see whether you've also considered using dilated convolution.
Yeah.
Dilated convolution. Oh, oh yes. I have not used the dilated convolution in our experiments. Sorry.
Okay, thank you.
This is one of the solutions to deal with the locality of the CNN, of course. Yeah.
There's definitely a lot of possibilities. Hard to keep everything. Are there any online questions? Okay. It's good that you tried it on so many different data sets to compare. All the examples that you showed had a uniform background. Do you have any that have, if you're talking scene text, I think of out on the street with street signs. Do you have any that have complex backgrounds, and does it perform okay on them?
You mean the MSER-based self-supervising here?
In all of the different examples of the images that you're trying to do the detection on, all of them here show very solid. You have a solid blue background here. Earlier you had a solid background, solid gray background. Do you have any that have complicated backgrounds, and does it perform also well on them?
Yes, this is a situation, but based on our experiment, the traditional MAE can still improve the performance. So if there is a complex in background and the MSER seems, we can compute a area ratio of the MSER areas with the whole image area. If it's a MSER area is too small, we will just degrade it to the traditional MAE and do not use the mask here. So there's a strategy to deal with this situation.
Okay, well, thank you very much. Let's thank our speaker again. We'll move on to paper 4.4. This is Yi characters online handwriting recognition models based on recurrent neural networks, RNN-net, Yi in parallel RNN-net. And our speaker is Yi Zhizhenyin.
Yes. Can you see my screen?
Yes, we can, and I can hear your voice. That's marvelous. Thank you for being with us. You have 12 minutes to present and 3 minutes for Q&A. Thank you.
Okay, thanks. Hi, good afternoon. My name is Zhixin Yin, and I come from Southwest University in China. It's my great honor to participate in this conference. The topic I want to present today is e-characters online handwriting recognition models based on recurrent neural network, RNNet and parallel RNNet. My presentation will consist of 5 sections. The first section, I will talk about the background and overview. And the second, I will introduce 2 recognition models. The third part is a standard database. The fourth section is our experiments and the results. The final is the conclusion. First, let me introduce our research. Online handwriting recognition has made unbelievable progress in widely used scripts such as Chinese, Latin, and Indian language. This technology is also applied in practice, such as the electronic signature, and the script used by the Yi people, which are the 6th largest nationality in China. Some researchers are conducting work on the recognition of offline handwriting, where there are few studies related to the recognition of online handwriting. But some e-script information systems require this technology to process handwriting data and enhance e-language information. Since Yi is a photographic script, it's closer to Chinese than other language, So the HDR for Chinese can provide a reference for recognition in e-character. The figure below is a Chinese script and an e-script. However, there are still many problems and differences in practical application. So proposing a suitable e-script simple processing model is necessary. To solve the above problem, we propose two e-online handwriting recognition models. For the server side with enough computational power and the mobile side with relatively limited resources. And we also construct an e-online handwriting database and present a method for processing the struct of e-stroke based on the structural feature of the e-characters and recognition techniques for Chinese character. The next section is about the recognition models. Here is the model 1, RNet. I had to say that all the networks are constructed by the GRU based on the original two-dimensional coordinates for attribute of x-axis displacement, y-axis displacement, stroke start point, and the stroke end point are ended. Thus, each item of the sequence input to the recurrent neural network is a 6-dimensional vector. RNet is built as a deep recurrent network. The model inputs the pre-processing stroke data into the network for further extraction. Then the further extraction, further matrix output from the final layer GRU is expanded into a 1-dimensional vector by the flattened layers. And then a fully connected layer is used for decision output to obtain a probability vector of 1,165 dimensions, and the character with the highest probability value after softmax classification is the final recognition results. It's mainly used for the recognition of handwriting character with high accuracy. But because Model 1 has limitation on the hardware resources of device, considering input thinness with limited computational resources, we propose a more mini model, is the parallel RNet. It combines the idea of neural network and traditional stroke-based feather extraction, which centers on a series of small-scale networks to recognize each sequence of stroke in the sample. In this network, all strokes are divided and then recognized by oneself using parallel subnetworks. Since the sequence recognized by each subnetwork must be a complete stroke, there is no need to add additional information to mark the stroke's begin and end. So the input vector to the network can be reduced to 4-dimensional. In this figure, GRU summary uses the structural information of strokes as the data augmentation, which is applied to assist in model decision making. Anyway, it's a lightweight model for handwriting input sense with limited computation in resources. And to address the problem of no public available e-online handwriting dataset for use, we construct a standard e-online handwriting database and propose a pre-processing method applicable to e-character simple to improve the accuracy of model training. We collected data from mobile devices, rotated and penned the samples to achieve sample expansion. The final sample data set database was constructed with 442,768 samples in 1,165 categories. Each row in the database is complete adjacent that represent a sample. The figure below is the application screenshot when we collected the database. Stroke convention is expected in the writing process, inspired by the online handwriting Chinese character data augmentation method. The drop stroke will apply it to e-character samples. It must be noted that to ensure sample retain the overall skeleton after drop stroke, the sample must retain at least 2 strokes. And we propose merge stroke method to mimic cursive handwriting in E, where each stroke in the original sample has the probability of being connected with its next stroke to produce a sample. the result from some simple after the complete drop stroke and merger stroke are shown in this figure. The next data augmentation process is stroke structure information. It can represent the detail of the location, size, writing direction, and the stroke length in simple. And the simple of the same character formed similar after prior processing. So we combine traditional structure-based and neural network-based method, use the structure and the potential correlation between stroke to assist the model in making the final decision. The stroke structure information show is as follows. After this method to the database, the number of simple point is reduced to less than 15. And the same time, the number of simple stroke is at least 13. And the order of writing stroke is solved by decreasing its number. We conduct experiments on our database and perform several comparative experiments based on RNNet and parallel RNNet. For the training of RNNet, we experiment with GRU of different depths, including 1 to 3 GRU layers and 1 to 2 fully connected layer. It can be seen that 2 FC layers converge faster and with high accuracy than 1 FC layer. At the same time, the model's training time increasing with the network's depths, while the recognition accuracy on the test set is basically the same for 2 and 3 layers. Therefore, the final network used 2 layers of GRU and 2 layers of FC layers, it means the ID5. Since parallel RNNet is a series of parallel GRU network working independently, so we need to determine all network sequence lengths and output dimensions. So the length sequence of the network is shown in the table 2. And when the RNNet is applied to the classification task, the output dimension represents the number of categories that the network can recognize. Therefore, the output dimension of subnetworks will directly influence the final recognition results. So we experiment with several different specification of dimensions, and several representative specifications are listed in the table 3. These models have the same network skeleton, and the different scale are reflected in the output dimension of subnetworks. We found the price of model accuracy improve in the increasing in training time when the output dimension increased. Comparing the model from ID3 to ID5, it's clear to see that setting the output dimension according to the sequence length of GRU has almost not bad effort on the final recognition accuracy, but reduce the training time. Based on these results, the model select ID4 as the final structure of networks. According to table 5, both merger stroke and drop stroke improve the accuracy of models and perform better when they are used together. It plays a role in reducing model overfitting. We also combine our models with some popular Chinese online handwriting models on database, which are built based on convolutional neural network. These results indicate that RNNet surpassed the previous method and help us improve the method accuracy by finding the information of spatial order in sequence data and outperforming other models in training time. While parallel RNNet has the most excellent training time, although it lost some performance, it's a model suitable for E-characters and other language with a small number of strokes. Nevertheless, the 2 proposed models still have rooms for improvement in terms of recognition accuracy compared to other advanced process for the other language. The models can only perform recognition of a single E character. E-handwriting recognition is in multiple lines has not been explored. In the future, we will try to use transformer and attention to solve this problem. Thanks for watching. If you have any question or suggestion, it's really nice to talk with me.
Okay, thank you very much. Okay, are there questions either online or in person? You pointed out at the beginning the similarity between the Yi script and the Chinese script. Why is there a need for a different architecture, or different procedure to recognize online Yi versus online Chinese? Why is there a need for?
Because I think
the
the Chinese, because I think the Chinese character is more complex than the E, and the E character is have more arcs than the Chinese. So we need to compose a different recognition model for the E character.
Do you think the model for the Yi is a simpler model than for Chinese?
I think it's not. I think the simple we propose is a special model for the E.
I encourage you in the future to do more direct comparison between what's possible with the Chinese and the algorithms there versus yours. But thank you for the work that you've provided for us.
Yes, yes.
Any further questions in person or online? Okay, we'll move on to the next paper. Paper number, where are we on? 4-5. Progressive Multitask Learning Network for Online Chinese Signature Segmentation and Recognition. And this will be presented by the fourth author, Zhang Chen, or maybe not. There he is. What do we need to do to get his video up? Okay, nope, it's there. But
Okay.
just a
Good
moment. We're trying to
afternoon.
get, there we go. Okay, perfect, great. And thank you for sharing your image to also to join us more closely.
Hi, everyone. Good afternoon. Can you all see my slides?
We can see it's trying to come. We're still waiting for it. So it's just have to wait. It says you've begun, but the system's still progressing. Just a little bit of patience.
All right. Just tell me when you are ready.
Yep.
Okay.
Zoom is thinking about it. It's still not coming. Maybe you can stop sharing and try resharing.
Okay, I will try.
Your bandwidth is low. Maybe you need to turn off your video. As much as we enjoy having you join us. And maybe stop sharing and try starting the share again. Okay, now try the share again.
Does it work for now?
Not yet. Are you someplace with very low bandwidth?
Yeah, it might be.
Can you maybe send your slides to our staff here?
Okay.
So put them in the chat to our. So if you look in your chat, they will give you the email address where you should share them. We'll try projecting them here and you can then see them and we'll forward for you. So watch your chat for instructions. And if we're still experiencing some difficulty. Is the speaker for paper 4-6 available to start now? Maybe we'll come back to you after we work on getting your slides. Zhang Hao, are you pause for a minute? And is our speaker for paper 4-6? Are you available to start now? Great, thank you, Rob.
Yes.
Okay, so Zhang Hao, stop sharing, please. Okay, there we go. Raphael. Okay, so slight change of plans, everybody, as we work through some technical issues. We're going to move on to paper 4-6 and come back to paper 4-5 in 15 minutes. Paper 4-6 is self-attention networks for non-recurrent handwritten text recognition. And it'll be presented by Raphael Darcey. And if you change, we can see your screen really well. If you put it into slide mode, there we go.
Yep, can everyone see that?
Very good. You have 12 minutes to present and 3 minutes for Q&A.
Okay, thank you very much. Very excited to be here today. My name is Raphael Das. I work for a company in the United Kingdom called Adaga. And we wrote a joint paper with the University of Bristol titled Self-Attention Networks for Non-Recurrent Handwritten Text Recognition. And I'd like to speak to you today about this. So first, a bit of the context of the problem we're trying to solve. We are focusing specifically on the line level offline HTR task, which is a task of transcribing a digital text representation from a static image of a handwritten text line. This is in contrast to something like online HTR, which transcribes text as it's being written dynamically. And you can also perform offline HTR on the level of whole documents or paragraphs, but we focus just on text lines. Naturally, this problem is both an image and sequence processing problem. And so a lot of the research has taken inspiration from these two fields. And usually the systems we use to solve offline HTR make use of both of an optical model that creates the initial transcriptions from the input images, and then a second language model, which performs some form of statistical spelling correction. However, in our project, we were only considering the optical model, and we assumed that the impact of any language model would be independent of the choice of optical model. A little bit about the history of optical models. Previous methods relied upon hidden Markov models and handcrafted features, but the current methods we use rely almost exclusively on artificial neural networks. Offline HTR was traditionally applied in a commercial setting, such as for bank check recognition or for postal address recognition. But in recent years, it's become increasingly popular for academic and archival purposes, thanks in part to the development of platforms like transcribers. As I mentioned before, kind of state-of-the-art methods make use of artificial neural networks. In particular, we use these hybrid architectures of convolutional and recurrent neural networks that are trained end-to-end with CTC. A little bit of context, the recurrent neural network can process sequence elements sequentially one at a time, storing the context of previous process elements inside of it so they can learn relationships over time. These CNN, RNN models are what's used by transcribers in industry, and users usually have to train a new model for each new handwriting style that they'd like to transcribe, which is quite annoying as this often requires more tagged data. There are some problems with recurrent neural networks. Firstly, there is a vanishing/exploding gradient problem, which means as two elements in a sequence become increasingly distant, it becomes increasingly difficult for the recurrent neural network to learn a relationship between them. The second problem, which is probably more applicable here for our project, is that the sequential nature of these recurrent networks precludes parallelism, which often makes it difficult and slow to train these models. There have been improvements to the traditional RNN unit, the LSTM and the gated recurrent unit. And while these can be computationally faster and can resolve some of the vanishing gradient problem, they don't really tackle the underlying problem, which is recurrency. Outside of HDR research, so focusing on some recent advancements in sequence processing, the transformer has become the new state-of-the-art architecture for many NLP tasks, and this has replaced the recurrent networks that were once popular. These transformers are entirely non-recurrent thanks to the use of self-attention networks, which makes them much more efficient to train than RNN-based architectures. This training efficiency has enabled the pre-training of large NLP models on data sets that were previously intractable to train on with recurrent networks. And these kind of generic pre-trained models work out of the box and can be adapted to downstream tasks with little to no fine-tuning. And examples of this are GPT and BERT. And we're also starting to see a similar shift in moving away from recurrent networks to transformer or self-attention-based networks in other fields such as image and speech processing. Just a little bit of kind of context of what a self-attention network is, what we refer to as a self-attention network or a SAN. This is equivalent to the encoder layer of the canonical transformer. These kind of have two primary components, the multi-head attention layer and the feed-forward network layer. The multi-head attention layer transforms incoming input features based on the semantic similarity between its underlying components, whereas the feed-forward network is what actually performs the learning inside the SAN, and it has like a nonlinear transformation, like a traditional artificial neural network. These self-attention networks are generally computationally cheaper and require fewer sequential operations in an RNN for a sequence of the same length and dimensionality. And you can see why this is why it makes them much faster to train. Another difference between RNNs and SANs are that recurrent neural networks can only model their relationships in one direction through time, whereas self-attention networks, because they don't consider the position, they can learn the relations between arbitrarily distant elements. We have proposed a new optical model architecture, which is basically a hybrid between convolutional neural networks and self-attention networks. And these are trained end-to-end with CTC. You can see a diagram of this architecture to the side. And we've basically taken the state-of-the-art CNN RNN model and replaced its bidirectional LSTMs with the self-attention networks. So we've kept the convolutional block the same. And this architecture has several hyperparameters, including the number of self-attention layers in the decoder step, the number of attention heads in the multi-head attention layer, the different embedding and hidden sizes, as well as the dropout rate, which is applied after every self-attention layer. Quickly, I'll discuss the data sets that we used in our experiments. We've used 4 human data sets. These are the Benton, the IAM, St. Paul and Washington data sets. You can see some of the characteristics there. These are quite popular data sets in HDR research. I'd like to note that this is biased towards English languages and Latin scripts. So this hasn't been evaluated on other languages. During our project, we also generated an entirely synthetic data set. We sampled random sentences from the Brown corpus, rendering them into images using one of over 400 handwritten style electronic fonts. And then we repeatedly deformed these images to kind of simulate random natural noise using methods such as the elastic deformation. As you can see in the table in the top corner, the synthetic data set was significantly larger than the human generated data set. And we intended for this data set to be used for pre-training, and then we can take models and fine tune them on human data afterwards. Here are some examples from the synthetic data set we generated. I'll read this up for just a moment so people can read them. And you can see we made some attempt to try and give different types of background noise and change the direction of the text. And you can see the kind of oscillations of the elastic deformation that we used. Moving on from that, describe the experimental setup that we used. We trained our models under the exact same experimental setup on each human data set separately, both with randomly initialized weights and weights that we achieved after pre-training on the synthetic data set. We used the RMS prop algorithm with CTC loss. We also introduced some kind of learning rate reduction mechanisms and early stopping mechanisms. And the kind of final output probabilities were decoded into our transcriptions using the CTC beam search algorithm. All images that we input our models were augmented and randomly distorted with the kind of canonical techniques such as affine warping, dilation, and erosion. This is just to artificially increase the number of training samples we have. And we also, the hyperparameters of our proposed architecture that we described earlier, these are the settings we use, and these were calculated using a grid search optimization on a combination of all the human data sets. And this was used for all the experiments. As a comparison, the RNN-based model we used had 9.6 million parameters, and using the hyperparameters above, our proposed architecture only had 1.7 million. Moving on to the results, averaged across all the data sets, regardless if it was pre-trained synthetically or not, our proposed architecture required 0.35 times the time that the RNN model required to train, which is a significant reduction in training time. However, there was a slight discrepancy in terms of the character and word error rates. So you can see before with pre-training, our model achieves about 8% or 7% of the state-of-the-art recurrent performance. And it performs a lot worse without the synthetic pre-training, which means the pre-training is necessary. And we also found that the positional encoding that is used traditionally with transformer and self-attention network models was not necessary, as shown in the table below. So all in, we have proposed a SAN-based optical model architecture as an alternative to a leading recurrent architecture. And we've demonstrated that this architecture is a viable and efficient replacement for recurrent networks. So there is a slight trade-off. You will take a hit to your character and word error rates, but this is at the cost of really reducing your training time. And as we've seen, the self-attention networks tend to be quite data-hungry models, and they perform best with a large amount of pre-training data. And I think that it's important for HDR for us to start moving away from recurrent networks and start using more self-attention network-based models, as this will allow us to train larger models on larger data sets, as I described before, that are completely intractable for recurrent methods. And this in turn, I hope, will enable us to develop very generic pre-trained models like an NLP, such as BERT and GPT, that we can use out of the box. And we can start reducing some of the initial costs that users have when it comes to using HTR. Yeah, that is the end of my presentation.
Great, thank you very much. Are there any questions in person or online? Can you go back to your results slide?
Yep.
Yep, that's the one. My vision's just a little bit bad. So can you explain what was going on with the Washington data set with 100% word error rate?
Yeah, so if I go back to show you here, the Washington data set was the smallest out of all the data sets. So without any pre-training, both the recurrent and the self-attention model diverged on the Washington data set, and they stopped after quite a short number of epochs. This was likely due to using the same experimental setup across all data sets. So in the future, we'd probably want to optimize that training setup and the kind of early stopping rate based on the characteristics of the data set.
Okay, I didn't think it was that much more difficult to read from the samples I've seen. Is that a question in the audience? Just stretching. Okay, great. Raphael, thank you for joining us.
Thank you.
Okay, we'll go back to paper 4.5. We have your presentation downloaded, or we have the presentation about to be downloaded. There we go. Xianghao, are you ready to join us again?
Yeah, I'm ready. Sorry for
Okay.
the trouble.
We've got a team of wonderful assistants here working on everything, and they're sharing the screen. Can people online see the slides?
I can't see the slides.
Can people online see the slides?
Yes, we can see it.
Great.
Yeah, I can
Okay.
see it right now.
Okay, great. So Xianghao, if you would just let us know when you'd like them forwarded, we will progress the slides for you. So again, joining us remotely for a progressive multitask learning network for online Chinese signature segmentation and recognition, Mr. Xianghao Shen will now present. You may begin. You cannot see the slides?
Sorry, my resolution is not clear, but I can see the slides, but the bandwidth is too low for me, I think. I will use my colleague's account for the next presentation, if I can.
So you'd like to postpone again? Is that what you're saying? Okay. Yeah, maybe you can look at the slides on your computer and just tell us.
Can you
when
guys? Yeah.
So if
I
you
will
just
use
go to
this
audio-
account.
If you go to audio only, we'll play the slides here. You look at the slides locally on your machine and tell us which slide you'd like to go to. Can you guys run the slides again? We don't have 2 minutes.
Can you guys show the slides again? I will present from here.
So long as the other people who have good bandwidth can see the slides, we're good to go. Can we get again confirmation from somebody else who's in the online audience that they can see the slides?
Yes, I can see it right now.
Okay, great.
Loud and clear.
Okay, but you know what they look like because you wrote them. Okay, so we will begin, and again, when you want them progressed, just let us know and move them forward.
All right, thank you guys. Hello, I'm today's presenter, Zhonghao Shen. I'm presenting for you Progressive Multi-Text Learning Network for online Chinese signature segmentation and recognition. And this is a great work from our the colleagues and I. We are both from Chongqing Handwriting Big Data Research Institute and also the Chongqing AOS Technology Corporation. Our main task is mainly about Chinese signature verification, though, and this is part of assistant research. Can you guys go next? Next slide, please. Okay, so what is Chinese signature segmentation? The main task is to segment a handwritten Chinese signature into individual characters or words. It's simple as clear. But why do we do that? Many people have such questions. One may argue you can just do the signature verification without doing the segmentation? Well, actually, we find we can boost the performance of the signature verification based upon individual characters. So the first thing is to split into the single words, single Chinese signature. As you can see, we are currently doing the research of the signature verification based on single characters. Also, the other benefit of doing the signature segmentation is to collect tons of Chinese single words. So we can do a lot of other things such as data augmentation. You can merge individual characters together to form as many Chinese signature as you want based on the contents. So that's why we do signature segmentation for Chinese signature. Can you guys go next? The previous one. The next one. Yeah. So there are technical difficulties. Okay, I guess. Yeah, the previous one, the previous slide. Can you move to the previous slides?
We're on the one with technical difficulties. You may not
But I
see-
can't. Yeah, the slide is
Technical
still showing
difficulties
this.
with colored.
Oh, okay, I can see it right now. For the technical difficulties, I have summarized 6 types. The first type is character overlap. You can see that there are two types of characters sharing the same strokes along the X dimension. Also, you have the character intertwin. The stroke is shared among the nearby 2 characters. Also, you have awkward layout. That is to say you have characters spaced very far behind. Also, you can have one character with a composite structure. That is to say you can further split the character into 2. That makes another different type of signature with different contents. Also, you have cursive writing that is hard for the OCR to recognize the right content. And the most difficult one, I guess, is artistic writing. You have a artistic flourish around the body of the signature. Actually, there are more difficulties. These are just common ones. Can you go next?
We've moved the slide.
Okay,
You can't see it yet because you have a delay.
Yeah, I can see it right now. Sometimes the delay is very long, sometimes don't. For the SOTA, we usually have over-segmentation methods. That is designed for the text line recognition. But this model has some limitation because it heavily relies on the linguistic models. But for Chinese signature, it is very short, normally comprised of 2 or just 3 words, and doesn't have any linguistic meanings. Also, it doesn't really solve any problems or difficulties we talked about earlier. Go next, please. All right, so that's our methodologies, the progressive multi-text learning network we present. The network has mainly three blocks. The first block is mainly about the pre-processing and the feature extraction. The second block is just stacks of transformer encoders. And the final block is to make the final prediction based on the multi-text and progressive learning. Can you go next? Okay, for the feature extraction block, we first have some pre-processing step. You first have to split the whole signature into strokes. How do you make the decision about the splitting points? Well, you just take the angle, the tangent angle of each point. If you have a sudden sweep of angle at such point, you make such split. All right, so for each point, you have three types of features. The first type is the state of the point. You have the pen up, pen down, and otherwise you are moving the stroke. So it's three-dimensional, one-hot encoding. And for the second type, you have the directional feature. We borrow the idea from the paper cited below. It's about 8 directional features. Such features have been used by many other papers as well. Basically, you just calculate the angle of each point and you divide the angle into its nearby direction, 45 degrees of angle. And the third type of feature is just a coordinate feature. It's simply the normalized XY dimension. All right, so also there are 2 types of branches. The basic idea is you have stroke feature that can be learned from the point feature. But there are mainly 2 types of stroke feature. One is the semantic meanings of stroke-wise features. Can you go back to the next slide? Go back, sorry. Not next. Yeah, as you can see, the first block, our feature extraction block, has 2 branches. The first one, you have a CNN network. This one is to extract the semantic meanings. And the bottom branch, this is for the spatial meanings. The top block only uses all 3 types of point features, but the bottom block uses only coordinate features for the spatial presentation. Okay, so after you learn the stroke-wise features, the stroke-wise features is then feed forward to the next block, the STE block, which I will talk about next. Can you go next? Yeah, and next. Okay, so for this block, it's simple. It's just 8 transformer encoders, each with 8 multi-heads. You just stack them, and there's nothing strange or weird about it. Can you go next? All right, finally, we got our backbone network, progressive multi-text interaction block. Why do we do that? We are motivated by some phenomenon we observe that some cases cannot be solved without knowing the Chinese signature meanings. So you cannot know where to split if you do not know the content of the signature, right? And then we observe that the 2 texts, the segmentation and the recognition, are mutually dependent. You cannot really do the other text without knowing the others. And then the network, for the network design, we just borrow the idea from the works below. For the basic network, we borrow the idea from the paper, the progressive multi-text learning with controlled information flow, but with some slight modification, because our 2 texts are different from the paper proposed. For the segmentation branch, it is basically a conditional random field. And for the recognition branch, it just mainly composed of fully connecting layers for the multi-classification. All right, so you just, for the progressive network, you first make some intermediate prediction based on the network I presented. And then you have the stochastic map, SM, stands for stochastic map. This block is used to regulate the information flow from the previous prediction and the older prediction, the older hidden state feature map H. So you want to learn your better presentation T from the previous prediction Y, rather than from the previous ones. So you want to make the mutual information here. I cannot show my cursor here, as low as possible. So that's a main point of the progressive learning. And this block, a stochastic map, is mainly designed from the deep variational information bottleneck, VIB. And then you make the final predictions based on the modified presentation TSEC and TOCR. And you use the same network to predict the final result. Okay, so can you go next?
Maybe you can be a little bit brief because we're running out of time.
All right, so there are mainly 6 types of loss for intermediate and the final prediction loss and the middle representation loss for the stochastic map. And then we use the total loss right down below cited by this paper. The main benefit is to have a regularized parameter C for each text, and this parameter C can be learned from its own rather than hard-coded. So can you go next? Okay, so for the database, there are no public database as far as we know. So we use our own, but our database is not open to the public for the personal security reasons. And also the training set is merely 80,000. So that's enough for the segmentation, but not really enough for the OCR. So you may say the OCR result is below the other OCR tests. Just let you know. And then can we go next? Okay, so for the segmentation result, we compare our model with the others. And you can see the importance of our OCR, but we're running out of time. Maybe if you are interested, you can go to our paper. Can you go next? And this is a comparison result of the recognition. Also, this may not be satisfactory, but our main focus is on the segmentation rather than the OCR. Can you go next? Okay, for the quantitative result, you can see there is a nearly 10% boost of performance of our model, comparing other models, both for the segmentation and the OCR. Let me reiterate the importance of the database. The database is not enough for the OCR, but enough for the segmentation. Okay, can you go next? Can you go next? Okay. So for the ablation study, we study the impact of each block. As you can see, the most important one is this feature block. The main idea is to convert the point-wise feature into stroke-wise. And also there are slight progress of the progressive learning and interactive learning. It is slight, but still like 1 to 2% of boost of performance. So that's all for today. Thank you very much.
Okay, let's thank our speaker. And thank everybody for your patience as we work through technical difficulties. If you have any questions for the author, I encourage you to reach out to him. I presume that your email address is in the paper. So if we
Yeah,
now
that's
can
right.
people change back to the Zoom window.
So hello everyone, my name is Nemotuan. So today I'm very excited to present about my topic related to improving isolated classification task for public manuscript. So today outline of presentation content with like 4 main points. The first one, I introduce a little bit about public manuscript, and then we talk about isolated character classification, and then we talk about like experiment, and finally we conclude our presentation. So like historical public manuscript, like thousands of public manuscript has been recorded on the PubLib for like historical, even Buddhist practice, astrology, or even like medical treatment. So, and for like Southeast PubLib manuscript analysis, like offer the known challenge for the document analysis task in like ICFHR 2018 contest. And PubLib manuscript can be divided to 3 types of manuscript. The first one is like Khmer from Cambodia, and second from Balinese from Indonesia, and also last one is Sudanese from Indonesia. So we jump to the challenges. So the first, like for historical PubLib manuscript has like faced many challenges. The first major is like image quality. So as we know that historical document like the face many problems with the physical issues as like degradation, defect, and also like I mean the low quality of images because we capture it with digital camera, so it's not provided the good quality. And another one is like character similarity and writing form. So the first one is like they have like many similar character, but there is like many different meaning. Example, like they have like around like 10 similar, but it is different meaning. Another one is like multi-level of character. As we know, I've seen in the pictures, like in the like PubLib manuscript, they have like they can divide to three level. Example, bottom man and up, and like top side. So and they also can contain with like different type of components. Example, like vowel, consonant, special, subscript, and also many else. So another one is like the most importantly is lacking of data training. So as we like it's a common problem in deep learning. So like data set are required for training in deep learning approach, and also like they have only few study on this data set. So today in this paper, like we try to explore, we aim to explore like front end and back end of isolated character classification. So in the front end, we will like discuss about data agreement, how to extract like additional data set, and also we talk about like image quality. And for the back end, we try to comparison between like we try to train on the deep CNN and VIT variant, like which one is the best for classification on PubLib manuscript. And so we're going to talk about data pattern generation. Like we know that since like recent deep learning approach require a large amount of training data, so we need to add some method for like enlarge the data set of isolated character data set from PubLib manuscript. So we have like 2 steps. The first one is you obtain the additional data collection from text line and the text image PubLib data set. And another one is we employ like data agreement techniques to increase the scale of existing and the new data collection. And so the first one is like how we extract the additional data set. So basically, we extract the character epileptic character from the text line image or the word text image. So we asked like 15 local university students from Cambodia and Indonesia for manually extract it from them, and we divide to two groups. The first group is the collector. They collect the character from PalmLib, and another one is like validator. They label it and then check it like it is correct or not, something like that. And yeah. So we're going to talk about image enchantment for PalmLib manuscript. So I mean, like we simply try to apply the simple method for the cleaning on import data set. So we found out that previous study they always like they put RGB or grayscale direct for training. So I mean, like for historical document, they should be try to improve the quality of image. So we propose like the simple steps for improving the quality. First one is normalization. Normalization is like we need to balance the contrast between the image, because we found out like the capture from digital camera, the balance or contrast is not balanced, and then also we need to reduce some noise. And another way is like we need to improve the readability of the low quality image by binary them to the binary image. So for normalization, like we simply use the simple method that do automatic contrast limited hologram with the duogram migration. So inspired by update version of contrast limit adaptive hologram, CLAHE. So we use it for like a correct contrast between text and the background, and then this method also can use some noise from the image, and also yeah. And for the binarization, we use WAN that labeled by the order name. So it was proposed to improve the solver method to improve the quality of the image. So I mean, like the traditional solver approach is struggle for segment between text and the background. For example, like it's contrast between foreground and background. So the text in background is down. So there may be less noise in the text image. So for the WAN, it can be like calculate the binarization level or something like that. So we can set the level so it's more effective than the traditional one. And for the training CNN and VIT, so in this step, we try to find it out like we try to comparison between multiple model of CNN and VIT architecture. So for CNN architecture, we choose like different training approach after like VGG 15 or VGG 19, ResNet 15 or ResNet 101, and also EfficientNet B0 to EfficientNet B3. And for VIT architecture, so we try we start with like the traditional one is VIT-F and VIT-B, and also we try to another variant like DEITS and DITV, and also we try to hybrid one the conditional transformer with 15 and 21. So we're going to talk about like experiment and results. So in our experiment, we use like 3 different data sets. The first one is data set from ICFHR 2018 contest data set. Another one is our new starting data set, and the third one is we match it together. Yes. So in our experiment scenario, we need to find out like we need to answer like third question. The first one is which the deep learning method technique is the more effective for backend approach for script in Asian PalmLib dataset. And for like second experiment, we need to find out like how that the quality of the dataset affect accuracy. And for the third experiment, we need to know that that's our new dataset, and the image enchant thickness effective for isolate character classification task. So here is the result of the first experiment. First experiment, we compare between share between like different CNN and VIT model on like ICHR 2019, 2018, and also with the data agreement, like basic data agreement. So surprisingly, we see that like ResNet and EfficientNet that can be lab on like so impressive result on classification task. So as we know that like transformer is trending now, but CNN like EfficientNet and ResNet is still be effective for public manuscript dataset. And for the second experiment, we as I mentioned about like the previous study, they try with the RGB and grayscale image. So we select some approach for train with the binary image. So we try to find out that like how binary image work on training. So we can see in the picture like binary image can be improve the quality of accuracy of the method, the approach. And for the last experiment is about we select the best backend of classification task in experiment 1. So we choose EfficientNet B0, and also the best amount, the VIT, DEIT, and also CVT, and we also apply it with our like data set, and also apply it with like IEPAM, is it like image enchantment. So we can see like the accuracy can be improved if we use the additional data set with the the image enchantment in the pre-processing. So pre-processing may be necessary for improve the accuracy of the correct classification. Yeah. So in conclusion, so we present about like we use additional data set and pre-processing it for improve the classification task, and also we present the new data set that can be extracted from text line, and what we make it around like 15,000 images, and also we compare between like CNN and Vincent, and in addition like data agreement and the cleaning may be necessary for improve the in-selected character classification. So consider the result, the ResNet and EfficientNet may be used for like our future work in public recognition system. Thank you so much.
Thank you very much. Are there questions either live in the audience or online? Anything online? I think everybody wants a coffee break. I know there's been lots of other work on the palm leaf manuscripts, and that they're becoming a really popular thing. So it's great to see more work on them. So I guess we will therefore conclude.
Hello, everyone. Do you hear me? Okay. So thank you for the introduction. As already said, I'm Christian Gold, and I was working with Thorsten Zech on removal of ruled lines. We are from Catalpa, which is a research department with the aim to make use of artificial intelligence to support teachers and learners. And our group especially supports teachers in the scoring process of handwritten exams. So in exam situations, students are under stress and nervous, and as a result, they often tend to write illegible and crisscross. So a common way to increase the cleanliness and readability, ruled lines are inserted, so students have an orientation and font size they have to stick to. But this causes a problem. So ruled lines decrease the recognition performance of handwriting recognition, and the removing of it is problematic when the reconstruction is missing. As example down here, if we split or if we erase just a ruled line without remaining the shape of the G, the recognizer might end up recognizing this character as an A, which would then be incorrect. So we want to train a network, and for that data needed to be available. And this data must look like there must be a version with and without ruled lines. And this of the same document, and this is just not available. And if you remove them by hand, we could all think about that we have to think, is this pixel on the line or is it a character pixel, and how to remove that or not remove it. So this is really a lot of work. What we come around with was creating a synthetic data set using word concatenation. So we're using the IAM words snippets and set them into text lines and several text lines into paragraphs. So one issue is that they have to be aligned on a horizontal line. And thus we are checking every character which is in this word snippet and try to align them with their bottom body line. So they are look-alike. They are on the same height. To make it even more realistic, we are using a lot of random variations, like the rotation of ruled lines, the thickness of the ruled line, the gray level of the ruled lines. We do some destruction of the lines, and we add background noise and a lot more, just to make it as realistic as possible. Here's an example of 2 lines. On the top, we have the version with root lines. So first we are creating without root lines, then we put on the root lines in there, and we can then use this as the input for our network. And we want to target our network to create the version we see on the bottom where no root lines are present. So this would be our network. We had experimenting with a lot of different kinds of networks with different layer numbers and filters and so on. And to decrease the computational costs, we split all these images we created synthetically into smaller tiles of size 512 by 512 pixels. But before going into the networks, I want to speak about the evaluation. So when you have the synthetic data set, we are able to make a pixel-wise comparison between this root line should be removed, and we can take every pixel, is it removed perfectly or not? So we can use the root mean squared error for that. But we want to do it on a real data set later on. But as I already mentioned, there's no ground truth available. So where a version is with and without root lines. So we have to use the derived extrinsic metric. So we use character error rate. For this, we have to train a recognizer, and we do that on a text line level. And we do not use any language model. So we are training with the IAM lines using the learner, the large writer independent text line recognition split, and we've come up with a CRR at the end of 11.5%. So furthermore, we're now able to compare different neural network setups by the recognition performance. So how clearly can the recognizer read our text? As said, we want to test it on a real data set. So we are using the FDLX data set, which comes from the University of Cologne. It has 5,600 documents and was written by more than 900 children. It's a German data set. And out of this, we use the first 50 documents. These have been written by 9 children, all of the grade 5th, which is about 9 to 11 years old children. And we had to manually transcribe them. That's why we only used 50 pages and in total. So the first thing to compare everything to would be to say, okay, we don't remove those root lines and feed them into the recognizer, and this would end up with a recognition performance where we have an error rate of 66%. So only 1/3 of all characters have been recognized correctly, which is really awful. So furthermore, we have seen an example where I just erased the root line on a morphological approach. And this should be our baseline here because it was a really easy one without putting too much thought into it. And we could go down to 35% error rate. So we halved the error rate already. And now we're coming to our networks. So I have been inspired by by an autoencoder architecture, which was used to get rid of all noise and coffee stains out of the documents and retrieve only the handwriting in these documents. So using that as a starting point, I experimented a lot with different numbers of layers, and all autoencoder architecture have the same shape. They're rotated hourglass with a bottleneck in the middle, which comes from downsampling, upsampling, and through this bottleneck, some information should be lost. And if we think further, we've been hoping that these would be our ruled lines. So at the end, this is working well, or at least better than the morphological approach, and we are able to reduce this number down to 31% in error rate, which is not a big step, but at least it's a step. And after experimenting a lot and varying a lot of this architecture, we've been thinking, okay, we can't get any further than that. So what to do next? So even going more complicated, or what we have done, we stepped back and thought we want to have a one-to-one image transition. So why we should increase or decrease the image size within the network, and came up with a simple 3-layer architecture with a quite bigger filter size in here. Again, we varied a lot of the number of layers and the filter size and how many filters there are, and got down to approximately the same result than the autoencoder. But if you can see on the test set of the synthetic data, we can see that the root mean squared error was reduced. So we're getting closer to the original input image, or the target image, I'm sorry. So furthermore, when we looked at these pictures, which was predicted by the network, we found that they are a little bit darker and they had a lot of trouble with the background noise. And thus we are thinking, okay, so when it went to all this network, at the end, it has to, there might be 90% of all pixels might have not be changed, and only the root lines should have been changed. So maybe this information is not going through the network at all. So we've been coming up with the idea that we are not using the network to erase it by itself, but to make a mask where the root lines are in there, and subtract this mask from the input image. And this was working well. So with a 3-layer and using this subtraction, we got down to 28 by 0.5% in the CRR level, which is still far away from the 11.5% we had from training on the IEM dataset. So there might be some reasons for that. First of all, we are now on a German dataset and not on the English one. So we have another character set in there, like the umlauts E, Ö, Ü, which are then mapped to A, O, U in English. So there's a gap. Then we have cross-out words a lot. Children in this age are writing, we can see that here in the example, they are crossing out, they're writing over it, they're crossing out characters in the middle of words, and a lot more. So we have a difference between children and adults as well. So children are learning to write, and adults have like decades of training to write by hand. Other influential parts are telemarks, and the others I already mentioned. But now I think it's interesting to see the results on a graphical base. So the original is on top, then we have the morphological where we erase the line. The autoencoder, we can see that it's blurry. When we look at the handwriting itself, and down there we have our all CNN with a 3-layer and subtraction. We can see that it's not blurry because the information from the input was presented at the end again. And we can see that the characters are, the shape of it are still remaining in here. Taking a closer look to that, when we have the synthetic data set with the original on left, the added rule with an overlay in the middle here, then the network should predict and remove the ruled lines. Having this in a close-up here, we can see that one specialty of this network was that not only the eye could be reconstructed because it was split into two parts from the ruled lines, but furthermore, the stroke of the E, which was aligning with the ruled line. So it was not just split up, it was aligning there, and if you just erased the ruled line, it was not present anymore. So the neural network was able to predict that as well in most of the part here. So we can see it in red, there's a little bit left over, which was not predicted. Coming to a conclusion, so removing root lines is really necessary. Even a naive morphological approach is helping a lot. And furthermore, we have been able to just reduce our numbers of layers and our upsampling, downsampling to just 3 layers with a subtraction, and this worked out the best. And as I'm a little bit over time, I want to skip the outlook and just want to come to the question section.
Thank you very much. Thank you very much for
Yeah, thank you very much for your presentation. Are there any questions? We have time for one question.
You did the naive morphological method to remove the line, but that doesn't fill the gaps. And you said your network is working to fill the gaps. There are other classical methods from decades ago that can fill the gaps somewhat. And they probably are computationally much lower expense than your networks are. Have you considered them? Will you consider them? And if not, why not?
We didn't consider them because what I showed last with the with this here. So I think that these traditional approaches with all the filtering or half transformation, finding the lines and whatever, especially this would not be possible when they are aligning on top of the root lines. I think, and this is what I figured out when I would look closer and zoomed in at these intersections, that the root lines are often, or most of the times, a little bit darker when they're intersecting with others. And those networks are able to figure out these small variations and pixels, which are have a little bit higher or they are darker. So to achieve the stroke characteristics which are aligning with the root line. That's why I didn't proceed with the traditional ones. I think they are capable of this example here with the eye. There would be probably be able to reconstruct that where they're, yeah. But I think not when they are aligning on the line. That's the beauty of it.
But what amount of that 28% error does that account for? So, is it worth it for the computational time and effort of applying a very large network? Anyway, it's something to ponder.
Okay.
Hello, can you hear me?
Yes.
Can you see my screen?
Yes, you can go on.
Okay, then I start. Hello, everyone. It is a great honor to share and communicate with you here. I am Ban Dongchen from South China University of Technology, Guangzhou, China. The topic I share today is complex table structure recognition in the wild using transformer and identity matrix-based augmentation. And I will share from the following 4 parts respectively. The first part is the background. And as we all know, tables are very common in our daily life. Although people can intuitively understand table contents, it remains challenging for machines, especially the tables taken in the wild. And some of the diverse tables are shown below, including fold and shadows tables, complex structure tables, wireless tables, mixed handwritten and print tables, oblique and distortion tables. And the current table structure recognition methods can be divided into 3 parts. The first is the cell extraction-based methods, and the graphic modeling-based methods, and the image-to-sequence-based methods. And each method has its advantages and disadvantages, as well as limited scenarios. The second part is the method. We treat the table structure recognition in the wild as an image-to-sequence recognition program, and adopt an end-to-end transformer model that can obtain both structure sequence of the table and the bounding box of each cell. Specifically, the model consists of a CNN-based encoder and the 2 transformer-based decoding brains, which can simultaneously predict the logical and the physical structure of a table. And figure 1 shows an overview of the adopted end-to-end transformer model. And among them, the CNN-based encoder is used to extract the high-dimensional feature vector of the input image, and the structural decoding brains is used to obtain the structural sequence of the table. And the cell bounding box decoding brains is used to obtain the bounding box of all table cells. Okay, since our model is a sequence recognition method, we need to convert the original annotation, such as HTML, into a sequence form. The specific structure categories and their description are as shown in the table 1. At the same time, we add a mask sequence, this slide, to ignore those structure categories that do not have corresponding cells. In addition to the categories in the table, we also need 4 special categories to build a sequence, as shown below. And the figure 2 is an example of the construction of a training GT. Current data sets usually adopt HTML, XML, LaTeX, and other formats to label table structure. But these formats are difficult to intuitively discover the characteristic of table structures. Therefore, we propose a new matrix representation to describe the table structure, and we call it identity matrix. Given a table, we can construct a row identity matrix and a column identity matrix to present the row and the column structure information respectively. And as shown in figure 3, the values in the identity matrix represents the structure of the table. For example, the cell in the blue box spans 6 rows in the table. Therefore, in the row identity matrix, the first position is 6, and the other positions are all 0. And through this method, we can construct a unique row identity matrix and the column identity matrix of each table. Based on the identity matrix, we can perform data augmentation, pre-processing, and post-processing of the tables in a feasible manner. And to increase the structural diversity of data sets, we propose a new data augmentation methods named TypeSbuilt for tables, which is also based on identity matrix. And for a table labeled in HTML formats, TypeSbuilt consider cropping the row and columns of the table, expecting to obtain a new table image and the corresponding HTML tags. For simple tables that do not have cells that span multiple rows and columns, we can directly obtain the crop table image and the corresponding HTML tags. However, for complex tables with cells that span multiple rows or columns, direct cropping may break those cells and not yield corresponding HTML tags. And the following two issues need to be considered. The first is where to cut from. And the second question is if the attributes of the cell are changed after cropping, how should the corresponding HTML tags be generated? And for the first question, as shown by the arrow in Figure 3, we can directly find a position where the crop can be performed from the identity matrix. And for the second question, when we crop a subtitle from the original image like this, we will find that the properties of cells has changed, such as the cell in the blue box. In the original tables, it spans 6 rows, but in the new crop tables, it only spans 3 rows, which means that the cell properties has changed. And we can follow the process in Figure 4 to correct the properties of the cells step by step to get a new table and its corrected labels. When we convert the table structure, into identity matrix, it can also be used as filtering tools. For the GTs, identity matrix can filter symbols with arrow labels. And for the results of the model, identity matrix can obtain those results that are absolutely wrong. Okay, the third part is the experiment. We conduct extensive experiments on several data sets to verify the effectiveness of our method. The statistics of each data set are shown in Table 2. We use the identity matrix to filter the original annotation, and we use ResNet 15 as the backbone network of the model. And the batch size on one GPU is 6. We use the PyTorch framework and the four GPUs for distributed training. And when training, the command data augmentation schedules and our proposed type scaling methods are used during training. And Table 3 and Table 4, in Table 3 and Table 4, we compare our methods. With others. It can be seen that our method achieves the best results on DAL and WTW dataset. These 2 lines. Okay, Table 5 verifies the effectiveness of the proposed type filter method. It can be seen that applying table filter can indeed improve the performance of the model on all data sets, and especially for the complex tables. And Table 6 and Table 7 verifies the robustness of the proposed type filter method, from which we can find that for the logical structure of table, only 60% of the training data and the type filter can achieve the performance of the baseline model. And for the physical structure of the table, only 40% of the training data and apply our type filter can achieve the results comparable to the baseline. It is fully proved that the proposed type filter can improve the robustness of the model. And the Table 8 verifies the effectiveness of the identity matrix-based post-processing. It can be found that on several benchmarks, the text structure results can be significantly improved after using identity matrix-based post-processing, and to fill out those absolutely wrong results, which can significantly improve the robustness of the table structure recognition system in practical application. And the fourth part is the conclusion. we treat the table structure recognition in the while as an image-to-sequence recognition problem and adopt an end-to-end trainable model that can obtain both the structure sequence of the table and the bounding box of each cell. We propose a matrix representation of the table structure called identity matrix. And based on the identity matrix, we propose a new data augmentation method named types filter, which can mitigate the impact of the data security on model performance, especially tables in the wild. In addition, the proposed identity matrix can also perform pre-processing and post-processing of the table structure. And finally, the experimental results on public data set demonstrate the superiority of the adopt model on table structure recognition problem in the wild. And they also reveal the effectiveness of the proposed steps filter methods. Okay, thank you all.
Thank you. Thank you very much for your presentation. Are there any questions?
Excuse me, the type splitters message usually seems to make the table smaller. Can this message make the tables larger?
Okay. Okay, this is obviously possible, but I feel like it requires different stimulus. For the regular table like PDF, we can randomly crop out a few rows or columns, and then we copy them and splice them so that a large new table can be obtained. However, for the table obtained by taking pictures, due to the distortion or other folding, we cannot guarantee the alignment of the cell of the table when we copying or splicing these rows or columns.
Okay, I know it. Thank you very much.
I see that we have a couple of questions online. So Gernot Fink is asking, are you considering handwritten or hand-drawn tables?
No, all our experiments are print tables.
Okay. The other question that we had was from Ajoy, who is asking, are you considering cells without content for evaluation?
I'm not clearly what you say.
Sorry, it says, are you considering cell without content for evaluation?
Okay. The cell without contents, we didn't use it for evolution. This is because our evolution is the TEDS structure, and like this slide, this column is the results with the cell content, and this column is the results without the cell content. Both of these we also evolution for those both of these.
Okay.
I extend my warm greetings to all the chairpersons, my fellow authors, and my fellow audiences. Today I'm presenting my paper EAU-NET, New Age Attention-Based Unit for Nationality Identification. My co-authors are Palainakote Shivakumar sir, Umapada Pal sir, and Chenglin Liu sir. So the following presentation has been divided into the following sections: introduction, literature survey, motivation, methodology, experiments, analysis, and conclusion. Firstly, why we need nationality identification. It plays a vital role in forensics for detecting crime from image documents, from handwritten documents. The proposed methodology classifies the writer's nationality based on the differences in handwriting styles from the strokes or age point. We introduce a novel model, a modified unit, the age attention unit, for the following task. So here are the samples from the 10 classes we are using for training. We have datasets from Bangladesh, Cambodia, China, India, Iran, Malaysia, Myanmar, Pakistan, Palestine, and Sri Lanka. So firstly, we go into the literature survey. We have the following papers. Duggan et al., who presented different methods for gender and writer identification. Nag et al. Paper wrote by our co-authors. They proposed a nationality identification method using the cloud of line distribution method for extracting features and classifying using a ASPM classifier. And then we have the Medha et al. Paper who used Gabor transform along with CNN for writer identification. So for motivation, as per the literature survey we've seen, there is only a couple of papers for nationality identification. Nag et al. Had only 5 classes and they focus on a different cloud online features. There are no papers using the age features for the same task. So we wanted to introduce a generalized method irrespective of the gender of writer, or pen, paper, or ink use. The proposed model, for the proposed model, we have a combination of age attention and UNIT for the age detection in handwriting text images. The proposed work combines the UNIT and CNN for the classification of handwritten text of 10 different nationalities. The results show that the proposed method is independent of the number of classes, size of the datasets, and applications. Here's the backbone of the proposed model, the model flow. Firstly, we extract the words from the whole document images. Then we binarize the images using OTSU. Then we go on to the feature extraction method using our proposed UA unit model. Then finally, we move on to the CNN classifier for the classification task. For age attention based unit, we extract the age features, the handwriting strokes from the handwritten document images page and reduce the background noises, the watermarks or the spots on pages using different image preparation techniques. Then we have the script connections which preserve the structural content of text. And finally, we have the gated convolution block, which separates the salient content of the text, the handwritten text, from the background details. So here's our model architecture for the EA unit model. Firstly, we have the unit backbone. Here's the unit encoder and the unit decoder. From inside the encoder, we have introduced the residual blocks and the gated convolution block for the age attention extraction. Firstly, we have the unit encoder and the residual block, gated convolution blocks. And finally, we have here the unit decoder. So this unit encoder is the same unit introduced for image segmentation. And then there we introduce the residual blocks. The residual blocks help us to prevent the structural content of the handwritten text. For the gated convolution, we can use the convolutions with attention to focus on the age features we have extracted using the segmentation method. We train the EA unit model using the DRIVE dataset, the digital retinal images dataset, and then we have here the following results, like a sample of images we have got from the unit model, and here we can see that from the input images, the structural content has been preserved, the form of the text has been preserved, and only we have extracted the ages from the handwritten format. Then we have the classifier for the nationality identification. We have introduced a 4-layer simple CNN classifier for the nationality identification, the classification task, for the gender classification. Then we move on to the experiments. And in the experiment, we have first done an ablation study. Then we go on to the experiments on age detection, experiments on classification of nationality, and then we have compared a gender classification task to show that our model is not confined only to the classification of nationalities. We can extend our model to other tasks also. So for ablation study, we have first used the baseline unit for age detection, and then we go for the classification. Secondly, we have used CNN directly without using our age detection model, and then we have found the result. The third point is the Harris corner detection, which we have used to replace our EA-UNet model and to compare the classification rate. Finally, we have shown the results of the proposed EA-UNet model. So here are the results of the ablation study. We found that when we use the original UNet baseline architecture, we only get 85% average classification rate. When we feed the images directly to the CNN, we get only 84%. For UNet with Harris corner detection, we get 87% accuracy, and for our proposed method, this is the UNet feature extractor along with the CNN classifier, we get up to 96% accuracy for the classification rates. Now the experiments on age detection. This is the sample images which I showed earlier. This for the qualitative results for the samples of each class. We found that the prominent ages are detected from all the handwritten words, and even the ages also preserve the original structure of the text, which we achieved through the skip connection. And then for the experiments on classification of nationality, we have shown the average classification rates for 10 class and 5 class nationality data. And then finally, we have compared our proposed method with existing methods for Nag et al. And Dagan et al. So here are the 10 classes which we have used for the classification nationality. And this 10 class dataset has been introduced by us for this paper. Previously, we had a 5 class dataset introduced by our co-authors in the previous paper, which is the Nag et al. Paper. So for the 10 class dataset, our proposed method achieves 96.8% average classification rate. We found 74.2% accuracy from the Nag et al. Paper, and the Dagan et al. Paper, which was originally designed only for gender classification, it achieves only 68.7% ACR. And for the standard dataset of 5 classes, our proposed methodology gave 93% ACR. Nag et al. Paper achieved 75%, and for the Dagan et al. Paper, it was 71.2%. To show that our model is not confined only for the nationality classification, we have proposed a gender classification task also, and we have used the IEM handwriting database to classify the genders using our EA-UNet feature extractor. For the gender classification, we get the ACR of 92.3% from our model. Nag et al. Achieved 81.9%, and Dagan et al., which was specialized for the gender classification task, they have achieved 89.5%. Here we can show that our model is not only confined to the nationality identification, it also achieves good results in gender classification. And here we go for error analysis. Like different things can happen, like the degradation of image quality. There can be a variation in writing style which can vary from different writers, and there will also be different colors which can be a bit difficult to extract the features when we binarize images, and also it also varies from the writing tools used. Here are some samples which have been misclassified by our model. Finally, we move on to the conclusion and future work. The UNet uses age detection to extract prominent information. Our UNet model, EA UNet model, outperforms other existing methods for nationality classification. Our model works well for other problems too, like gender classification. It's an IM dataset. And we plan for the future work. We plan to extend the work for addressing challenges and degradations in near future. We also plan to develop an end-to-end model for classification. Thank you. Please let me know if there are any questions.
Thank you very much for your presentation. Are there any questions? Yes.
Can you say more about how the dataset is generated for each nationality? How many writers have you used? Or is it just a single writer writing for a nationality?
No, we have collected datasets from different writers from different countries, and they had variations in the writing tools, such as pen, paper, the pages used. Many had watermarks on their pages, and all this stuff. Like the documents weren't collected from a single writer from a country, and we have collected for 10 different countries.
So it's just a single writer from each nationality.
No, it wasn't a single writer. There were many writers for the same country, and who varied in gender, ages, and everything.
Okay, thank you.
Okay. Could it be possible that I mean, as you mentioned, that there is data from different sources, actually like from data set collected in different countries? Could it be that what the network is actually learning is to differentiate between whether one input image is coming from one data set rather than actually the nationality of the person?
Actually, what we have noticed is for the Chinese text, they have the Chinese writes in horizontal vertical boxes. So when they write the Indian text, when they write text in English, they also have the ability to write in horizontal and vertical strokes. Whereas for Indian writers, they are more confined to writing in cursive. So these are the few differences which we notice when we collect data from different countries, the handwritten data.
Do we have any other question? Okay, do we have any idea of what the human performance will look like for this data set in particular? Also, I don't remember if you show what's the exact size of the data set. How many samples are you working with?
Okay, so we have collected around 1,000 images, which varied from maybe 30 in a class to more than 100 in the same class. It was around a total of around 1,000 images.
That's in total or just training?
No, that's the total of the 10 classes. For each classes, there were variations of 30 to around 100 or maybe more than 100, 120 images for a single class.
Yes, it's okay.
Yeah.
Please
So,
start.
Thank you very much, Professor Liu. So my name is Hong Tuấn Nguyễn, and I'm come from Qualcomm TAT Joint Research Laboratory at the Tokyo University of Agriculture and Technology. So today I would like to present our work in the handwriting recognition and also automatic scoring for the descriptive answer in Japanese language test. And in this work, our motivation is the from the fact that the scoring handwritten answer is the daily burden for the teacher. So as long as the teacher take time to score the answer, the wariness is increased, and that leads to the higher inconsistency in scoring. So that we want to make that to be the automatic scoring. And as we know, the examination is essential to evaluate the student learning and also their ability. Because the scoring is daily burden for teachers, so it could be more challenging during the university entrance examination because there is a limit of scoring time. So the selective question or multiple choice had been proposed to reduce the effort on scoring, but these kinds of questions make the student to learn how to select rather than how to solve the problem. So that now we think that the descriptive answer, descriptive question is still considered as the a better way to evaluate the solving problem skill of students and also their understanding of on the problem. And as we mentioned before, the descriptive answer take a large time and effort for marking and also challenging for computer-assisted automatic scoring. So in this research, we focus on recognizing the handwritten answers and also build the automatic scoring that could be helpful to reduce the examiner effort during the scoring process. So in 2017 to 2018, the National Center of University for University Entrance Examination in Japan, they organized the trial test on the math and also Japanese descriptive question with more than 100,000 students. And they here is some example of the student answer for Japanese descriptive question. And there's a large amount of handwritten Japanese answer been collected from this trial test. So that how large of this data set compared to the published data set in the same research topic. So here we found there's one of a similar research topic of there's one database is from the SCAT EBT dataset, and in order to compare, so this is our in the Japanese dataset there's a 40 times larger in the number of writers, and it means there's more writing style. Also, there's more the number of answer is larger, so that the context variation is maybe much larger, and the number of character also be larger. And now one of most important is there's no handwritten text label for this answer in the Japanese dataset. So that it's really difficult to employ any supervised learning method based on the deep neural network. So that we need to, in order to standardize the answer image for handwriting recognition, we employ the multiple step of pre-processing to extract the single characters from the image, and that after that to form a vertical text line. So first is the answer sheet will be we will employ the histogram projection in order to extract the answer block from the answer sheet, and then from this answer block we will employ the morphological operator in order to extract the character box and merge all of them into the vertical text line. So according to the data, so this pre-processing step is achieve the high accuracy, and only a small number of pattern has the heavy noise is caused by the route color by eraser. So only a small number of sample require the manual pre-processing. And from that standard data set, we manually prepare the labels for only 100 handwritten answers. So it's equivalent to only 0.05% of the whole data set. And we will use this 100 handwritten answer as a test set for our handwriting recognizer. So, but only 100 answer is not enough for training any large deep neural network. So we only train a very simple CNN model on using only 100 labeled answer here. And then we will employ that trained simple CNN model on the 1000 handwritten answer and manually verify the label predicted by our simple model. Then this 1000 handwritten answer will be used as the training set for the final handwriting recognizer. So here is some example that we have manually labeled the answer, and also in the below this is the example of some answer that contain the eraser route colors, and it might cause a problem in the recognition. So next is here is the automatic scoring framework using the deep neural network, and from the handwritten answer image, we will employ the pre-processing to extract the single character, as I said before, and this semantic character will be recognized by the ensemble model. And so inside this ensemble model, there's 5 different deep neural network. As here we employ the well-known structure, and the predicted character will be the sequence from E1, E2 to En, and we also added one special token E classes in order to require the model to predict the score of this answer. So this sequence will be the input for the transformer model. For the BERT model, it contains the L transformer layers, and the output of this transformer layer will be fed into the feed-forward softmax and give the prediction score. It will be the score of the answer. Then here is next I would like to show how we can evaluate the accuracy of automatic scoring system, because we do not have the the label for handwritten answer, so we only evaluate the score of we only evaluate the agreement between our automatic scoring system predicted score and the score evaluated by human. So here we use the quadratic weighted kappa or QWK to evaluate the degree of agreement. So according to the previous study, so this QWK value would be higher than 0.8 in order to achieve the almost perfect agreement, so that it would be used in the practice. And because when we use this QWK evaluation, it will eliminate the demand on the text labeling for evaluating the handwritten recognition. But so first I will show the result on the handwriting recognition. As here we only evaluate on the only 100 manual label answer. And first we show the shallowest model VGG16 and the deepest models of denseness. Then the result using the ensemble of all 5 models. So for both processing here, we use the 5-gram language model using Japanese Wikipedia. And the next 2 rows will be the result when we apply the fine-tune using 1,000 answers that have been verified. So by using the fine-tune, the using a dataset to fine-tune is improve the accuracy much higher. And the best model here is the model of the ensemble model, so that we employ the result from ensemble model for recognition for the automatic scoring. So
excuse me, please control your time. So you have 1 more minute to
okay.
present.
Yeah, it's okay. So this is the automatic scoring result here. We have 3 questions for each year. And as you can see that the question number 3 of each year is seem more difficult as the lower mean score. So that and this question also require a longer answer from students. So maybe it's more difficult than other question. And when we evaluate using our QWK value, we see that the degree of agreement is also higher than 0.8, as so that it's much higher and can be used in the practice. So for conclusion, we would like to conclude that 4 points. First is the ensemble deep neural network for offline Japanese handwriting answer. And the second is the training procedure with multiple steps. And the third one is the way to combine the handwriting recognizer and also automatic scoring. And the last one is the combined architecture, even without the correction of misrecognized character. And do not require any rubric annotation, we still can achieve the same level as a human examiner. So thank you so much for your attention.
So thank you for your presentation. So now we have 1 simple question. So any participant, if you have a question, just switch on your microphone.
I have a question, please.
Oh. Yeah, please.
Yes.
Yes, so I wanted to ask, since you're using a deep learning model to basically recognize answers, can it get biased to certain handwriting styles?
So do you mean that using this handwriting recognition, can we?
So for some students, for some students, it's giving them better grade compared to other students, like based on their handwriting styles?
I see. So actually here we do not have any text label for each handwritten answer. So we only evaluate on the whole data set based on the score provided by examiner. So might be some question has been recognized with our recognizer can have a mistake when recognize the answer, but when combined with the automatic scoring, it still provide a good prediction on the score for that answer. So I mean, from our experiment, so we found that even do not need the perfect 100% of accuracy, we still can employ our recognizer for automatic scoring.
Okay, thank you. Due to the limitation of time, so please let's stop here. And if you have more questions, so you may discuss in more details later.
Yes,
So now let me invite the presenter of the second author. So the second paper. So Alicia Forners, please share your screen. So the title of the second paper is Music Graph Optical Music Recognition Through Object Detection and Graph Neural Network. Okay, good. Please.
Do you see my screen?
Yes, it's fine.
Okay, so thanks for the presentation. I would like to present the work of Arnau Baró, a PhD student at the CBC, working on optical music recognition, done in collaboration with Pau and myself. And the idea in this paper was to use graphs for optical music recognition. So let me just, this will be the outline of the presentation. We will explain OMR, the dataset, then we will go for the architecture and the results. So why we care about music scores? There are many handwritten music scores in archives, and especially for sacred music, religious music in churches. And there are many that are still just there waiting for being transcribed, edited, so that people can listen and know about this. So we have still musical cultural heritage just waiting there for being, uncovered. And the problem is that there are many, so a manual transcription is too much work. So that's why we have the idea of using optical music recognition. This is just like OCRs or HDR, handwriting recognition, for music scores. So in this case, the transcription is just taking the music notes and then creating this output file, which usually is MEI or music XML or MIDI, so that we can edit this with music editors. Like in Word, we could have this for text so that we can later edit or even listen. Typically, optical music recognition has been recognized using the classical techniques, but then later with the appearance of deep learning, there were many methods that were somehow inspired from HDR. For example, here we have an example with LSTMs, with CNNs and LSTMs. And then also there were some others on sequence-to-sequence models that are also used for text recognition. But if we think in the nature of music symbols, we can see that there are some differences with text. First, we see that there are many repetitive rhythms. In this case, we have a quarter note in different positions. So we have this 2D information. And in some other cases, we have the same note, but with different rhythms. So we see that there are two components here. And then in addition, we also see that music scores, the symbols are decomposed into primitives. So here we have in different colors, the different primitives. In some cases, this is an isolated symbol, like a sharp, or in some others, like a beam. It's part of a composed symbol, a composed music group of notes. So why not exploring the representation of graphs? Because with a graph, we could create the different nodes, and with the different edges, we could relate the different primitives. So for example, in here, we see how we could represent a group of nodes with the different node heads and the different edges that are linking the different parts of the music symbol. And from this, we could explore this. The problem with deep learning, and the same with graph neural networks, is that we need a lot of data. And due to this, we created 18,000 measures, bar units, like this one, and then we labeled all the different elements. So it's in COCO format for object detection, because we will later use object detection, and also we also have the position and the pitch for each one of the nodes. In the end, we have the XML. So the architecture is the following. We have in here the input image, and we use an object detection network, like a faster RCNN, for detecting the different parts. But for the case of the training, we directly take the bounding boxes in the ground truth for the graph neural network, that this will come later. And for creating this, there are two different options. KNN means that the different primitives are related to each other if they are close enough. So this is just a measure of the distance. The other option is that we go for some music heuristic that comes from music notation, which means that there are some primitives that are related to each other's, and in some other cases it makes no sense. For example, this primitive, this is a rest, so it's not related to anything else, so it makes no sense to link this to any other nodes. And in this case, we have a node head, which usually is linked to a beam or a flag. So that's why we create these edges. So as I said, we have two options. The option of linking everything, so creating edges between primitives if they are close enough, or the other option is only linking those that make sense. So for the first idea, what we have is that with the faster RCNN, we have the different candidates. These will be the different primitives that later will be nodes in the graph. And then in this case, we will have later the trained GNN. But there is a problem when we have the testing music score. So this is the one that goes for the object detector, and is that there are many detections. So we have a soft non-maximal suppression, and I would like to talk about this post-processing, because these are the results that we had for the different primitives in the case of the object detection. But we saw that in the case of beam, which is this red part here, or the stem, which is this blue part in here, the detection, since these are very thin elements in horizontal or in vertical way, the recognizer, the detector, sometimes misses them. So that's why we combine these results with the post-processing, which is using some morphological operations, very classical techniques, so that we can detect these thin horizontal and vertical lines. And that's why we can improve the detection a bit. Because if we don't detect the nodes, then later it's very difficult to create a node. An edge is easier, but a node is necessary in this case. So it's important not to forget any primitive, because they will be the nodes. So in here we have some qualitative results. For example, in here we see that in this case we detected one beam, but with the post-processing we can detect the second beam in here. Or in here we have the problem of a stem that it's missed. So in some cases we can recover this, and in some cases we still don't recover this. For the rest, I think that it's quite straightforward. The detector is doing quite a good job. So as I said, we have for the test music score, we have the detector. We apply the soft non-maximal suppression, which is a softer version of the non-maximal suppression, because in there what we have is that we remove those with overlapping and lower confidence. In here we don't remove, we just decrease the confidence. And then we have the trained GNN, which is finally the one that from the different primitives it gets, which is the final symbol. So in here, just remember that we have the different primitives, and the output of the trained GNN, the graph neural network, is this directly the symbols. So all the primitives in here are close together so that we create an eighth node, for example. And concerning the results of the recognition, we have these ones. So if we apply the KNN, the symbol error rate is close to 10%. If we apply the music heuristic, which means that we have much less edges to analyze, then we get a 5%. And this is the overall architecture. For the training, we are training the detector in here, and for the training, we directly take the ground truth for the primitives, but anyway, we train the GNN. So in both cases, we reach this part, which is the final result. In here, what we have are different examples of the qualitative results comparing the music heuristic and the KNN. In this case, we see that there are much less edges, but it's normal that in some cases we miss an edge. And in this case, the problem is important in the sense that the note changes. So instead of an eighth note, since we have missed the relation with this flag, this becomes a quarter note. This is not happening with KNN when we have much less edges to analyze. And in here we have another example in which the music heuristic is nice, but in here we have many, many edges, and it can happen that some of them are so low in the end that we have exactly the same problem as before, that in here, due to the extra amount of edges, it can happen that the graph neural network misses some of them. And then in here, what we have is that, for example, in this one, it misses the beam, it closes the beam before, and then that's why we have the quarter note. So there is no perfect solution. So as a conclusions, we have seen that the results are very promising. So graph neural networks are nice in the sense that we have the 2D representation of the primitives, and then we have all the neural network, the graph neural network for the inference. The object detection is very critical, but anyway, we have seen that the results can be fine. And the total error rate, it's close to 5%. So as a future work, of course, this was just the experiment on evaluating how far we can go with graph neural networks for music scores. And now, of course, the next step is to go towards handwritten ones, and then later the old ones, which was our goal. And in here, one of the first works that we would like to see is if we can use, we know that the data is not that big, but we would like to use the Mustima++ annotation and trying to see if there is some kind of transfer learning that we can do from one to the other. And that's it. Thank you very much for the attention.
Okay, thank you. Any question? So we can have one question. So let me take the advantage to ask a question. So it seems that the graph neural network can improve the recognition accuracy of music recognition. My question is, it looks that you are still processing the music document line by line, right? So I suggest that if you use GNN, it's possible to process all of the lines together without line segmentation. Would that be useful?
Yeah, right now in this first experiment, you see that we are taking just one bar measure to see if the graph neural network is able to go from the primitives to the but of course, I think that later, whenever we see that this is stable, and then we can decide that there are too many, and then we have some other rule for creating the edges. I think that the next step would be to go directly applying to the full page, and I think that this is the next steps together with the handwriting recognition part, because I think that this is printed, so this is quite nice. But then whenever we go to handwriting, things will be different. But yes, we agree.
Oh, okay. Thank you. So the time is up. So let's stop here. Thank you again for your presentation. So let's move on to the third paper. So the presenter of the third paper is Zhang Zhang. Please share your screen. So the title of the third paper is combining CNN and transformer as encoder to improve end-to-end handwritten mathematical expression recognition accuracy. So
Okay.
now
Could you hear me?
yes, I can see your slide, but yeah, okay, it's fine.
Okay.
So please start.
Okay. I'm sorry that I have some trouble with my camera, so I'm afraid that I can't present in face. But okay, thanks for your introduction and good afternoon, everyone. I'm Zhang, and I'm particularly honored to be invited to speak here. So today I would like to present about our paper combining CNN and transformer as encoder to improve end-to-end handwriting mathematical expression recognition accuracy. And I would like to divide my talk into 4 parts. So the introduction, methodology, experiment, and conclusion. So first, let me introduce you about our topic. Our task is to modify the structure of the model to achieve better accuracy and efficiency in HMER, which is handwriting mathematical expression recognition. And HMER has played an important role to improve efficiency for academic work by converting handwritten text into LaTeX text that can be compiled by computers. But however, there are 2 main challenges compared with traditional OCR. That the first is the high requirements for the recognition accuracy of symbol size and position, and also the needs to identify the spatial position relationship between symbols. However, we're inspired by some works that have been done. So first of all, the attention-based encoder-decoder model has become the main solution structure for HMER after the success of the WAT model, which is watch, attend, parse model. And meanwhile, transformer is succeed for its unique framework and surprisingly good result in natural language processing and computer vision area. So since the CNN model is hard to obtain global information, but good at aggregate local information, and transformer-based models are inherently capable of accessing global information. So we consider of combining CNN and transformer. And we're also inspired by some work that have already been done, like botnet and codenet and conformers. So therefore, we developed 3 combinations of CNN and transformer encoder under the attention-based encoder-decoder model, and we test its efficiency. It has 3 combinations that include the tandem approach, parallel approach, and mixing approach. So the first part is our baseline design. So we developed our baseline based on BTTR model, as shown in the reference here. In this structure, we replaced the traditional RNN decoder with the transformer decoder in the AED framework, and we improved the conciseness. In the CNN encoder part, we use DenseNet to extract features and to optimize the gradient transfer process. So we also add 2D absolute precisional encoding to help the transformer decoder better identify the image feature vector locations. So in the decoder part, we replace the value with the glue in the feed-forward net, which is performed better on transformer model. And we also changed the post-norm normalization to pre-layer norm. Since post-norm is very sensitive to initial parameter values, it would take a lot of time to adjust learning parameters. And the structure of the pre-layer norm omits warm-up initial training and further saves time. Okay, so next, in our tandem approach design, we further change the structure of the encoder part of the baseline model by adding the transformer encoder and make it connect with the original CNN encoder in tandem, as shown in the figure 2. So the output of the CNN encoder is taken at the input of the transform encoder. So through this process, we hope the final output can capture more global contextual information to improve the accuracy. We also want to examine the combination in parallel structure So we designed the parallel approach. First, the feature extracted from the original image data are operated by two encoders at the same time. And then the two feature sequences are concatenated to generate the final feature sequence by a linear mapping layer. And for the transformer branch, we first patchify the input image into a sequence of 16 times 16 patches, as the Vision transformer does. And then we feed this sequence into a linear embedding layer to generate the input sequence of the transformer encoder. And also the number of layers, the number of transformer encoder layers can be verified. So our last structure is the mixing approach. We are inspired by the botnet, though similarly, we designed the dense self-attention net, which is different from the dense net by replacing the 3x3 convolutional kernel in the last stage of the dense net by the multi-head self-attention. And also we changed the ReLU to the GLU and the batch norm to the instant norm. Okay, so next step, let me introduce our experiment process. So for the dataset, we selected the CROM, which is the competition on recognition of online handwritten mathematical expressions dataset for training and testing. So we selected CROM 2014, 2016, and 2019 dataset as the test set, and 2014 dataset as the validation set. The experiment recognition rate, which is this EXP rate, is received from the result from official evaluation tool. So our experiment results are listed on the PowerPoint now. We'll list the result of both the state-of-art, some state-of-art, and traditional models, and also with our models. So you can see that the tandem approach of our model performs best overall in the three datasets, and it has achieved the experiment recognition rate of 58.56 on CROM 2019. Okay, so in the experiment, we have also tested the effect of the number of transformer encoder layers in tandem and parallel structures. So in tandem approach, you can see that we tried 4, 8, 12, and 16 layers separately. So each layer is the multi-head self-attention with 256 output neurons, including a feed-forward with 1024 neurons. And increasing the number of layers in the tandem approach to around 12 increases the model's performance, but too many layers burdens the model to be too complex, so the efficiency falls back. And we applied the same setting as in the tandem approach. So in the parallel structure, the number of layers of 8 performs the best in all data sets. Well, differently, in the mixing approach, we examine the number of attention head of 1, 2, 4, 6, 8, and 12 separately, and we ran the test while keeping the final output dimension fixed at 192. So the best validation recognition rate was achieved with the 8 head attention head on CROM 2016 and 19 test set, and reached the peak value of the recognition rate. So compared with the single head model, the 8 head model improved the recognition rate by 2.18% and also 1% on the two data sets separately. So in conclusion, our paper introduced 3 combination of the CNN transformer, which is tandem approach, parallel approach, and also the mixing approach. And we received the result that the overall tandem approach performed the best, and also we tested and examined the effect of the numbers of transformer encoder layers and also the number of the attention heads to the recognition rate. And for our future work part, as we know that transformer model needs a large data set to train the model, but actually we didn't include the data augmentation in our paper. So in the future, we could apply larger data set to train the transformer model in order to receive better performance. And also we could research on the root cause of the influence of different layers and head numbers, attention head numbers on the model to improve our work. Okay, thanks for your attention, and that's all.
Thank you for your presentation. So any question from our attendees? Please just switch on your microphone and raise your question.
I would like to ask a question, please.
Okay.
Please.
Yes. Does your model work in an autoregressive fashion?
Excuse me. Your voice not really clear.
Sorry, am I audible?
Okay. Okay.
Yeah.
Here.
Does your model work in an autoregressive fashion?
Yes. Yes.
So
working.
this leads to my next question, that this will incorporate a language modeling in itself, right? So
yeah.
So does like a language like math, does it really need a language model, or like can you compensate with the CPC loss as well? Just an idea.
Exactly. I believe that it would. Yes, I believe that it would compensate for that. And actually, I think in our models, we have sacrificed some of the during some of the process to sacrifice the accuracy, because there's still some problems that we can't like deal in our models. So yes, it could be a possibility.
Thank you.
Okay.
So regarding language model, I thought that your model does not use a language model, but it's possible to combine with a language model in inference stage, for example.
Yeah.
Yeah. So any other question? Okay, so we can stop here. Thank you again.
Okay.
Thanks. Yeah, please exit your sharing. So let me invite the author of the fourth paper to, so Lin, please share your screen. And the title of the fourth paper is a Spatial Attention and the Syntax Rule Enhanced Tree Decoder for Offline Handwritten Mathematical Expression Recognition.
Okay.
Yeah, okay.
Can you see my
Yes.
screen? Okay. Yes.
Yes.
Hello, I'm Zhao Li from South China University of Technology. And our work is about the tree decoder for offline handwriting mathematical expression recognition. And I will talk about the handwriting and mathematical expression recognition and our method and the experiment detail. And firstly, handwriting mathematical expression recognition consists of online and offline recognition. And for the recognition solutions, recent end-to-end method deal with it by string decoder and tree decoder. In the string decoder-based methods take the programs as an image to sequence text, emphasizing expression symbols awareness. And the tree decoder-based method as a name show regard the expression as a tree structure, which emphasize the spatial structure of expression. And as we all know, unlike printed expression recognition, HNDR faces the challenge of ambiguity of handwritten symbols. And on the other hand, unlike general text recognition, expression has complexity of two-dimension spatial structure and more interference, backward similar symbols, and so on hinder the progress hinder the performance of HMER. And some studies have emphasized on expression recognition since 2017. WAP is proposed in these fields and improved through GRUs with the coverage attention to parse the expression symbols sequence, which inspired most of end-to-end work after that in recent years. And research based on tree decoder was emerging in the field of HMER. The tree structure represent the expression more naturally, and bring a normal approach to deal with HMER. And as we see, in tree decoder based method, expression can represent not only latex string but also subtree structure triples and simple tree structure. Specifically, the subtree structure triples consist of child node, parent node, and their relations, in which the node presents the expression symbols and its connected symbol is represents parent node. And in the other hand, we use word error rate and expression rate as our metric, our method metric. And next one, I will introduce our method. The contributions of our work are about we first introduce spatial attention enhancement to predict node information, improving the structure accuracy. And we employ syntax maps to constrain the generation of ungrammatical mathematical expression. The overview of the model architecture is above, where we employ the DenseNet as our encoder and take the model's output subtree structure and then transform it to the tree structure. The decoder of our method consists of three parts. The child node prediction model to predict the current node information, and the parent node prediction model to predict the parent node from previous child node, and the relation prediction model to predict the relation between parents and child nodes. And at the child node prediction model, we inspired the previous work and improved true decoder with GRUs and attention blocks to pass the child node and parent node respectively. At the parents prediction model, at the parents prediction model, we treat predicting the parents node as finding previous child node which has best match with current child node. And we in this part, however, only using semantic information to predict the parent node may lead to inevitable errors, especially when we face the identical symbols in one expression. Thus, we introduce spatial attention mechanism to evaluate the prediction errors of parent node, in which the model could combine the spatial information to predict the node. And there will be a verification experiment, and we can find that the model can predict the parent node more correctly. As the visualization show, we can find that as the simple minus is the child node, and as minus is the child node, and its parent node should be the simple n and not the simple one. And at the time, spatial attention can locate the simple n according to the spatial structure, helping the model to output the correct node and information. And on the other hand, we find that we found that the model sometimes output the errors expression which is ungrammatical, and like the simple A should be the subscript with the simple N. And since that, we summary and introduce two syntax rules into the relation prediction model to regulate the output expression grammar. The stated rules is that different mathematical symbols have different restriction of connection relations. The dynamic rules is that each mathematical symbol cannot have repeated connection relations at the same time. And we put forward the marks representing the syntax rules in the relation prediction model. If the mathematical symbols can be reconnected to its related symbols, the corresponding syntax marks varies 1 and other L0. And now here the table is represent the table represents the latest syntax marks, and finally we define the loss function as above, like the loss of child node prediction and the parents node and relation prediction. And we define attention self-regularization loss using the KL divergence to speed up the network convergence. And we conduct the experiment on Chrome's dataset, which are also the benchmark on HMER. And here is some samples of Chrome dataset. Yeah. And okay, as before the experiment, we first simplify the parameter of dense dwarf PD method, which is also the treaty code-based method on 2020, and it's the baseline of our method. And we find that the inference speed increased by more than 50 milliseconds without affecting the recognition performance. So because our method for the dense dwarf PDF methods using two GRUs with attention to pass the symbols, we also use the simplified parameter settings in our method. And to verify the performance improvements, we conduct operation experiment on Chrome 2014. As shown in table, we can find that the improved performance as we introduce spatial attention and syntax rule, and specifically the gap between expression rate, the tree of expression rate and the flattest expression rate becomes smaller after we introduce the syntax marks. And here is the performance comparison of with the other method. As the table shows, about our method is near 3 points higher than dense dwarf PD on Chrome dataset. And the last is the conclusion. We propose a new tree code model integrating spatial attention and syntax rules. Not only improve the structure prediction accuracy, but also decrease the appearance grammar error of mathematical expression. We illustrated the great performance of our methods for applied HMER through some experiments and on Chrome dataset. And now here's my presentation is over. That's all. Thanks for your listening.
Okay, thank you for your presentation. So, any question from our attendees? So, it looks that from your experiments, that using our syntax rules, so which are represented as syntax masks, can improve the accuracy. But similarly, use a language model can also may produce similar effects. So do you think if you combine language model in influence of the expression recognition, would that be helpful to further improve the accuracy? That means the language model to be complementary. Yeah.
Well, we have never thought this trick without our method, and I think it's a great idea to use language model and to improve our method, and I will in future I will put it into my method in to improve the performance and
okay. Okay, thank you. So any other question? Okay, so maybe we can stop here. Thank you again. So please exit your sharing. So let me thank all the presenters so far, and now let me move on the chair to Dr. Joy Monda to chair the next 4 papers, please.
Yes, thanks to Professor Liu for chairing this session. Thank you, Professor Liu, for chairing the first 4 papers for this session. So next paper is FRNet end-to-end full-page recognition model for handwritten Chinese essay, presented by T. Su. Please, Su, please share your screen.
Okay, can you hear me?
Yes, I can hear you. Yes, we can hear you. Please share your screen.
Can you see?
Yes, we can see you.
Okay. Thanks for the chair. Thanks for all the attendancy. I'm Tonghua Su from Harbin Institute of Technology. This work is entitled with FPRNet, end-to-end full-page recognition model. It's for handwritten Chinese essay. It's co-worked with my student Hong Mingyu, Shuchen Liu, and my colleague Zhongjie Wang. Let's see the contents. Firstly, I introduce the background of the work, then describes the architecture of my model, and thirdly, I give the experiments, and finally give the conclusion remarks. Let's see the introduction. As we see, the handwritten Chinese character recognition plays a very important role. It is to transcribe handwritten Chinese text images into a machine encoded form or editable form. So it has a long research history in the pattern recognition and document analysis history. Also, it is widely used in office automation, forms automation, and AI-assisted education recently. So our research is heavily related to the AI-assisted education system. Here's a real-world scenario. The essay recognition and scoring is very commonly used in the essay scoring applications, especially to the kids. Here we can see the samples from the real world scenario is very complex. For example, we can see there's some miswriting, some correcting from the teacher. Also, there's some distortion during the scanning, and also we can see the background, the cells is not consistent, and also each person has his own personality during the writing. Also, there are some correction marks in the paper. So how to do such challenges? We have surveyed some related works, especially falling to the segmentation-free strategy. One is the ReadingMap.net. It proposed 2 years ago. We can see it employs bilinear interpolation operations and the convolutional layers to handle the mapping from 2-dimensional to 1-dimensional string. So it can transform the multi-line feature map into a single line features. So it handles a full page recognition task. Also, the Spain proposed 1 year ago. We can see from the architecture, it employs a FCN encoder. Then features is operated by the convolutional layers, and also especially with the reshape operation. It is different from the mentioned bilinear interpolation operation. So this operation can pretend the information with a little loss during the transformation. So we will follow such a strategy. Also, that has an enhanced version. It is based on a vertical attention network. By this way, we can see we can employ 2 different loss. For example, the CTC loss and the cross entropy loss. In this way, they have a very good performance. Based on such inspirations, we proposed our architecture. This architecture is encoder-decoder structure generally, and we have combined several new ideas. Firstly, we have a depth-wise separation convolution and gate block. Also, we have employ a multi-branch structure to considering the information, the features at different scales. And also, we proposed order line strategy to handle the confusion during the skewness of the samples or images. So as for the encoder, we can see one of the parts is DS gate. DS gate uses a kind of depth-wise separation convolution and 1+1 convolution. In this way, we can have a very compact computation. It is very blue in the computation cost. And the second is in subgate. It is combined with the residue block, and also we have a reception model, reception block combined. It can considering the features in more details. Then we can see we have a gate block. It can merge the tenting edge and sigmoid activation functions simultaneously. Okay, let's see the decoder. Here you can see we have a CDC loss to to considering the segmentation-free features. Also, we can decode the high-level features. During the decoding, we have also employ a reshaped dimension reduction method. So the features are arranged instead of the interpretation, because interpretation may lose some information during the transformation operations. Specifically, we have proposed the order align strategy. It is to handle the problem during the decoding. We have found that the standard decoding process may have some, we can see from the suffix C, we have some duplicate mapping errors. Also, that may be incorrectly mapped to adjacent token, adjacent lines. So if the input image have skewness, there may be many confusions, especially during the adjacent lines. So I want to handle this problem. Here's the all-align strategy or axiom. Here you can see we can move the duplicate and black characters that is introduced by the standard decoding process. Also, that will contain or keep their orders in the image level. So they have a string level and the image level correspondence. So in this way, we can improve the sequence orderliness that will be work in order. Finally, we can say something about the experiments. Firstly, is the dataset. We have collected in-house samples. It is written by the kids or genuine students. So this kind of image is called essay image. It has been collected from different provinces in China. For example, Heilongjiang, Jilin, Hebei, and Jiangsu. They totally have 2,000 samples. Here is the setup. We have adopted 3 metrics. Here are listed 2 of them. One is the character error rate and the blue. The blue is to reflect the string fluency of the sentences. So it's high is better. Here we list some results to give some illustrations. Here we have 2 kind of experiments. One is the paragraph level, and the other is the full page level. From the paragraph level, we can see that we have a better result no matter in the CI or the blue. Also have little or shorter parameters. As for the full page level experiments, we can see that our method works better even without the order line. But if we enhanced with order line, there will be at least 1 point improvement in the performance. And also the blue have much increase. Also, we have compared with traditionally segmentation-based method that is worked as Tencent Cloud API. We can see that we just used very limited training data. We have higher result, higher performance. Okay. Here I'll give some illustration of the realization. The subfigure B is the baseline from the Rigimami network. So we can see from the figure that our models works more concisely. We can see the mapping of the character in the image that have very compact reception field. So it seems better to the original net. Okay, we have the conclusions. Here I proposed an end-to-end model for full-page handwritten recognition. It's applied to the Chinese essay image to entitled with PRNet. It is encoder-decoder structure, and the encoder can learn the special pattern at different skills, and that has little results during the transformation from two-dimensional to one-dimensional. And as for the decoder, it has a more enhanced alignment effect. We have the order pretty effect. So it guarantees the sequence with more order preserved during the inference stage. So that's all. Okay, can you hear me?
Any questions from audience or online? I have one question, because one paragraph contains multiple lines. So how do you send to decoder the full paragraph to the decoder part? That means the recognition part. Because if you send the whole paragraph to the decoder, I think it lost the contextual information because of it contains multiple lines.
Okay. So your question about the full page, how to contain this special node relationship, is that right?
Yes, yes. How do you preserve the your contextual information between the words or lines in a paragraph?
Okay. It is fully depending on the convolution layer to extract the features. So the feature during the first stage of the several earlier stages, it can extract the features in two-dimensional but during the later stages, we have the transformation from two to one-dimensional. For example, the reshape operation or the interpolation transformation. It will convert the two-dimensional feature to the one-dimensional. It is concat all the two-dimensional one by one lines to just one bigger lines, so it can be learned the whole process. So the full page recognition can works. Okay.
Thank you. Thank you. Thank you.
Thank you very much.
The next paper is UO HTD Urdu Offline Handwritten Text Datashet by Aftab Rafiq. Please share your screen. Aftab, are you there? Okay, then we can move to the next paper. Finger touch detection feature using frequency distribution in writer verification based on finger writing of a sample symbol, presented by Izao Nakanishi. Please share your screen.
Okay, can you see my presentation?
Yes, we can see. Please start.
Thank you for your kind introduction. My name is Isao Nakanishi from Tottori University. Tottori University, Japan. So we have proposed writer verification based on finger writing of a simple symbol. This method focus on usability than security. So a user writes a simple symbol, for example, circle, cross, square, a triangle, that everyone knows and never forget using a finger on the smartphone screen. And user is verified whether she is genuine or not. As conventional individual features, we used finger pressure and finger touching area, but we did not use finger touching direction, which is introduced such as in this paper. So it is important that these are invisible and difficult to imitate. So they become countermeasures for spoofing. Finger touching direction is detectable in some smartphones. An ellipse is fitted to the finger touching area. On the screen of the finger touching area. This is an example of finger touching direction data. However, positive values were changed to negative values at 2 successive points. However, it is unlikely that such a rapid change in the finger direction occurs on the smartphone screen when writing a simple symbol. So they may degrade the verification performance. So I think one cause of the rapid change is that if the long axis on an ellipse fitted around minus pi over 2, like this, is slightly changed to this by fingertip movement, but direction is supposed to be around pi over 2 radian. So significantly changed from minus pi over 2 to pi over 2 radian. So for prevent such a rapid change, we introduce the pre-processing. If the absolute difference between two successive direction data is larger than pi over 2, detected direction is inverted. So this is after processing data. So you can see the rapid change is improved. So in order to examine the effect of pre-processing, we evaluated the verification performance using these conditions. The number of subjects was 10, and they wrote circle, triangle, and square 10 times. And verification method was Euclidean distance matching. And among 10 data, 5 was used for making a template, and the rest 5 were for testing. So finger touching direction data direction varies over time. So we defined features as follows. For example, a mean of directions and the direction at the start point as follows, etc. So this is the error rate for verification before introducing processing and after introducing pre-processing. Error rate were reduced by introducing pre-processing. So the effect of introducing pre-processing was confirmed. Next, the introduced finger touching direction feature is one-dimensional. So the smaller number of feature dimensions is not effective for pattern matching. So we propose to multi-dimensionalize the direction feature. However, to directly use finger touching direction data like this in pattern matching makes the direction feature dependent on the written shape. So we introduce a frequency distribution in the direction feature. The frequency distribution of finger touching direction is calculated, and then distribution is represented as a histogram like this, where the total frequency is normalized to 1, since each histogram has a different total frequency. This is an example of a histogram of finger touching direction data. So using that histogram, template was obtained by ensemble averaging the histograms of 5 finger touching direction data. And verification was performed Euclidean distance matching using the template. Result error rates for each symbol. Comparing error rates in the one-dimensional case, error rates were reduced. So the effect of multi-dimensionalization was confirmed. So let me conclude my remarks. We have proposed light verification based on finger writing of a simple. So in this study, we introduce finger touching direction feature, and also introduce multidimensionalization based on frequency distribution. So we obtained error rate of about 22% to 25%. To use the proposed feature with conventional ones is our future work. So that's all. Thank you for your listening.
Thank you. Thanks to the Naganesi for his presentation. Any questions? No questions. Thank you for your presentation.
Thank you.
Next paper is Urdu handwritten ligature generation using generative adversarial network, presented by Mariam Sarif. Please share your screen.
Yes, is my screen visible?
Yes. You can
start. Okay. Hello, everyone. My name is Mariam Sharif, and I'm a master's student at National University of Science and Technology in Pakistan. And today I will be presenting the paper titled Urdu Handwritten Ligature Generation Using Generative Adversarial Networks. The authors of this paper are myself, Nanul Hassan, and Faisal Shafai. We will first start off with a brief introduction. So basically, Urdu belongs to a family of complex script. Most of the words are made up of one or more ligatures, and each ligature is then made of a combination of two or more letters. The shape of a single character in the Urdu language changes in accordance with its position in a word. The complex nature of Urdu hinders it to have state-of-the-art performance for handwriting recognizers. A large database encapsulating all the fine details present in the script is thus required. As data gathering is a challenging and costly task, augmentation techniques are implemented to achieve dataset expansion. Generative adversarial networks is one such deep learning-based solution that allows the generation of new realistic and authentic-looking data samples. As stated, the complex nature of Urdu language poses significant challenges to achieve state-of-the-art performance for handwriting recognizers. Thus, for it to be made possible, a large enough database that has numerous data samples that engages all the different traits of the Urdu language is required. In this paper, we explore for a way to achieve an expanded dataset with diverse samples using an already available small Urdu ligature dataset. First, we will focus on a few research works done for handwriting generation based on GAN architecture. The first work presented is focused on the generation of Urdu ligatures. The UNHD dataset consists of Urdu lines that are passed through the pre-processing steps of binarization, segmentation, and then resizing. 317 unique ligatures are obtained using this scheme. They have implemented 7 different GAN architectures where they have claimed that cycle GAN gives them the best qualitative results. Unfortunately, no quantitative results were given. Their work involved training a single architecture to produce a single ligature at a time rather than a single architecture producing all the ligatures at once. The second work referenced here is the work presented by Alonso et al. They have used GANs to produce French and Arabic words. The generator and discriminator are made up of consecutive rest blocks. In addition to the traditional GAN paradigm, they have also used a text recognizer as an auxiliary network in their work. Comparing the generated French and Arabic samples, we observed that some French samples do not exhibit any cursive characteristics, whereas the same is not the case for Arabic samples where ligatures are cursive in nature. The generator thus faces some confusion, and the Arabic samples are thus a little bit lacking in quality as compared to the French samples. The last work mentioned here is the state-of-the-art handwriting generator named ScrabbleGAN. Key feature is its capability to produce cursive handwriting. The generator and discriminator architectures are fully convolutional. Their work follows the concept that handwriting is a local process and each character is only influenced by the character before and after it. A text recognizer is also used as an auxiliary network in their work. Now we draw a simple comparison between these three words. The first work is capable of producing Urdu ligature samples, but no single GAN is capable of producing all the ligatures at once. The second work is successful in expanding an Arabic dataset. However, it fails to take into consideration the difference in the interword and interword spacing for the Arabic script. The third work is capable of producing cursive handwriting. However, it was only implemented for languages making use of the Latin script. Now we look at our proposed approach for generation of Urdu handwritten ligatures. For employing the GAN paradigm for Urdu generation, a few certain things need to be kept in mind. For one, the model architecture should be capable of producing cursive handwriting. As seen from the verse before, this can easily be achieved with the help of fully convolutional networks in the generator and the discriminator. Secondly, we want to be able to control the type or basically the ligatures that are being produced. For that, a large number of class condition GAN variants are also available. So keeping the previous points in mind, the proposed networks makes use of a fully convolutional generator. This causes the generator to have the ability to produce cursive handwriting. The generator can be seen as a concatenation of identical and class condition generators. A filter is chosen for each character in the generator. In the ligature, the corresponding filters are concatenated and then multiplied with the latent vector noise Z and passed on to the convolutional layers of the generator. Due to the overlapping feature of the receptive fields in the generator network, the influence on neighboring characters is also taken into account, which helps create smooth transitions between the different characters. The discriminator is also a fully convolutional network, but it has a completely opposite architecture as compared to the generator. To further clarify our proposed framework, we consider this example. Here, a 4-character ligature is shown. So 4 corresponding filters are produced by the filter bank, and then they are concatenated and multiplied by the latent vector noise Z. This is then passed on to the generator, which produces a ligature sample. These samples, along with the real samples, are passed on to the discriminator, which try to score if the samples it received are either real or fake. The score of the discriminator is then basically used for updating the model parameters of both the discriminator and the generator. So for this paper, the ligature dataset has been contributed by Faruqi et al., where they have successfully extracted 317 unique ligatures. Most of the ligatures are made up of 2 and 3 characters. Standalone characters are also considered as 1-character ligature. The generator architecture is made up of convolutional layers followed by upsampling layers. Leaky ReLU and path normalization are also used in conjunction. And the generator produces ligature samples of a fixed size of 64 into 64. 3 different GAN variants have been employed, namely the deep convolutional GAN, Wasserstein GAN, and Wasserstein GAN with gradient penalty. Now we look towards evaluating our proposed net architectures both qualitatively and quantitatively. For the qualitative analysis, we consider the quality of samples generated by the 3 GAN variants. Here, row A represents the original data samples. Row B, C, and D represent the samples obtained from DC GAN, WGAN, and WGAN GP respectively. Upon observation, we can see that the samples from DC GAN are adequate, showcasing diversity and refined quality. However, due to the added constraint in the loss functions of the WGAN and WGAN GP, Their samples are much more refined, and minuscule details such as the dots and the slashes that are present above and below the ligatures are better portrayed in their samples. For further validating the quality of our samples, we compare our results with two other works. The first work that we consider is Faruqi et al. Here, the rows from these subfigures from row A to G represent the samples generated from their 7 different GAN variants, and the highlighted row H represent the sample generated from our work. As it can be clearly seen, our samples are much more resolute and have lesser noisy pixels. Another work that we compare our work to is Alonso et al., where they have successfully generated Arabic words. Upon comparison, we can observe that the details are picked up by their network. However, the edges of their samples are a little bit blurred, whereas our sample have much more clear edges and are much more concrete. For the quantitative analysis, we have chosen 2 evaluation indicators, namely the Frechet inception distance and geometric score. For both of these indicators, lower value is better. Since no prior evaluation results were present, we calculate the score for our 3 GAN variants and compare their results. In agreement with the qualitative analysis, WGAN-GP gives the lowest score, meaning that it produces the most authentic looking samples. For further validating the generated samples quantitatively, we expand the original dataset with the scan samples generated from the WGAN-GP variant. An additional 50 samples are created for each ligature class. We train and test our recognizer network on the original and the expanded dataset. An improvement in the character error rate can be seen, which validates the authenticity of our generated samples. There are some key points to take away from this research. First of all, Urdu alphabets, like English alphabets, have varying weights, and so does the ligatures. Some ligatures formed mostly from 6 or more than 6 characters might result in cramped ligatures due to the initial pre-processing step. This can be seen in the subfigure B in the top row. The proposed method fails to fully learn to distinguish between the details in such ligatures, as can be seen in the subfigure C of the top row, which is the sample generated from our generator model. Another thing to consider is that the shape of the Urdu alphabet changes depending upon its position in a ligature. As we see the second row, a single character graph is shown to adopt different shapes. Thus, when we give character sequences not present in the dataset to the generator, we get arbitrary shapes as output. A dataset containing all the forms for all the characters should be used for future training of Urdu generators. We finally conclude our paper. In this paper, GAN architectures were implemented for generation of Urdu handwritten ligature samples using a small ligature dataset. Due to the convolutional nature of the generator, smooth cursive handwriting was made possible, and successful generation of ligatures was achieved. Out of the 3 variants, WGAN-GP produced the most authentic samples, which were then implemented for the expansion of the dataset. Improvement in the performance was observed. Improvement in the performance of a text recognizer was observed due to the expanded dataset. Thank you. And any questions?
Let's thank to Sarif for her presentation. Any questions from online or offline? I have a question. How do you measure your quality of generated image?
For that, I have used 2 evaluation indicators, the FID score and GS score. But since this is, I think, the first work done for the generation of Urdu samples, so I didn't have any other results that I could compare it to. So I did a comparison between the generated samples of my own 3 invariants.
Any other questions? Okay, thank you for your.
So good morning, good afternoon, and good evening, ladies and gentlemen. I am Numandras, and I'll be presenting our paper, Transformer Architecture for Unconstrained Offline Urdu Handwriting Recognition. This is a joint work with Hazik Arbab, Aruba Maqsood, Khuzaima Nasser, Dr. Adnan Al-Hassan, and Dr. Shafat. So this will be the outline of the presentation. I'll be starting from the introduction and problem statement towards the application literature review, all the way towards the conclusion and future directions of our work. So with the introduction, the idea is that given a Urdu handwritten text image, we have to pass it through some system that could digitize it. By digitization, I would mean that to somehow convert it into some editable text. The problem with recent attempts in OCR's system towards the Urdu handwriting recognition is that either they rely on heavy pre-training or they lack an efficient language model. So we propose a deep learning model in order to overcome these deficiencies. Some of the applications of Urdu handwriting recognition include the digitization of books and scripts, postal mail sorting, bank check processing, preservation of history and heritage, national ID number recognition system, digitization in health and academic institutes. Before moving on to the proposed methodology, I would like to briefly discuss about the attempts made in this domain. So the first attempt that was given to Urdu handwriting recognition was the By-Long short-term memory network model architecture. The authors proposed this model, which takes an input image, they pass it through some pre-processing layer, then comes the convolution layers that extract some relevant features. These features are then treated as embeddings to the recurrent layers, and then it is passed through some transcription layer. The transcription layer here uses some CTC loss. So the problem with this model is evident that it lacks a language model. The way how human perceives handwriting is that they not only take the image signal, rather they also have a language understanding. So combining the image signal and language understanding, they are able to generalize well. Taking inspiration from this, there is a need of a language model. So we need the model to understand the language itself. And then comes the second attempt. To the best of our knowledge, this was the state of the art, the previous state of the art in Urdu handwriting recognition. So the model is quite similar to the previous one, but the authors also proposed an n-gram language modeling technique. Of course, after the advent of deep learning, it is evident that deep learning language models perform better than n-gram language modeling, and so there is a room for improvement. Coming on to the next architecture that was also proposed, which somehow eradicate the previous problem. They used an LSTM decoder here. There's a convolution encoder and then an LSTM decoder. And of course, there is a use of attention as well. The authors proposed this model in order to have an inherent language model that is learned by the LSTM decoder here. Of course, when the sequence is quite long, the LSTM face the vanishing gradient problem. And so there is also a room for improvement. All in all, keeping in mind the previous research gaps, this was the model proposed by Microsoft, transformer-based OCR model architecture. It is completely replaced by a transformer, a vision encoder, vision transformer encoder, and then a language modeling decoder. So the use of transformer is that they use an attention trick, which has a complexity of n squared. It is a matrix multiplication trick, and almost all the transformer layers are linear or dense layers. Of course, with the presence of dense layer and huge architectures, these models tend to overfit quickly on the dataset if the dataset is if the examples in the dataset are not sufficient. So these models lack generalization capabilities when it comes to very small dataset. And so these models rely on heavy pre-training. So keeping in mind all these research gaps, we proposed or modeled the task of Urdu handwriting recognition as a sequence-to-sequence learning and proposed a conv transformer architecture that eliminated the need for a separate language model. And we proposed a deep learning architecture that trains simultaneously on Urdu printed and handwriting dataset to yield state-of-the-art result on the task of Urdu handwriting recognition. So this is our proposed model. We use convolution blocks. The image is first passed through some convolution blocks. Then the features extracted are treated as embeddings to the encoder of a transformer. And then we have a language modeling decoder. So the idea is that we present a convolutional block in order to enhance the generalization capabilities of the transformer. And of course, transformer also face the n-squared computational complexity problem. And so if we are doing sentence level Urdu handwriting recognition, of course, the sequence gets very large. So somehow the convolution blocks tend to reduce the spatial resolution and try to extract the relevant features from the image. These features are treated as embeddings to the encoder of the transformer, and then we have a language modeling decoder. This whole architecture is trained in a teacher forcing fashion, where teacher forcing would mean that we do feed the outputs to the decoder, but those outputs are right shifted to somehow increase the decrease the training time. And then during the testing of this architecture, we are using beam search. Of course, we need the most probable sequence at the end of the day and not the most probable or the best probable word or the token. So coming on to the data sets that we used, one was NUST UHWR dataset, which was the Urdu handwriting dataset, and also ADAB dataset, which is Arabic dataset. The statistics about the dataset are present in this slide. So coming on to the results, we compared with the previous state of the art, specifically on Urdu handwriting recognition. Here, the graph shows the character error rate. So keep in mind that lower is better here. On the right is shown our model, which is the conv transformer model. And on the left, you can see the conv recursive model with the n-gram language modeling technique. So on the training all the way towards the testing splits, our model performs marginally better. So coming on to the discussion, if you have a bit understanding of the Urdu language, I would like to show here 3 results. The top two are taken from Google Vision API. The middle ones are taken from the conv recursive model with the n-gram language modeling technique, and the last 2 ones are presented by us. So if you have an understanding of the language, you would see that the mistakes made here by both of the models, the Google Vision API and the conv recursive, is not present by our model due to the reason that we believe, or we argue, that the model is learning the language and somehow is not just taking the signals from the image, rather it also has the language understanding. So towards the conclusion and future work, conv transformer leads to better generalization due to the presence of convolution blocks and an efficient language model. Future direction includes the pre-training of our architecture on larger data sets before generalizing to a specific task. And the conv transformer encoder can be pre-trained on a vision task like ImageNet classification, and the transformer decoder can be trained on language-specific language modeling task. And that would be it for the presentation. Thank you. Any questions, please?
Thank you, Naman. So we have time for a couple of questions. Any questions from audience here? Anyone from online? Any question there? Because I have a few questions.
Sure.
So this language model, what you are talking is trained on what type of data? Like how big is the data?
So the data set is basically the NUST UHW. So let's take one data set. It's the Urdu handwriting data set. Not only it takes the image as an input, but also the ground truth. But keep in mind the ground truth is right shifted, and it is a technique named as teacher forcing. So we are forcing the decoder to learn the language while the encoder is giving us the relevant features of the image. And that's how basically an encoder-decoder transformer architecture works. So it's inherently learning the language as well as processing the image. like in neural machine translation. So this task is basically inspired from neural machine translation.
All right. Another question is on the beam search.
Yes.
This search, can you go to that slide?
Sure.
Yeah. So what is the complexity of this model? Like, is it like
Yeah. So beam search is basically the breadth first search algorithm, but of course we are using some heuristics. Like the normal beam search uses the beam length, and then we also use the length penalty and heuristics like that in order to decrease the complexity of the beam search. So of course, if we have like infinite beam length, then it would be very infeasible to use the beam search. So of course there are heuristics to control
the input is line, right? Or input to this one line.
So the input starts from the beginning of sentence token, and then this model works in auto-regressive fashion.
Okay. All right. All right. Any other question from anyone? If there is no more question, we can thank Nauman. Thank you, Nauman.
Thank you so much. Thank you.
Okay, so with this, we will move to the next presentation. That is by Felix Ott, is there. Benchmarking online sequence to sequence and character-based handwriting recognition from IMU enhanced pens. This is on online handwritten recognition. Over to you, Felix. Can you share your screen?
Yes, thank you. Can you see my screen?
Yes, please go ahead with your presentation.
Yes, thank you. So hello everyone, my name is Felix Ott from the Fraunhofer IIS in Nuremberg, Germany. And I'm going to present our journal paper about benchmarking online handwriting recognition from IMU enhanced pens for sequence-to-sequence and single character-based classification tasks. So I will first motivate online handwriting recognition and give then an overview of our proposed datasets. And next, I present experiments about the sequence-to-sequence and single character-based classification tasks. And I also propose results about data augmentation and different loss functions. So I will first differentiate offline and online handwriting recognition and go more into detail of online handwriting recognition from sensor-enhanced pens. So research about offline handwriting is very advanced, which is typically, for example, optical character recognition and is based on images. Online handwriting contains the spatiotemporal context where the data is a trajectory and is represented as a multivariate time series. The trajectory of the pen tip is typically gathered from a tablet device. And the data of online handwriting from sensor-enhanced pens is represented also as a multivariate time series of several sensors integrated in the pen. Hence, the information of the data is richer compared to the trajectory-based online handwriting, as the motion dynamics of the hand and with that of the pen can be gathered. In our paper of reference 1 here, we combined, for example, offline handwriting with online handwriting for sensor-enhanced pens. And applications of an online handwriting recognition from these pens range from graphomotoricity, which is important for the learning process of children, for example, also important for Parkinson's disease identification or hand-air writing also. So typically, stylus pens are used together with the touchscreen surface, but the writing style is influenced by the surface. State-of-the-art pens with integrated sensors exist here, but they are mostly only prototypical, while the pen provided by Stabilo, presented on the next slide, is a finished product that can be applied in real-world applications. The sensor-enhanced pen live streams to a connected device via Bluetooth and is built with a front accelerometer and a rear accelerometer, a gyroscope at the front, a magnetometer. Each of the sensors stream in X, Y, and Z direction, and the force sensor allows to measure the force and separate the words. The ground truth labels are provided by a recording app. And more details, if you're interested about the pen, you can have a look at the input publication here. And so what are the challenges of online handwriting with these pens? These challenges do typically not appear in that amount for offline handwriting recognition, and which makes the task of online handwriting recognition interesting for research. So first, as there are arbitrarily many possible holding options of the pen, it is difficult to generalize the gyroscope data. And this appears, for example, between beginner and advanced writers. And second, the magnetometer data depends on the writing surface. For example, it's different for writing on tablet and for writing on paper. And next, there exists a lot of different writing styles, for example, cursive or printed writing. And related is that characters consist of different strokes that can be ordered arbitrarily with different writing directions. And next, the microscopic elevations of the paper lead to a noise in the sensor data, which is also not present for offline handwriting recognition. And last, there exists a domain shift between sensor data from different writers, particularly between right-handed and left-handed writers. But we will see that also later. So for the task of online handwriting recognition, we collected a large variety of different data sets, the ONHW database. We initially published the ONHW JARS dataset, which contains lowercase and uppercase single characters. The ONHW symbols dataset contains also single letters, but symbols and numbers. The ONHW equations, words 500, words random, and words trajectory dataset contain sequences of letters, so basically words and equations, while the ONHW equations dataset contains more than 10,000 samples of mathematical equations from 52 writers. The words 500 dataset contains the same 500 words per writer, and the ONHW words random dataset contains randomly selected words. And last, the ONHW words trajectory dataset is written on a tablet with the sensor-enhanced pen that allows to compare for writing on different surfaces. We additionally published the datasets containing left-handed writers. Here, the number of writers is significantly smaller compared to the right-handed datasets, but this approximately matches the real-world underrepresentation of left-handed writers, which is approximately 9%. So the first challenge is the large variety of sample length of sequences, which is also present in state-of-the-art trajectory-based datasets such as the VNONDB and IMONDB datasets. Also, the distribution of characters varies, for example, for the ONHW equations dataset. And this is also present for the single characters. So while the ONHW JARS dataset is equally distributed, and also the ONHW symbols dataset, which is smaller in size, that's the split ONHW equations dataset, which is basically the ONHW equations dataset just split into single numbers and symbols. This dataset is also unequally distributed. So this slide presents exemplary sensor data. So this is, for example, a sensor data of the label of the equal sign. This shows exactly, so through the force sensor shows exactly the two different strokes. These two figures show an exemplary equation and an exemplary word. The equation shows that it can be separated through the force sensor into single characters or numbers and symbols, while the word cannot be separated into single characters as it's cursively written. And comparing the sensor data for writing on paper and for writing on surfaces of tablets shows that the writing on the tablet is smoother, and hence the noise in the signal is less, particularly for the accelerometer. So in the following, I will present results of our benchmark due to the short amount of time, I will highlight only the most important results. So for evaluating the sequence classification tasks, we report the word error rate and character error rate, and we use the CTC to train the sequence-based tasks. This table shows results for the ONHW equations, words 500 and words random datasets, for the writer-dependent and writer-independent classification tasks. When we benchmark a large variety of methods based on convolutional architectures in combination with recurrent layers. So while our implementation of inception time in combination with a BiLSTM layer results in the lowest character error rates and also word error rates for the ONHW equations dataset and for the words random dataset. Our method of a CNN plus BiLSTM outperforms other methods on the words 500 dataset. And as the writer-independent task is more challenging than the writer-dependent task, the error rates significantly increase. For example, here from 1.65% to 11.28% for inception time. When we analyze the character error rate for each writer, here for the ONHW equations dataset, we see that there are several writers for which the character error rate is very low. For example, here 8, 9, 10, 11. While for other writers here from 36 to 39, for example, the character error rate significantly increases. This is due to different writing styles of different writers and the model overfit on specific writers. Furthermore, we evaluated 5 different data augmentation techniques for a more generalizable training. So the summary is that time warping, which warps the sensor data in the time direction, has the highest positive impact and reduces, for example, here for the ONHW equations dataset, the character error rate from the baseline of 3.5% to 3.18%. These two tables summarize the single character-based classification results, where the simple recognition rate in percent is the evaluation metric. So we evaluated a large variety of 28 different architectures, and our CNN in combination with a recurrent unit outperforms other methods. Here we evaluated LSTM, BiLSTM, and TCN layers, but the results depend on the dataset, and it's also a tuning of the hyperparameters. While we previously trained the methods with the cross entropy loss for the single character classification tasks, we further evaluate different loss functions here. As I presented previously, the equations dataset is unequally distributed over the class labels, and this is not well represented by the cross entropy loss. And the summary here is that label smoothing and joint optimization most significantly increases the baseline classification results. The loss functions had an impact on the training, as the class labels are not equally distributed here of the datasets, especially for ONHW equations. And I summarize our contributions in the following. So we recorded and published a large variety of different datasets for online handwriting recognition. We proposed a benchmark of different architectures for the sequence-to-sequence classification tasks, especially words and equations, and for the single characters. We evaluated data augmentation and different loss functions, and we analyzed real-world challenges, which is interesting for future research. For example, the domain shift between tablet and paper, and also the domain shift between right-handed and left-handed writers. Here are our fundings, and the data sets are available. I try to keep the data website up to date and also consistently publish source code there if you're interested in further research. These are our main references, and thank you for your interest in our paper. And now I'm available for questions.
Thank you, Flex. Yeah. There is time for a couple of questions. Any question from online audience or offline here? So I have a few questions.
Yes.
So on this online handwritten data sets, do you observe some kind of domain shift across like age groups or maybe geographical ways? Do we have such data sets?
So the data sets are all recorded in Germany. So
okay.
In
terms of age,
graphical domain shift is not present. And with respect to the age, so we recorded for these data sets only adults above an age of 18, but up to an age of 70. So it does not depend on the age, but it depends on the writing style, and people with an age of 70 most probably write different to people with an age of 18. So, and this is represented by also the results. So there's a domain shift between the writer, also for only right-handed writers, only because of the different writing style, and especially between left and right-handed writers because they hold the hand different, and this results in different accelerometer and gyroscope data.
All right. And in terms of performance, like when it is trained on, let's say, one writer and tested on other writer, do you see a huge gap, or is it like?
It depends on the writer ID. For example, if you train and test on writer 24 to 34, it should work. The accuracy, the error rates drop or increase only slightly. But if you select randomly writers that write very different, then it's obviously not possible. But we also tested to post-train and adapt on new writer, for example, on left-handed writers, and it works quite well.
Okay,
does that answer your question? Thanks for the question.
Any other question? If not, thanks for your nice work. I think this data sets will be really useful for this online handwritten recognition community. We'll move to next presentation now. This is the final presentation in this session. This is by Arpita Datta, and Arpita will be presenting her work on BCBID, first Bangla comic dataset and its application.
Hello.
Yeah, all right. Can you share your screen?
Yes, sir. Is it visible? Hello.
Yes, it is.
Good morning, everyone. Good morning, everyone. Thanks a lot to ICFHR to give me the opportunity to present my work here. I am Arpita Datta, a research scholar pursuing PhD at the Department of Computer Science and Technology at Indian Institute of Engineering, Science and Technology, Shibpur. Today, I am going to present some research foundation on comic analysis. Basically, the curation of a new comic dataset, which is the first dataset among Indian language. We have considered Bangla, and also we demonstrate some applications of comic research apart from some new applications on comic research apart from the traditional research. So let's here's a brief outline of my entire presentation. So let's start. Before going to the details, just let's see what is actually comics. Since all of our childhood, all of us read comics, but nowadays comics is not only an entertainment medium for children. Actually, it's a very essential medium to convey the complexity of any issues aesthetically. So according to the storytelling secret of comics, the main definition is actually it is a medium through which human condition can be depicted in a brilliantly minimalistic way through the image and text embedding, so that it creates a long-lasting impressions among a huge number of audience from 8 to 80. So the basic motto of creating comics is to drive the attention from the readers. While designing comics, the artist basically think about using several visual components. Those are standard components for designing comics in order to illustrate the entire storyline aesthetically. These are the components. See, this is a typical comic book page. This is panels things through which the entire storyline actually propagates. The characters, these are the protagonists of the stories, and this speech balloon things actually represents the conversation between the comic characters, and the girders are the separators of the panels, and so on. So let's focus on the comic research background. Actually, since the last decade, a couple of researchers from academia industry have focused on comic analysis. However, the visual components are in various shapes. There are wide variety of shapes. So retrieval of these comic components and the analysis is very challenging. So most of the research work still today on comic analysis have focused on content analysis and their retrieval kind of things. This is a diagram of which actually summarizes the comic research part. This is taken from Olivier et al. Survey paper on comic research. But the main focus is on content analysis till date. However, there is a lots of open areas to be explored for comic analysis in order to provide a user-friendly experience to the readers while they read them in digitally. These are the sentiment or emotion analysis of comic stories, online automatic content adaptation tool, or comic video summarizations. These are some open research areas that need much attention from the researchers, and it is a multimodal interaction domain. So researchers can various domains, from document image processing to computer vision to natural language processing to speech processing. They may get interest in exploring this field. So these are the challenges associated with comic research. First challenge is to mitigating the copyright issue for collecting the data set, because comic is the own creation of authors. So if the copyright is expired or the permission is properly granted from the authors, only then these images can be used for further research. So for 4 publicly datasets are available, that EBDQ, manga, DCM, and comics. And this manga is for Japanese comics, and EBDQ, DCM, and comics. This EBDQ is French and English, and DCM and comics are English comics, for which either the copyright has been granted or it expired. But there are 2 private datasets, GNC and VLSC. Their corpus is available, but the images are not available due to not resolving that copyright issues properly. So another challenge is for Indian language, there is no publicly available data set for pursuing research on comics due to that copyright issue. And another challenge is most of the research only focus on that content analysis part. So to explore any new field on comic research is a challenging part, because there is no available data for pursuing on these kind of things. So after observing this scenario, here we just present a new data set of comics, which is first among Indian language. That is, we have considered Bangla for the time being. This is not a very breakthrough scientific contribution, but it's a needed one for pursuing research. So we will try to provide a description and a detailed annotation procedure for curation of this data set, and believe that it will provide a lot of insights to the research community. And the second thing, we have also demonstrated some already proposed visual analytics tasks on comics. We will evaluate the result in this data set which we have created. And we have also proposed a method for sentiment analysis of the comics. To the best of our knowledge, we are the first to propose this method based on textual content analysis. So this is the our data set, BCBID data set, that Bangla comic book image data set, which is a collection of 3327 images till of now, from 64 Bangla comic stories and from 8 writers. And it includes a wide variety of images and also various shapes and dimensions. And this is also made publicly available on website. And due to copyright issue, we have collected those Bangla comics which are actually available in web comics with this link, for which the copyright has either granted or expired. And some of us, we have collected from hard copies. That thing we have taken the required permission. And we have also included some Bangla translation of English comics like Tintin, Jungle Girl, and Mandrake. We have also included in our data set. Now, the annotation purpose, we have considered annotations for pursuing research in 2 different domains. First one is obviously content-based analysis, because retrieval of those various types of shaped element is challenging. So, and the second part is for encoding the underlying semantics of those images in a proper structured way, so that it can be used for pursuing further research like sentiment analysis or automatic comic content analysis or automatic comic scene analysis, etc. And these are the content-based analysis kind of thing. One thing I have to mention, the already available data set, no data set provides the annotations for each and every type of visual element of comics. Suppose some data set provide annotations for panel characters, speech balloons, that is panel characters, and narrative text box, that is bounding box annotations. Others provide annotations for speech balloons, though they are various kind of shapes. They just provide annotations for bounding boxes. So seeing this, we have tried to generalize the annotation for each and every shaped elements for pursuing research on content-based analysis of comics, like panel characters and text boxes. This can be done through bounding boxes. However, speech balloons have a huge variety of shapes, so that shape can be captured through polygonal annotations only. So these are the things we have provided here, and we have done this famous publicly available tool, that is VGG annotation tool, and export it into CSV and JSON format for using them further. And error rectification we have also done, because when many people are engaged in developing ground truth, it is a possibility that it may occur some error. So in our case, 15 people are engaged. So we have taken a threshold value 0.35% of page width and height. that is used for error calculation, and we have also calculated the mean value for each corner point from those 15 values, and we have seen that by setting this threshold value, the error actually limits within 5 pixels from the corner points and the mean position. So next is that CBML based XML annotations. This thing we have provided first for comic research, because to encode the underlying semantics, let's just check, like for speech balloon, like this balloon tag actually incorporates all the information associated with speech balloon, like who is the speaker of the speech balloon, or what type of speech balloon it is, and the corresponding text will be embedded within that tags, so that it can be used later for further research. And by these tags, all the elements are encoded, like and also there are tags for encoding metadata like FW, which denotes the end of a particular page. There are also tags for encoding graphic sound, like sometimes a single sound like boom, splat is used for describing an emotions. That emotions are also incorporated separately, so that it can be used for video comic style video generation or comic style video summarization. So keeping this on mind, we have encoded the entire structure using these 13 tags. Let's check this example. Here is the image. I know this is Bangla text. For the time being, just ignore the text, but just think that this is the first speech balloon, like this balloon types is speech. This is the character name Captain Who, and this is the ID, that is the first balloon. Similarly, through this panel tag, entire panel hierarchy is incorporated, like there are 2 characters and this is the first panel and so on. Now the thing is, if we want to just incorporate these tags manually each and every time by typing those tags and the attributes, then it may occur some error. That's why we have also developed a graphical user-based interface, which actually controlled by these 9 buttons and these text fields also. So that each time a button is just clicked, the corresponding attribute value, the user can also input that value, and in the back end it will be automatically retained in this XML structure. Like if we just click add balloon, it will actually incorporated balloon type. It will show a dialog box for entering the value for type field. Then it will also show a dialog box for entering the value for this attribute, and so on. And automatically in the back end it will be written in like this structure, and the text field will also incorporate the text information here automatically. And we have also used here a UTF encoding, so that it can incorporate the text in any language. The tool is available in this link. So here is an annotation summary for our data set. That is CAP means content annotated pages. We have total 1057 content annotated pages. These are panel characters, balloon, text boxes and narrative text boxes, and these are total XML annotated pages. Like we have also 2032 total number of XML annotated pages. And till today, this is the summary of that our data set. And next we will also demonstrate some research work on content-based analysis evaluated on our dataset, and that is the previous work for speech balloon detection and narrative text box detection. And for panel and characters, for the shortage of time that they are in the paper, we have not included here. Next, sentiment analysis. As we have already said that we first addressed the challenges. So this is the challenge. Main challenge lies the informal text and the complex writing pattern, as it is comic stories. So every time the author don't always complete the sentence, or it also incorporates some ambiguous meaning. So, and another one main challenge is that limited publicly available data. So in natural language processing based on machine learning is a very challenging task for this purpose. So for the time being, we have considered a lexicon-based approach for sentiment analysis of comic stories based on textual content. Here is a brief outline that we have pre-processed the raw text with this procedure. We'll explain through examples. And then polarity detection, we have calculated the respective sentiment score and assign the the designated level. Let's just check. This is an Bangla text, as English is an international language. So this is the translated text from that Bangla text. So just check the example, that tokenization thing, that I can do this job very well. You just wait for much fun. In first tokenization step, each token is separated. Then at the punctuation removal, first that exclamation and the full stop will be removed. Rest of the token will remain same. At the stop word removal, you, I, can, do, these stop words can be removed, because in sentiment analysis, as it is completely based on a lexicon dictionary, these words don't play any additional role. So just remove these stop words and just keep the rest of the token. Next is stemming. In lexicon dictionary, every word is stored in their root form. Otherwise, a word should be written in many other forms. So in stemming purpose, the root word should be retrieved so that it can be further matched with lexicon dictionary to retrieve the associate polarity and the sentiment score. So for the time being, every token is in their root form. So in stemming, it will remain as it is. And that polarity detection of words, that lexicon dictionary senti wordnet, this is for Bangla and English, both the dictionary is there. In those dictionary, by consulting this dictionary, each token, the sentiment word will be associated with their respective sentiment score and their associated polarity, whether it is positive, negative, or neutral. For the timing, we have considered those three, positive, negative, and neutral, as matched with the lexicon dictionary. So before proceeding to the sentiment score calculation, there are some special checking also, like these many, much, few, very, most. These are some priority words, like I can do this job very well. Well is a positive sentiment word. So when it is associated with very, the associated sentiment score should be increased. That means it is strongly positive. The positivity should be increased. Similarly, inversion check, like there are some inverted words, not, never, which is when associated with a negative sentiment word, the resultant is positive. So it should be checked carefully. Like I do not work badly. If bad is a negative sentiment word, and when it is associated with not, that means negativity will be inverted. The entire meaning will be positive. So that's why we have to check these special cases also. So these are the computation method for every.
Can you summarize, in interest of time, can you summarize in couple of
sorry, sir. For every token, the sentiment score is calculated like this. If the priority words exist, it will just double the sentiment score, and if inverted word exists, and negative the sentiment score. And through which that normalize between -1 to +1, that -0.2 to -1 negative sentiment, 0.2 to 1 positive sentiment, and -0.2 to -0.2 neutral sentiment. So these are the some instance, like just say both of them are writing with great joy in their minds. These are actually positive sentiment. That joy and great both are positive words. These are the total number of positive, negative, and neutral sentiments in our. These are the graph related to accuracy, that precision, recall, and F score. This is the performance evaluated. This is our method. And conclusions that we have represent a first ever collection of Bangla comic data set and propose a lexicon based method. In future work, we'll try to overcome this lexicon based method through some multimodal sentiment analysis kind of thing, so that it can be done through some machine learning or deep learning based approach, and we'll also try to increase the data set and annotations continuously. So these are the reference. Thank you for listening.
Thank you. Yeah, thanks. Let's thank Arpita. And if there is any question, one quick question, if you can, anyone have? No. All right, then let's thank Arpita for her presentation. And let's thank all the speakers. With this, we conclude this session. We'll break for coffee. So I think organizers will. There is a coffee, right? Yeah, there's a coffee outside. So we'll break.